Data science is the hottest job of the 21st century, and Python is the hottest programming language of the 21st century. And that is why the average salary of a data scientist is around $120,000, and the average salary of a Python developer is $100,000. So it's pretty obvious that anyone who has skills in both data science and Python would be in great demand in the industry. And that is why we have come up with this full course on Python for data science. Now, before we go ahead, I'd like to inform you that we'll be coming up with a series of high quality tutorials on artificial intelligence and computer vision. So please do subscribe to Create Learning's YouTube channel and click on the bell icon so that you have a notification of our upcoming videos. Now, let's have a quick glance at the agenda. We'll start off by working with the basics of Python, such as variables, data types, and operators. Then we'll go through Python's data structures, which are tuple, list, dictionary, and set. After that, we'll learn how to do numerical computing with NumPy. Going ahead, we'll work with the pandas library to implement data manipulation operations. Following which, we'll do data visualization with the matplotlib library. Once we are done with these, we'll head on to the data science part. We'll start with our first machine learning algorithm, which is linear regression. Then we'll learn how to do binary classification with the logistic regression algorithm. After that, we'll work with naive Bayes algorithm, which is a probabilistic classifier. Going ahead, we'll start off by understanding what is unsupervised learning. Following which, we'll understand the concept of clustering. And finally, we'll work with k-means and hierarchical clustering. So let's start off with the session. So let's start off by installing Python, and we can install Python from this website over here, www.python.org. So I'll click on this. All right, so you see that you have the latest version of Python over here, Python 3.8.0, and you can download the Python version with respect to whatever operating system you're using. So if you have a Windows system, then you can download Python for Windows. If you have a Linux or Unix system, then you can download Python for Linux or Unix. And if you have a Mac operating system, then you can download Python for Mac operating system. And since I have a Windows system, I'll download it for Windows. So I'll just click on this over here and you see that the download has started. Right. So now I actually have Python installed in my system. So once the installation of Python is done, we need something known as an IDE. So IDE basically stands for Integrated Development Environment. And Integrated Development Environment basically makes your work much easier while programming. So it gives you certain prompts and you have all of the tools present in the IDE. And one such IDE, which is very famous for Python, is PyCharm. So we can install PyCharm from the site over here, jetbrains.com/PyCharm. So let's just wait till the site opens up. All right, so you have the download button over here. You just click on this. And for our programming purpose, we'll just download this community version over here, right? So for pure Python development, you click on download and the download would start. And again, since I'm using a Windows system, so this is for the Windows system over here. All right. Now, Anaconda is a Python distribution, which basically provides you all of the packages inbuilt. So you have packages such as Matplotlib for visualization, Pandas for data manipulation, and NumPy for numerical computing. So you don't have to manually install all of these packages. So when you actually install Anaconda, all of these packages are actually pre-installed in Anaconda. And for doing all of your coding, you have something known as the Jupyter Notebook. So first to use a Jupyter Notebook, we would need Anaconda. So let's go ahead and install Anaconda. Right, so this is anaconda.com and I'll just click on download now. So we need the Anaconda distribution. And again, I'll click on download, right? So we've got Windows, Mac OS, and Linux. And this is the latest version of Python 3.7. So that is what we had downloaded earlier. So this was the older version of Python 2.7, but everyone has moved on to Python 3.7 now. And that is why we'll also be downloading Anaconda for the latest Python version, which is Python 3.7. So we'll automatically start the download for 64-bit operating system. So once the download for Anaconda is done, we need something known as the Jupyter Notebook, which I've already told you. So as it is written over here, Jupyter Notebook is basically a browser-based interpreter that allows us to interactively work with Python. And this is how your Jupyter Notebook looks like. So let me go ahead and open up Jupyter Notebook. Right, so let me open up Anaconda prompt first. So I'll type in Anaconda prompt. So this is the command line interface. Now to open up Jupyter Notebook, I'll just type in Jupyter space notebook and let me wait till this opens up. All right, so this is the Jupyter Notebook over here. right? And this is how it looks like. Now to open up a new notebook, we just have to click on new and we'll click this new Python 3 notebook. And we have successfully opened our new Python notebook. Let me just rename this to Python programming. Now, once this is done, let's go ahead and write our first Python program. So we'll just use the print statement. So you just have to type in print, and inside this, I'll type in, let's say, this is Sparta. And all you have to do is click on run, and you have your first program ready. You have successfully printed this Sparta on the console. Well, you've just taken the first step to hacking NASA, right? So you just have to take the baby steps and you'll be an expert at Python programming, and you have successfully started with your first Python program. All right. So now that we have written our first Python program, the question which needs to arise in your mind is, every programming language needs to deal with a lot of data. So where do we actually store this data? Well, this is where variables come in. So let's say you have to store the names of all of the students present in a classroom. So let's say the names are John, Sam, Matt, Bob, Anne, Julia, and so on. And you have 50 such names. And you have to store all of these names somewhere. So how do you do it? Well, all you have to do is take a variable and store all of these names in a variable. Now, you must be thinking, what exactly is a variable? So let's understand that with this example. So simply put, variables are basically temporary storage spaces where you can store data or values. Now, let's take this example over here. So consider this folder to be a variable. So what you do is you store this value temporarily inside this folder. So this value is John, which is the name of the student. So you've taken this value and place inside this variable for a certain amount of time. Now after that, since this is only a temporary storage space, you can take out this variable and replace it with Sam, right? So now this variable holds the value Sam. And after some time, again, you decide that Sam is not the name which I want to store and I want to store the name Matt. So again, you take out the name Sam and store Matt inside this folder. So this is how variables work. They are temporary storage values where you can keep on changing the values inside it. So now that we know what exactly are variables, let's go to Jupyter Notebook and work with variables. So again, I'll open up a new Python 3 notebook over here. So now to assign a variable, I'll just create a new object over here and I'll name it as var1. I'll use the assignment operator and I'll give in the name. So the first name would be Bob, and to print it out, I'll just type in var1 over here again. Right, so we have successfully stored the value Bob inside var1. Now I'll change the value inside this variable. So what I'll do is I will actually store the value Sam inside this var1, and let me print it out again. So now var1 stores Sam. So initially var1 had the value Bob, and after some time I had replaced the value with Sam. Now again, let me change the value. So inside var1 I will be storing Matt, and let me print it out again. So this time it has the value Matt. So as you see, variables are just temporary storage spaces where the values can be changed. Now every variable is actually associated with a data type. So there are different types of data which a variable can hold. It can be of integer type, it can be floating or decimal type, it can be a boolean, it can be a string. So when it comes to integers, so you basically have numbers such as 10, 500, 1000, -10, -27, and so on. And floating are basically decimal point numbers, so 3.14, 15.97, or -2.1678. So any such decimal point number would be a floating point number. And then you've got Boolean values, or basically logical values, and true and false are basically your Boolean values. And then you finally have the string values. So a string is basically a set of characters enclosed together, right? So Sam is basically a set of characters, it is a string. And then you have Matt, which is basically a set of characters, it is a string. And strings are generally enclosed within double quotes, single quotes, or triple quotes. Right, now let's assign some different types of data to our variables. So let me create a new variable A, and I'll store the value 10 inside this. Now I'll go ahead and check the type of this. So the type of this variable would be int. Now inside A, I'll actually store a decimal point number. So this time I'll store 13.4, and then let me check the type of it. So type of A, again I'll click on run. So this time we see that it is a floating point number. So what you can basically notice is the type of the variable would depend on the type of the data which you are actually storing inside the variable. So if you store an integer type data inside the variable, then the type of the variable would be integer. And if you store a floating point or a decimal type data inside the variable, then the type of the variable would be floating type. Now similarly, let me go ahead and store a boolean value inside this. So I'll store true inside this. Let me check type of A. So the type of A is bool. Now let me store a character value. So I'll type hello world. Let me remove out this W over here. And then again, I'll check the type of this. So type of A. And then the type of A is string. So finally, we have one more type of data, which is basically complex number. So complex numbers, you basically know that it has a real part and an imaginary part. So let me just type it out. So 4 plus, let's say 8j. Now, normally in mathematics, it is actually represented as 4 plus 8i. Now, when it comes to Python programming, we represent the imaginary part with j. So 4 is the real part over here and 8j is the imaginary part over here. So just to confirm it, I'll again check the type. So type of A. The type of A is complex. So all of these are the different types of data which we can work with in Python. So going ahead, we'll work with operators in Python. So we've got arithmetic operators, relational operators, and logical operators. So let's start off with arithmetic operators. I'll head on to Jupyter Notebook over here, and arithmetic operators are basically the normal mathematical operations which you do. So that would be addition, subtraction, and then you've got division, and then you've got multiplication. So these are the different symbols which you'll be using to perform these operations. So we'll start off with addition. So let me just add in a comment. So to add in a comment, you will use this hash and then you'll type in whatever you want to add. So comments are basically statements which are not executed by the Python interpreter. And these are only to help the coder or the learner. Right. So I'll execute this cell over here. So I'll have one variable and I'll store 10 inside this, and I'll have another variable B. I'll store 20 inside this. I'll click on run. All right. So I'll start with addition operation. So I'll just type in A plus B and you get the value of 30. Well, this is quite simple. So this is the basic addition operation which you've been doing since your kindergarten, right? And also we'll be doing some similar operations. And then I'll go ahead and perform A minus B. So what do you think is the answer? Well, it's minus 10, because when you subtract 20 from 10, you'll get a value of minus 10. Now let's also multiply these two numbers. So I'll just type in A cross B. So that would be 10 into 20, which will give you 200. And then finally, I'll just type in A divided by B. So you'll get a value of 0.5. So 10 by 20 gives you a value of 0.5. So these were the basic arithmetic operations. Now we'll go ahead and work with some relational operators. So I'll just type in relational operators over here. So again, I'm putting down a comment. So relational operators. And relational operators basically help you to understand the relation between two variables. Now, what do I mean when I say it helps us to understand the relationship between two variables? So let's say when you have two variables, the value in one variable could either be greater than the value in the second variable, or it could be less than the value in the second variable, or it could be equal, or there might be no relation at all between these two variables. So this is where we'll have relational operators to find out what is the exact relation between two operands, right? So again, I'll just type in A equals 10 and B equals 20 over here. I'll click on run. Right, so I'll start with the less than operator. So I'll type in A less than B. So over here, I'm just checking if the value of A is actually less than the value of B. So we get a value of true. This means that 10 is actually less than 20. Now let me check if A is greater than B. Now we get a false value because 10 is not greater than 20. Now I have the double equal to operator. So with the help of the double equal to operator, we check if both of these values are equal to each other. Again, we get a false value because 10 is not equal to 20. Now there is the not equal to operator. So A is not equal to B. So A, I'll give in this exclamation mark, and then I'll give in this equal to symbol, and then I'll give the second operand, which is B. So we see that A is obviously not equal to B, or in other terms, 10 is not equal to 20. So these were some basic relational operators. And then we'll go ahead and work with the logical operators. So I'll type in logical operators over here. So the two basic logical operators are AND, OR. And this is how you represent the AND operator, and this is how you represent the OR operator. Now we'll actually start with the AND operator. Now AND operator is used to check the condition or the logic between two variables. And this is how the AND operator works. So if both of the operands are true, only then the final result will evaluate to true. And if either of the operands is false or both of the operands is false, then the final result will be false. So I'll just create two variables over here, and this time I'll be storing the value true inside A, and I'll be storing false inside B. So I'll just execute this over here. All right, so now I'll type in A and B. So we are basically checking true and false. So what do you think will be the result? We get a false value because we need two trues, and only when we have two trues, that is when we'll get the true value. Now we'll check B and A. So when it comes to B and A, we are basically changing the position of these operands. That's it. So now it becomes false and true. And the answer is false. Now let me check A and A. So this will be true and true. So when you compare true and true, you get a true value. And finally, let me check B and B. You get a false value. So this is how the AND operator works. Now let's go ahead and work with the OR operator. So when it comes to the OR operator, if either of the operands is true or both of the operands are true, then you get a true value. And only when both of the operands are false, that is when you'll have a false value. So this time I'll type in A or B. This would mean true or false. And obviously we have a true value over here. Then I'll type in B or A. So this would mean false or true. And we obviously have a true value. Now let me go ahead and check A or A. So this would mean true or true. So when you have two trues, obviously it's a true value. And then finally, let me check B or B. And we have a false. So this is the only condition where you'll get a false value when it comes to OR. Right, so those were the basic operators in Python. Now let's head on to Python strings. So Python strings are the most widely used data types when it comes to Python. And as I've already told you, strings are basically sequence of characters which are enclosed within single quotes, double quotes, or triple quotes. And triple quotes are used to denote multi-line strings. So as you see this example over here, I am going to France tomorrow. So you have triple quotes around the string because this is present in multiple lines. So hello world is present in single quotes. This is a string. This is Sparta is present in double quotes. And again, this is a string. But when it comes to I am going to France tomorrow, this is a multi-line string. So that's the basic premise for strings. So now let's go to Jupyter Notebook and work with these strings. All right, so I'll create a new variable over here and I'll store a string inside this. So I'll put in the string Joey doesn't share pizza. I'll click on run. All right, so obviously no one likes to share their pizza, do we? Right? So now let's go ahead and work with the string. So let's say I'd want to extract the first character, which is J, from this entire string. Now when it comes to Python, the indexing starts from 0. So J is basically present at index number 0. So if I want to extract J, I'll type in A1, I'll put in square braces, and then I'll type in 0. And I have successfully extracted the first letter. And similarly, if I want to extract the last character from this entire string, so for that, you'd have to put in -1. And when I click on run, you get the value A. So this is how you extract the last character from the entire string. Now let's say I want to extract a sequence of characters. So I'd want to extract this entire word, which is doesn't. So 0, 1, 2, 3, 4, 5. So the index starts at 5 and it will go on to 6, 7, 8, 9, 10, 11, and 12. So let me type in 12 over here. I'll click on run, right? Now over here I have given 12 because when it comes to the second term over here, it is exclusive. So 5 is inclusive, 12 is exclusive. So 0, 1, 2, 3, 4, 5. D is present at index number 5. Then 6, 7, 8, 9, 10, and 11. So T is present at index number 11. But if you only given 11 over here, then you'll get dozen, right? So what you have to keep in mind is when it comes to the second indexing term, it is exclusive. So that is why you'd have to go in del 12 and you'll get the entire word, which is doesn't. Now let's see how can we check the length of a string. So to check the length of a string, we have this length function. So inside len, I'll just pass in this variable, which is a1, and we see that the length of the string is 24 characters. Now when you say 24, so this would include all of the spaces and all of the apostrophes and full stops and all of those characters as well. All right. Now let's go ahead and work with some of the inbuilt functions of strings. So if I want to convert all of these characters into uppercase, so I'll just have to type in a1 and then I have this function upper. So I'll click on run, right? So I have successfully converted all of these characters to capital. Now similarly, if I want to change all of these to small case, so I'll type in a1 dot lower. So everything is turned to lowercase. Now similarly, if I want title case, so I'll type in a1 dot title. Right, so I have successfully changed all of these words to title case. So J is capital, D is capital. So over here, since apostrophe is taken as another character, that is why T is also given capital. And then we have S as capital and P as capital. Right, so these were some basic functions when it came to strings. Now let's go ahead and work with some non-primitive data structures in Python. So the main non-primitive data structures in Python are tuple, list, dictionary, and set. So when it comes to all of these data structures, so you can store multiple elements inside one data structure. So till now we've worked with only variables, and when it came to variables, we could store only one value in one variable. Now let's say if you go to a music concert and you'd have to store the names of all the people attending the music concert, and the strength of the audience would be around 10,000. So to store the names, you would require 10,000 variables. Now that's a lot of variables and you'd have to manually store all of these names inside 10,000 variables. So that's a humongous task and that's a tiresome task. So this is where you would need these data structures where you can store multiple elements inside one single data structure. So we'll start off with the first data structure, which is basically tuple. So when it comes to tuple, it is an ordered collection of elements enclosed within round braces. So we have CuriousJSON over here and he'll be coming in between to give us some pointers. So CuriousJSON tells us that tuples are immutable. Now, what does he mean when he states that tuples are immutable? So basically when you go ahead and create a tuple, so let's say you add 5 elements inside one tuple. Now, you can't change or modify the tuple which you have created. So that would basically mean that, let's say if you have 5 elements, then you can't change the value of the second element or the third element, or you can't add another element inside the tuple which you have already created. So this is basically the immutability nature of tuples. And this is how you can create a tuple. So you'll use these round braces over here, and inside these you will given the values, right? So as you see, tuple is actually a heterogeneous data structure. So over here you are storing a numerical value, a character value, and a Boolean value. Right, so let's go to Jupyter Notebook and work with tuples. So let me create a tuple. So I'll name the tuple as tup1 and I'll give in the values. Right, so this is our tuple tup1. Let's see how can we access individual elements from this tuple. So accessing elements from tuple is the same as accessing elements from a string. So all you do is, given the name of the tuple, which is tup1, you given this square braces, and then if you want to extract the first element, which is basically present at index 0, you'll type in 0 over here, and you have extracted the first element, which is 1. Similarly, if you want to extract the last element, you have to type in -1, and you have extracted the last element, which is 23. And if you want to extract a sequence of elements, so let's say I want A, true, and B. So this would be from index number 1 going on till index number 4, because we'd want 1, 2, and 3. So I'll type in 1:4, right? So I've extracted A, true, and B, right? So this is how you can extract individual elements from a tuple. Now, as I've told you, a tuple is immutable. So let me go ahead and try to change the value which is present inside a tuple. So I'll type in tup1 and let me change the value which is present at 0th index. and I'll change it to, let's say, 100. And we get an error over here. So the error is tuple object does not support item assignment. And that is because tuples are immutable. Now let me try to add a new value inside this. So we've got 1, 2, 3, 4, 5. So that would mean this is index number 4. So let me try to add something at index number 5. I'll type in Harry Potter. Again, we get the same error. So tuple object does not support item assignment because it is immutable. Now we'll head on to the next data structure, which is a list. So lists and tuples are quite similar. The only difference is lists are mutable while tuples are immutable. Now, what do I mean when I say lists are mutable? So this means that lists can be changed once they are created. So if there are 5 elements in a list, so the second element or the third element can be modified. And again, since I've said that there are 5 elements, so another 5 elements can be added inside this list. So this is the basic difference between lists and tuples. And this is how you can create a list. So you'll basically given square braces and you'll given all of the values inside the square braces. So let's head on to Jupyter Notebook and work with lists. So I'll type in L1 and I'll give in some values over here. And then I'll print it out. Right, so this is a list over here. And accessing elements from the list is same as tuple. So if I want to access the first element, I'll type in L1, I'll give in square braces, and then I'll give in 0. So I have extracted the first element. Now let's go ahead and access a sequence of elements. So I want to access these 3 elements over here, true, 2, and b. So this is index number 2, and then going on till index number 5. So L1 and 2 colon 5. Right, so true, 2, and b. So we have successfully extracted these 3 sequence of elements. Now let me go ahead and actually change the values inside this list. So I'll change this value 1 to 100. So I'll type in L1 0 and I'll assign the value of 100. Now let me print out L1. So as you see, initially the value of this element was 1 and then we have changed the value to 100. Now let's say I want to add a couple more elements inside this list. So I'll type in L1.append and I'll add an element and name it to be, let's say, sword. And then let me print out L1. Right, so I've successfully added a new element. So now I can actually add a list inside a list. So let me again use the append function over here. And then I'll add a list inside this. So I'll type in 1, 2, 3, 4, and 5. So let me again look at L1. Right, so I successfully added this new list inside this list. Now we can also go ahead and remove these elements. So to remove the last element, we've got the pop function. So I'll type in L1.pop. So as we see, this last element has been popped out. Now again, let me type in L1.pop and let's see what will be popped out. Right, so this time this element sword has been popped out. Now let me have a look at the modified list, right? So we are only left with these values because sword and this list has been popped out. So this is how we can work with lists. Now let's head on to the next data structure, which is a dictionary. So dictionary is actually quite different than a list and a tuple because it consists of key value pairs. And these are actually unordered collection of key value pairs which are enclosed within curly braces. And again, dictionaries are mutable. So this is how you can create a dictionary. So you'll put in curly braces over here. So first you'll put in the key. So over here the key is apple and then you'll give in a colon and then you'll give in the value. So for the key apple, the value is 10. And then you'll give in the next key value pair. So after comma, the next key value pair is orange 20. So orange is the key and 20 is the value. So let's go ahead and create our own dictionary. So let me create the dictionary over here. I'll type in D1 and then I'll give in these curly braces over here. So I'll just give in some names of fruits. So let's say the first key is mango and the price of the fruit would be the value. So mango costs 45 bucks. And then we've got apple. So let's say apples cost us 30. And then we've got orange and then orange costs around 77. After that, we've got guava. And then this would cost around 125. Now let me print it out. So this is our dictionary. Now what we have is key value pairs. So if I want to access only the keys, then we have the keys function. So I'll type in d1.keys. So I'll give in the name of the dictionary and then I'll follow it up with the keys function. d1.keys, right? So I have extracted all of the keys, which are mango, apple, orange, and guava. Similarly, if I want to extract all of the values, which are basically the price of all of these fruits, I'll type in d1.values. And I have extracted the prices of all of these fruits. Now let's go ahead and modify some of these elements. So I want to change the cost of mango. So I'll type in D1 and then I'll give in the name of key. So the name of the key is mango and the cost would be 100. And then I'll type in D1. So initially the cost of mango was 45 and then I've altered it to be 100. So this is how we can work with dictionaries. And then we've got the final data structure, which is a set. So a set is an unordered and unindexed collection of elements enclosed within curly braces. So what do I mean by unindexed? So when I say unindexed, this basically means that sets don't have any index to it. So we can't really access the elements with respect to their indexing. And also another thing to be noted is sets do not allow duplicate values. So let's say if you add a value 10, then you cannot add the same value again. So it will take the value only once. And this is how you can create a set. So you'll have curly braces over here and then you'll give in all of the elements inside it. So let me create my final data structure over here. So I'll type in 1, A, and then I'll give in a floating point value, let's say 3.78. Let me print out the set. So this is our set over here. Now what I'll do is I'll copy this and let me try to add some duplicate values. So I'll add 1 all of these times and then I'll also add A. Now let me print out S1 and then see what value do I get. So we see that duplicates are not allowed. 1, even though I have given around 5 or 6 times, it has been taken only once. And A I've given 2 times, but then again it comes only once. So obviously set does not allow any duplicates inside it. Now let me go ahead and add some new values inside the set. So I'll type in s1.add hello world. Right, so I've added this new element. And if I want to add more than one element at a single time, then we've got this update method. So I'll type in s1.update and I'll give in a list of values. So I'll type in, let's say, Sparta, and then I'll type in 123. Then I'll give in, let's say, 3 plus 9j. Then let me print out S1. Right, so all of these elements have been added. Again, you see that the order of these elements is not preserved. It is random, right? So 3 plus 9j comes over here and then we've got 1, 123, right? So the random is not at all preserved. Right, so we are done with the basic data structures in Python, which were basically tuple, list, dictionary, and set. So now we'll head on to the flow control statements. And in flow control statements, we'll start with the if statement. So in real world, you will come across a lot of situations where you'd have to make a decision on the basis of a condition. So let's say if this happens, then you'd have to perform a set of actions. Else, you'd have to perform a different set of actions. So let's take this example to understand this better. So let's say it's raining and you'd want to play football. So if it's raining, then you can't do anything and you just have to sit inside. Else, so if it is actually not raining, then you can go out and play football. So these are some of the real world situations which can actually be represented in programming with the help of if-else statement. So let's go to Jupyter Notebook and work with if-else. So here I'll create 2 variables. So I'll give in the value of 10 to A and I'll give in the value of 20 to B. And then let me check if the value of B is actually greater than the value of A. So if B is greater than A, then I want to print out B is greater than A. So since this condition has been evaluated to true, that is 20 is greater than 10, and since this is true, this statement has been executed. So we get B is greater than A. Now let me actually flip it. So I want to check if A is greater than B. And if this evaluates to true, I want to print out A is greater than B. So we don't get any result, and that is because this condition has been evaluated to false. And since this condition has been evaluated to false, this statement has been skipped. So this is where else clause comes in. So let me use else over here. Now I'll type in if A is greater than B, then I'd want to print out A is greater than B. Else I'd want to print out B is greater than A. Right? So here the first condition evaluates to false, and that is why it is kept. And then we're given the else clause, and this condition is printed, B is greater than A. Now let's say if we have multiple conditions. So if we have three numbers and we want to check which is the greatest out of those three numbers. So this is where we would need if, else. So let me actually assign the values again. So I'll assign 10 to A, 20 to B, and I'll also assign 30 to C. So now I'd want to check if A is greater than B and A is greater than C. So I'll type in if A is greater than B and A is greater than C. And if this evaluates to true, I want to print out A is the greatest, and this evaluates to false, then I'll type in elif, which stands for else if. So I'll give in the next set of conditions over here. So I'll type in B is greater than A and B is greater than C. And here I want to print out B is the greatest. So B is the greatest. And again, if this evaluates to false, I'll finally put in else, and I want to print out C is the greatest. So here the final result is C is the greatest. Now let's understand this whole thing properly. So first we come to the if statement, and then we check if A is greater than B and A is greater than C. That is 10 greater than 20 and 10 greater than 30. So both of these are false, and false would evaluate to false, and that is why we'll skip this statement over here. Then we'll come to else if, and we are checking if B is greater than A. So 20 is greater than 10, which is true. Then we'll check is 20 greater than 30, which is actually false. So true and false will evaluate to false, and again this is skipped. And finally we'll come to else, and we'll print out C is the greatest. So this is how we can work with if else. Now let's use the if statement with a tuple. So let me create a tuple over here. So tup1, and let me give some values. A, B, and C. So I have created this tuple. Now after this, I want to check if the element A is present in this tuple. So if A and tup1, then I'd want to print out A is present. Alright, so since this condition is evaluated to true, that is, the element A is actually present in this tuple, and that is why we print this out. Now let me just check if the character S is present in this, and if it is present, I want to print out S is present. So this condition evaluates to false, and nothing is printed out. Now similarly, let me go ahead and work with if and list. So if with list, and then I'll go ahead and create a list. So L1, and then I'll give in a bunch of values inside this. So 10, 20, 30, 40, and 50. Now I want to check if the first element in this list is actually 10. And if the value is equal to 10, then I want to change it to 100. So if L1 of index 0 is actually equal to 10, then I'd want to change this to 100, and then I'll finally print out this list. Right, so initially the first element in this list was 10. With the help of the if statement, I've changed it to 100. Now similarly, let me go ahead and work with if and dictionary. Dictionary with if. I'll create a dictionary, D1, and then I'll give in a bunch of key value pairs over here. So I'll type in the name of the fruit, which is mango, and then I'll assign the value, which is 10. And then the next fruit would be apple. And then the cost would be 20. And then the final fruit would be banana. And then the cost would be 30. Alright. So now I want to check if the value of mango is 10. And if it is equal to 10, then I'd want to add 100 more to this value. So if D1 of mango is actually equal to 10, then I'd want to add 10 more to this. So D1 of mango would be equal to D1 of mango plus 100, and then I'll print out D1 over here. Right, so initially the cost of mango was 10. Then using the if statement, I have incremented the value to 110. Right guys, so this is how we can work with the if statement. Now let's head on to looping statements. So looping statements are basically used to repeat a task multiple times. So let's understand looping statements with this example. So you have a bucket and you'd want to completely fill it up with a mug of water. So the condition is, while the bucket is not full, you will keep on adding a mug of water to it until it is full. So here the repetition task is, you will have a mug of water and you will keep on pouring that into the bucket until it is full. So you're repeating a task until the final condition is met. And this is how the while loop works. So, and in looping statements, you basically have while and for. So we'll start with the while loop. So let's go to Jupyter Notebook again. So let me initialize a variable first. So I'll type in I equals 1 and then I'll use the while loop. So the condition would be while I is less than or equal to 10, I'd have to print out I. Now after this is done, I have to increment the value of I with 1. So let me print this out. So this is the result. Now let's understand this better. So initially I have a variable I and I have initialized it with the value 1. Then I'll start this while loop. So over here, I'll check if I is less than or equal to 10 and initially I's value is equal to 1. So is 1 less than or equal to 10? So it is true. And since this is evaluated to true, I'll come inside the while loop and I'll print out the value of I, which is 1. Then I'll increment the value of I. So 1 plus 1 would become 2. Again, I'll check if 2 is less than or equal to 10. And since 2 is less than or equal to 10, I'll again come inside the while loop and then I'll print out 2. Then again, I is incremented. I's value would become 3. So I'll check if 3 is less than or equal to 10. Again, it evaluates to true. I'll print out 3. And then this loop repeats itself until I's value becomes equal to 10. Right, so the final value would become equal to 10 and then I's value would become 11. So here I'll check if 11 is less than or equal to 10 and that condition would fail. And when the condition finally fails, we will come out of the loop. So this is how the while loop works. So now using the while loop, I want to print the 2 table. That is 2 cross 1 equals 2, 2 cross 2 equals 4 and 2 cross 3 equals 6 and so on. So I'll have the first variable initialized, which is I equals 1, and then I'll type in n equals 2. So I have my variables initialized over here. Now I'll start the while loop and this loop will go on till I's value is less than or equal to 10. Now inside this, I want to print out, so n and then cross I is equal to, I'll just put in n cross I. So let me print this out. So after this, I have to actually give in one more condition, which is I equals I plus 1. So if I don't increment the value of I, then it will go into an infinite loop. So I'll hit run. So we have this 2 table over here. So let me explain this properly. So initially I's value is 1. So I'll check if 1 is less than or equal to 10, which is true. So I'll come inside this and I'll print out 2 cross 1 is equal to 2. And then I'll increment the value of I, which is 2. Then I'll check if 2 is less than or equal to 10, which is again true. Then I'll come inside and then I'll print out 2 cross 2 is equal to 4. Then again, I's value is incremented. It becomes 3. Then I'll check if 3 is less than or equal to 10. And since this is true, I'll again come inside and then I'll print out 3 cross 2 is equal to 6. And this goes on until the i's value is equal to 10, and then I'll print out 2 cross 10 is equal to 20. And when we increment i's value again, it becomes 11. So is 11 less than or equal to 10? Well, it evaluates to false because 11 is greater than 10. Right, so this is where the loop ends, and we have the final value, which is 2 cross 10 equals 20. Now let's use while loop with a list. So I'll basically create a list with a bunch of elements inside it, and with the help of while loop, I want to add 100 more to each of the value inside the list. So let me create the list over here, L1, and I'll add in a bunch of values over here. So 1, 2, 3, 4, and 5. So the list has been created now. Now I'll go ahead and initialize the variable I to be equal to 0. So this is also done, and then I'll start the while loop. So inside the while loop, I will basically check till I is less than. So let me remove these brackets over here. So while I is less than length of L1. So length of L1 would be 1, 2, 3, 4, and 5. So I would go from 0 to 4. And then I basically want to increment each element inside this list. So L1 of I would be equal to L1 of I plus 100, and then I also have to increment the value of I, so I would become I plus 1, and then finally I'll print out the value of L1. Right, so initially the values in the list were 1, 2, 3, 4, and 5, and after running the loop, the values became 101, 102, 103, 104, and 105. So let's understand this loop. So initially value of I was 0, and I'm checking if 0 is less than 5, which is true. So I'll come inside and I'll assign L1 of 0 to be equal to L1 of 0 plus 100. So it'll be 100 plus 1, which is equal to 101, right? So 1 would become 101, and then I's value is incremented by 1. So I's value is 1 now, and then again I'll check if I is less than 5, which is true. So I'll come inside and then I'll assign L1 of 1 is equal to L1 of 1 plus 100. So I'm adding 100 to this element 2. So it becomes 102. And similarly, this will go on till index number 4. And when it becomes 5, so 5 is not less than 5, and that is when we'll come out of this loop. So this is how we can work with the while loop. Now we'll head on to the for loop. So for loop is used to iterate over a sequence. So that sequence could be either tuple, list, dictionary, set, or even a string. And this is the syntax of for loop. So for value in the sequence, and then we'll give out the body. Now this might seem a bit vague or difficult to understand. So let's directly head to Jupyter Notebook and go ahead with the code. So let me start off by creating a list. So I'll type in L1 equals, and then I'll give in a bunch of colors inside this, which would be equal to blue, green, and then I'll just assign red to it. Now, once this is done, let me use the for loop and iterate over this list. So for I in L1, I'll just print out I. Right, so I have printed out each individual element of this list. So for I in L1, right? So when I say I, this value of I initially would be blue. So for I in L1, so L1 has these three elements, blue, green, and red. And initially I's value would be blue. So I'll come inside this list and I'll print out blue. And now it's incremented and I'll go to the next element in the sequence, which is green. So I will have green inside it. I'll come in and I'll print out green. And then I'll go ahead to the final element inside the list, which is red. So again, I'll come inside and I'll print out red. So this is how the for loop works. Now we can actually create nested for loop. So that would mean a for loop inside a for loop. So for this, let me create two lists and two separate for loops. So I'll create, let's say, color, and I'll assign some values. So the values are green, yellow, and pink. And then I'll also add another list, and then I'll name the list to be equal to item. And I'll add a bunch of items to it. So let's say the first item is chair, the second item is book, and the third item is phone. Now I'll start a for loop So for I in color, I'll add another for loop over here. So for j in item, I will print out I comma j. And this is what we have. So let's understand this. So we'll start with the outer for loop, which goes through this list over here, which is color. So for I in color, so initially i's value would be green. Now when the i's value is green, we'll come inside the for loop and we'll start the inner loop for j in item. So initially j's value is chair. So I'll print out green chair. Now again, I'll go back and increment the value of j. So then we have book inside j. So I'll print out green book. Then again, j's value is incremented. It becomes phone. I'll print out green phone, right? So now the inner loop is also done. I'll go back to the outer loop and then I'll increment green to yellow. So now i's value is yellow. So again, I'll come inside the loop and then I'll print out yellow chair, yellow book and yellow phone. Again, I'll go back to the outer loop and then the value of I is pink. Then I'll come inside and then I'll print pink chair, pink book and pink phone. So this is how you can work with nested loops. So now that we're done with the flow control statements, we'll head on to functions. So what exactly is a function? To simplify this, what we are basically doing is we are taking in a bunch of code, putting it in a simple module, and we can invoke it whenever we want to perform a specific task. So let's take this example of an ATM. So over here, depositing money inside the ATM would be one function, withdrawing money would be another function, and checking balance would be another function. Now, let's say if you want to deposit money and you would have to write around 100 lines of code to deposit money. And let's say if you want to deposit money around 100 times, then you'd have to write this 100 lines of code 100 times. Now, instead of this, it would be wonderful if we just had one deposit function and all we did was invoke this deposit function and we could deposit our money happily, right? So this is where functions come in. Similarly, when it comes to the withdraw function, we'll just have to add one function where we'll write in another bunch of code only once. And whenever we want to withdraw money, we'll just invoke this function. Similarly, whenever we want to check the balance, I'll just invoke the balance function and I can happily check the balance. So let's go to Jupyter Notebook and work with functions. So to create a function in Python, we'll be using the def method, and then after the ef, we'll give the name of the function. So I'll just create a very simple function and I'll name that function to be hello. And this needs to be followed with a parenthesis. So after this, I'll give in a colon and then I'll give in the body of this function. So this function just prints out hello world. So hello world, right? Now, if I have to invoke this function, I just have to type in hello with these parentheses. All right. So if I want to print out hello world, all I have to do is copy this, paste it over here. So all I have to do is invoke this function and then I can happily print hello world how many times I want. Now after this, what I'll do is I will create a function where I'm taking an input value and adding 10 more to it. So I'll type def and I'll name the function as add 10. And this basically takes in a parameter value. So if you see this previous example, you see that I did not pass anything inside this parenthesis, but we can actually pass in a value inside the parenthesis. And I'm passing in x, which basically could be any arbitrary value. And I'll put in a colon over here. Now what this does is this returns 10 plus x. So it takes in x, adds in 10 to it, and then returns the final value. This is the function. So let me invoke this. Let me pass in 5 inside this function. So when I pass in 5, it will add 10 to it and it will return the final value, which is 15. Similarly, let's say I'll add an 100 inside this. So it will return a value of 110. So this was another example. Now going ahead, we'll check if a value is even or odd using a function. So I'll type def and then I'll just name this function as odd even. And again, this takes in a value. So I'll use the if condition and I'll check if x and I'll check if x %2 is double equal to 0. So whatever input value is given, I will divide it with 2, and if the input is equal to 0, then I will just print out x is even, else I will print out x is odd. So I have created this function. Now let me invoke it and pass in a value. So I'll pass in 9 and let's see what is the result, right? So this function tells us that 9 is an odd number. Let me again pass in a number inside this. So I'll pass in 4. So this time this function tells us that 4 is even, right? So this is how we can create functions with Python. Now we'll head on to a major part in Python, which is object-oriented programming. Now when you actually look around you, what do you see? You are surrounded with objects, aren't you, right? So you might have a laptop in front of you, you have a phone in front of you, you have a bike, you have a dog. So all of these are real world objects. And if you want to represent these real world objects in programming paradigm, then you would need something known as object-oriented programming, right? So simply put, you have all of these real world objects around you. And if you want to represent all of these real world objects in programming paradigm, that is where you'll go ahead and use object-oriented programming. So now when it comes to object-oriented programming, you basically need to understand two particular concepts, which are basically classes and objects. So as it is stated over here, a class is basically a template or a blueprint for real world entities. Now, what do I mean by it? So when I say template, a template would comprise of two things. One is properties of the object and the next is behavior of the object. So let's take a phone. Now a phone would have certain properties associated with it and it will also have certain behavior associated with it. Now the properties of a phone could be its color, its cost and its battery life. So what is the color of the phone, how much does it cost and how long does the battery last? So these are some properties which are associated with every single phone that everyone has. And then all of the phones have certain behavior common to all of them. So you can make calls with a phone, you can watch videos in a phone, and you can also play games in a phone, right? So these are the properties and behavior associated with a phone. Now a class basically combines these properties and behavior in one single template. So that is a class. Now let's understand what exactly is a object. So objects are basically specific instances of a class. So as I've told you, a class is a general template. And when you want a specific instance of that general template, that is when you have an object. So when I say phone, that phone would be your class. And the objects of that phone would be Apple, Motorola, and Samsung, right? So Apple, Motorola, and Samsung would have the general template of a phone. So they will have the general properties and they will also have the general behavior. So if these objects are of the same phone class, then you will get those same properties, which is basically all of these phones would have color associated with them, cost associated with them, and then you will also have battery life associated with them. And when it comes to behavior, these three phones would have those functionalities common. Right, so in all of these three phones, you can make phone calls, you can play games, and you can also watch videos. So this is what I mean when I say objects are specific instances of a class. All right, so now that we know what exactly is OOPS and what exactly are classes and objects, let's go ahead and perform some object-oriented programming. So let's go ahead and create our first class. And to create a class, we will have to use the class keyword and then we'll give in the name of the class. And by convention, the first letter of the name of the class needs to be capital. So I'll type in capital P and then I'll follow it up with HONE. So it is phone. And then inside this, I will give in the properties and the behavior of the class. So a phone, basically with the help of a phone, you can make phone calls and you can play games. So I'll start off by creating methods. So the first method is to make a phone call. So I will name this method as make call. And then this will have something known as self. So this self basically means that this method belongs to the instance which invokes it. So this might be a bit confusing, but once we actually create an instance of this class, it'll become very clear to you. So we have created this method, and when someone invokes this method, I'll just type in making a phone call. And then I'll give in the second method, which is play game. Again, this will have this self attribute. So again, the self attribute basically stands for whichever instance invokes this method, it belongs to that. All right. So I will print out playing game. All right. So I have created this class, which is basically the general template of a phone. Now I will go ahead and create the object. So to create an object, I will type in P1, which is basically the instance or the object of this class. And I will have to type in the name of the class followed by the parenthesis. And I have successfully created the instance of this phone class. Now, if I have to invoke these methods from this object, so I will type in the name of the instance. I'll use the dot operator, and then I can directly give the name of the method in this class. So if I want to make a phone call, I just have to type in p1.makeCall. So p1 is the name of the instance. After that, I'll give in the dot operator, and then I'll give in the name of the method inside this class, which is makeCall. Right? So now I have successfully invoked this method of this class. So P1 is an instance of this class, and I'm able to access this method with the help of this instance. Similarly, I'll type in P1.playGame. Right. So now I have started playing game. Right. So this is how we can create instances. Now let me actually go ahead and add some parameters to the methods inside this. So again, I'll create a new class. Or basically I'm modifying this class, I'm not creating a new class. So I'll type in class, so this will be phone, and then I'll create a new method, and this will be basically to add the color of the phone. So I'll type in add color. So now every method inside the class needs to have this self attribute, and then after that I'll give in another parameter, which is basically color, and inside this I will set self.color equals color. Now you have to understand that this self.color and this color are actually different. So this color is the value when someone gives while invoking this method, while this self.color is the inbuilt attribute inside this class of that particular instance. So if this seems confusing, let me repeat it again. So this color which you see, it is basically the parameter or the value when someone gives in while invoking this method. And the self.color is the value which is being assigned to the color attribute of the instance which is being invoked. So let me actually go through, and this will become very clear to you, right? So I have created this method, and then similarly, I'll add another method called as add cost. So again, this will have two parameters. First is self, and then next would be cost. And then I'll type in self.cost equals cost. So this is also done. So going ahead, I will create one more method where I'd have to show the color and show the cost. Right. So till now I have only taken the color from the user and taken the cost from the user. Now I also have to print it out. So I'll create a new method called as show color. This would have self, and this would basically return the color. So self dot color, and after this I would have show cost. Again, the parameter would be self, and this would be returning the cost. So that would be self dot cost. All right. And then I'll again create those two basic functions, which are basically making a phone call and playing a game. So definition of make call, this would be self. I am just printing out making a phone call. After this, I'd have to create the final method, which is play game. Again, this will have the self attribute, and then I'll print out playing game. Right, so I have successfully created this class. Now I'll go ahead and create an instance of this class. So I'll type in p2 equals phone. Now let me go ahead and add the color and cost of this phone. So I'll type in p2.color. Now let me go ahead and add the color and cost of this phone. So I'll type in p2.color and now let me go ahead and add the color and cost to this phone. So I'll type in p2.addColor and the color of this phone is, let's say, blue. Now similarly, I also want to add the cost of this phone. So p2.addCost and the cost of this phone is, let's say, $200. Right. Now I have assigned the color and the cost. Now let me show the color and the cost. So I'll type in p2.showColor. So we see that the color of the phone is blue. Now let me also print out the cost. So p2.showCost. So we see that the cost of the phone is 200. All right. So now what you see is this self.cost equals cost or self.color equals color. So this color is basically this value which we are passing in when we are invoking the function, right? So this blue is going over here and this is being assigned to the attribute color of this class phone. So to make it more clear, let me actually create one more instance of this class and let me add the color to that. So p3 equals phone. So I have created this and then I'll type in p3.addColor and the color of this phone would be red. Now let me show this out, p3.showColor. So the color of this instance of the phone p3 is red. Now let me type out p2.showColor, which is blue. All right. So this self, what you see, this basically denotes the instance which is invoking the method, right? So over here, when we invoke the add color with the p2 instance, this self attribute was with respect to the p2 instance. And similarly over here, when we were invoking the add color with respect to the p3 instance, the self attribute was of the p3 instance. This is how we can add parameters to our methods and invoke them through our objects. Now let's head on to an important concept in object-oriented programming, which is inheritance. So what comes to your mind when you hear the word inheritance? So simply put, inheritance basically means that when something acquires the properties of someone else's or something else's, right? So let's say you are inheriting your features from your father, or you are inheriting the land or the property from your ancestors, right? So either it could be materialistic inheritance or it could be the features or the looks from your parents, right? So inheritance is basically acquiring properties from another person or another thing. And when it comes to object-oriented programming, it pretty much means the same thing. So over here, you will have two classes or more than two classes. One class inherits the features or the properties of another class. And that is pretty much the concept of inheritance in object-oriented programming. So let's again head back to Jupyter Notebook and start with inheritance. So to show inheritance over here, I'll just create an extension of the original class. So what I'll do is I will create a new class and I'll name this class as iPhone, and this iPhone will be inheriting from the base class phone which we had created earlier, right? So this is the base class and this new class iPhone would be inheriting from this base class. Now this would have one extra method which is cureCancer. Now as you know, iPhone is very famous and it's famous because it can actually cure cancer. So that is why it costs so much. So that is amazing, isn't it? So cureCancer, I'll give in the self attribute and then I'll just print out I can cure cancer. So I have created this new class. Now let me create an instance of this. So IP1 equals iPhone. So I have created the instance. Now let me go ahead and invoke the methods. Now as you can see, this class or this instance of the class has the methods addColor and addCost. Now, even though I have not explicitly stated these methods inside this class, they are still a part of this class because it is inheriting from the base class, which is Python. And since these two methods are part of the base class, I can automatically invoke these two classes. So let me assign a color to this phone. So the color of iPhone is gray. Now I'll go ahead and also set in cost. So IP1 dot add cost, and the cost of iPhone would be, let's say, $899. And then let me invoke the method which is only there in the iPhone class. So IP1 dot cure cancer. All right, so I can cure cancer, right? So this is how inheritance works in Python. Right, so we're done with object-oriented programming as well. Now we'll go ahead and work with some packages in Python. So we'll start off with the NumPy package. So NumPy basically stands for Numerical Python and is the core library for numeric and scientific computing. So that's too much of information. So simply put, NumPy basically has a multi-dimensional array. Now to process those multi-dimensional arrays, you have certain functions and you have certain operations pre-built in the NumPy package. And that is how you can work with these NumPy multi-dimensional arrays. So you can perform all sorts of numerical and scientific operations on this NumPy array. So let's go to Jupyter Notebook and work with this very famous package called as NumPy. So to start working with the NumPy library, you'd have to first import it. So you'll type in import NumPy as NP. Now this is just an alias so that I can keep invoking this package whenever I need, right? So NP is the alias. Now before you can actually go ahead and work with this library, you'd have to install it. So to install it, since we are working with Anaconda, let me open this up, right? So to install this, you'd have to type in pip install NumPy. Right, but then again, if you're working with Anaconda, NumPy, Pandas, and Matplotlib, all of these come pre-installed in Anaconda. But then again, if you're working with PyCharm or if you're working with any other Python IDE, then you'd have to manually install NumPy. All right, so NumPy is already installed and I have successfully imported NumPy into my system. Now it's time to go ahead and create my first multi-dimensional array. So once you install NumPy and you invoke the library, you have to create a NumPy array. And you can create both a single dimensional array as well as a multi-dimensional array in NumPy. So to create a NumPy array, you just have to type in np.array. So as I've already told you, np is basically the alias for NumPy. So you'll type in np.array, and this basically takes in a list of values or a list of lists. So to create a single dimensional array, what you'll do is you will pass in a list inside this np.array, and this will give you a NumPy array. Similarly, to create a multi-dimensional array, you will pass in a list of lists, right? So this is one list, and inside this you've given two lists, right? So the first list comprises of the elements 10, 20, 30, and 40. And the second list comprises of the elements 40, 30, 20, and 10. So let's go ahead and create our first NumPy arrays. So I'll create a single dimensional NumPy array first. So let me just add in this comment, single dimensional NumPy array. So as I've already told you, to create a NumPy array, we'd have to type in np.array, and inside this I'll give it a list of values. So let's say the list of values are 10, 20, 30, 40, and 50. So I'll type in 40 over here and 50 over here, and I'll store this in a new variable and name that variable as n1. Now let me print out n1 over here. So this is our NumPy array. Now let me also check the type to be sure. So type of n1, and this shows us that this is a NumPy ND array or n dimensional array. Now let's go ahead and create a multi-dimensional array. So I'll type in multi-dimensional. So over here I'll be storing this value in n2. So np.array. Now you have to keep in mind that you pass in a list of lists over here. So I'll create one list, and inside this I'll create the first sub list, and the values would be 10, 20, 30. And then I'll create another sub list. The values I'm giving are 30, 20, and 10. Now let me print out n2. So this is my multi-dimensional array, which comprises of 2 rows and 3 columns. So the first row comprises of 10, 20, and 30, and the second row comprises of 30, 20, and 10. Now again, let me check the type of this. So type of n2. So type of n2 is again NumPy n-dimensional array. And this is how we can create NumPy arrays in Python. So guys, this is just the starting, and you can do a lot of stuff with these NumPy arrays. Right. Now we'll go ahead and see how can we initialize a NumPy array with all zeros. So let's say if we want to create a simple row array which comprises of 2 zeros, then we have this zeros method. So np.zeros, you are invoking this zeros method from the NumPy package. So when you type in np.zeros, and then you have to give in the dimensions of it. So the dimensions of the NumPy array are 1 cross 2, and then you'll get this. Similarly, if you want to create a 5 cross 5 NumPy array which comprises of only zeros, then you just type in np.zeros, and inside that you will give in the values. So let's initialize our NumPy array with zeros over here. I'll type in n1 and then np.zeros. So I want the size of the NumPy array to be 1 cross 2, and then I'll print this out. Right, so I have successfully created my NumPy array of dimensions 1 cross 2, which means 1 row, 2 columns, and the values are just zeros. Now similarly, I'll create another NumPy array. So n1 equals np.zeros, and I want this to be a, let's say, 6 cross 6 NumPy array which comprises of only zeros. Again, let me print in the value of n1. Right, so I have created this NumPy array which is of dimension 6 cross 6, and it comprises of only zeros. Now similarly, let's say if you want to initialize a NumPy array with the same number. So this is where we have the full method from NumPy. So we have to type in np.full, and this takes in 2 parameters. So the first parameter is the dimension of the NumPy array, and the second parameter is the value with which you'd want to fill up your NumPy array. So over here, I am creating a NumPy array of dimension 2 cross 2, and the value which I'm filling it up with is number 10. So let's create this. So I'll name this as n1 again, and I'll type in np.full. I'll give in the dimension. I want to create a 3 cross 3 NumPy array, and I want to fill it up with the number 7. And then let me print out n1 over here. So we have created this 3 cross 3 NumPy array where all of the elements are just 7. Again, we can initialize our NumPy array in a different way. So if you want to initialize our NumPy array with a particular range in mind. So let's say I want my NumPy array to be filled with all of the values from 10 to 20. So basically the interval is 1, or the skip value is 1. So I'll have 10, 11, 12, 13, 14, 15 going on till 19, right? So I want to fill up my NumPy array with a particular range. So this is how I can do it. Now, another form is I basically give a skip value. So when we don't give the third parameter, arange automatically takes the skip parameter as 1. So when we look at the second example over here, the range is basically from 10 to 50, but the skip value is 5. So your first number would become 10, second number is 15, 20, and then this goes on till 45. So you have to keep in mind that this last number which you see, this is exclusive. It is not inclusive. So when you add 5 more to 45, if it is less than 50, only then you'll get the last value. If it is equal to or greater than 50, then you will not get that value. Right. So let's go ahead and initialize our NumPy array with a particular range. So again, I'll type in n1. So this would be np.arange, and inside this, I will basically give in the range with which I want this NumPy array to be filled with. So I want this to be filled starting from 1 going on till 11. And then let me print this out. Right, so this NumPy array, the values start at 1 and go on till 10. Now similarly, let me create another NumPy array with a specific skip value. So n1 equals np.arange, and let's say I want the range to be from 100 and going on till 300, and I want the skip value to be equal to 50. So let me just print out n1 now. Right, so this is my NumPy array. So 100 is the starting value, 250 is the last value, skip value is 50. So that is why I get 100, 150, 200 and 250. And when you add 50 more to 250, it becomes 300. And since 300 is not inclusive, that is why you will not have that number over there. Now let's see how can we initialize our NumPy array with random numbers. So if you want to initialize our NumPy array with random integers, then we've got this randint sub method from the random method. So again, you will set the range of the numbers from which you want the random numbers over here, right? So the range of the numbers is 1 and 100. So starting from 1, going on till 100, you will choose 5 random numbers. So let's go to Jupyter Notebook and work with this. So n1 equals np.random.randint, and then inside this, let's say I want 10 random values, and the values would be coming in the range between 100 and 200. So I want 10 random values. Let me print out n1. Right, so these are the 10 random values between 100 and 200. So that was how we could initialize our NumPy array in a lot of different ways. Now let's see how can we check the shape of our NumPy array. So checking the shape of our NumPy array would basically give the number of rows and number of columns present in the NumPy array. So all you have to do is create a NumPy array first and then use this shape method. So when you use the shape method, this will tell you the number of rows and number of columns present in this NumPy array. Now, with the help of this shape method, you can actually change the shape of your NumPy array. So initially, when you are initializing it, this NumPy array had 2 rows and 3 columns. But with the help of this shape method, you can change it to 3 rows and 2 columns. So let's go to Jupyter Notebook and let's see this visually. So again, n1, and let me create a NumPy array over here. np.array. Let me give in some values. So let's see 1, 2, 3, and 4. And I actually have to give in a list of lists. So let me cut this and paste inside this. And then my second sub list would be 5, 6, 7, and 8. So I have created n1 over here. Let me check the shape. n1.shape. So the shape of this NumPy array is 2 cross 4. This would mean we have 2 rows and 4 columns in this NumPy array. So that would basically amount to 8. Now, instead of 2 cross 4, I want this NumPy array to be of the shape 4 cross 2. Or in other words, I'd want to have 4 rows and 2 columns. So all I have to do is type in np.shape equals 4 cross 2. So this is done. Now let me print out n1. Right, so initially this was our n1 array, which was of the shape 2 cross 4, and then we reshaped it. Now this is how it looks like. Now once we know how to initialize our NumPy arrays and how to check the shape of our NumPy arrays, let's go ahead and perform some simple mathematics on top of these NumPy arrays. So we'll look at some basic addition operations. So to add two NumPy arrays, we will just use the sum function from the NumPy package. So over here, I am creating two NumPy arrays, n1 and n2. And when I use the sum method over here, I'll pass in n1 and n2 as a list, right? So this will add all of these individual elements from both of these NumPy arrays. So when you add 40, 30, 20, and 10, it will give you a complete value of 100. Now, you can also set the axis. So if you don't set the axis, then it will add all of the individual elements which are present. So when you set axis to be equal to 0, then it actually does vertical addition, right? So what I mean by vertical addition is it would add the individual elements of each index of this array. So index is 0 over here for n1 and n2. When you add 10 plus 30, it would become 40, and that is what you have. Similarly, when you come to index number 1 and you add 40 plus 20, you get 60, and that is what you have. Now, instead of axis to be equal to 0, when you set the axis to be equal to 1, you basically are doing horizontal addition. That is, you are summing up the values which are present in one individual NumPy array. So here 10 plus 20 becomes 30, and that is what you have. And over here, when you add 30 plus 40, it becomes 70, and that is what we have over here. All right. So let's go to Jupyter Notebook and perform these methods. So again, let me create a new NumPy array. I'll call it A over here. So it will be np.array, and I'll pass in a list of values over here. That would be 10 and 20. And then I'll create another NumPy array. So I'll type in np.array again, and the values inside this would be 30 and 40. So I have successfully created my two NumPy arrays. Now going ahead, let me use the sum method. So it would be np.sum, and inside this I'll just pass in a comma b, which are basically the NumPy arrays which I've created, and I get a complete value of 100. Now let me go ahead and set the access. So np.sum, I'll type in a comma b, and then let me set the access. So I am setting the access to be equal to 0. And when I set the access to be equal to 0, as we have already seen, we have vertical addition over here. So 30 plus 10 gives you 40, and 40 plus 20 gives you 60. All right. Now let me go ahead and set the access to be equal to 1. So I'll pass in a comma b, and I'll set the access to be equal to 1. Right, so 10 plus 20 becomes 30, and 30 plus 40 becomes 70. So those were some basic addition operations on top of the NumPy arrays. Now let's see how can we join different NumPy arrays. So we've basically got these different methods. We've got vstack, which stands for vertical stack. Then we've got headstack, which stands for horizontal stack. And then we've got column stack. So when it comes to vstack, what we do is we join these NumPy arrays row-wise. So over here we have two NumPy arrays, n1 and n2. And when we use vstack method upon these two NumPy arrays, we are basically joining these two NumPy arrays row-wise. Then we have the headstack function. So when it comes to headstack function, we are combining these two NumPy arrays column-wise. So when I say column-wise, we will take in this first NumPy array, and then we'll attach the second NumPy array to the back end of this. And then we have column stack, where we basically take in two single dimensional NumPy arrays, and then we stack them column wise to create a two-dimensional array. So as we see over here, we've got two one-dimensional arrays, right? So n1 and n2, and when I use column stack on top of this, I get a two-dimensional array. So over here, these two are stacked column wise. All right, so let me go ahead and use these three functions. So let me create n1 over here. So n1 is equal to np.array, and let me give in the values 10, 20 and 30. Then n2 would be equal to np.array, and the values inside this would be, let's say, 30, 40 and 50. So I have created n1 and n2. Now it's time to use vstack on top of them. So I'll type in np.vstack, and inside this I'll pass in n1 and n2. So let me get the result, right? So I have horizontally, so I have stacked these two columns row wise. Now similarly, instead of vstack, let me use horizontal stack. So I'll type in headstack over here. Right, so when I use headstack, I get this. So I'm horizontally stacking these two NumPy arrays. And then finally, let me use np.columnStack, and I'll pass in n1 and n2. And I have taken these two individual single dimensional arrays. So 10, 20, 30, 30, 40, 50, and I have stacked them column wise to create a two-dimensional NumPy array. Right, so this brings us to the end of this NumPy module. Now let's go ahead and work with another interesting package in Python, which is pandas. So pandas stands for panel data, and it is the core library for data manipulation and data analysis. So as NumPy provides us a multi-dimensional array, similarly, pandas provides us a multi-dimensional data structure for performing various data manipulation operations. So it provides us both a single dimensional data structure and a multi-dimensional data structure. So as we see over here, the single dimensional data structure is called as the series object, and the multi-dimensional data structure is called as the data frame. And we're mostly working with the data frames in Python. So data frames become extremely important when it comes to data science operations. So all of the machine learning algorithms which you apply, linear regression, logistic regression, decision tree, and so on. So all of these are applied on data frames. And this is because all of the data sets which you have, all of the CSV files which you have, text files which you have, they can be converted to a data frame in Python, and all of the manipulations can be done on this data frame. All right, so let's start off with the Pandas series object. So as you see over here, a series object is basically a one-dimensional labeled array. So the difference between this and a NumPy array is, when it came to the NumPy array, it was not labeled, but the series object is a one-dimensional labeled array. And this is how you can create a series object. So before we go ahead and create a series object, first we'd have to invoke the pandas library. So we'll type in import pandas as PD. And PD again over here is just an alias for pandas. So after we invoke pandas, we'll type in pd.series. So over here, you'd have to keep in mind that S is capital. And inside this, we'll pass in a list 1, 2, 3, 4, and 5. And we have created this series object. So let me start off by importing pandas. So I'll type in import pandas as PD. So let me just wait till this package is loaded. So that is done. Now again, since I'm using Anaconda, pandas comes pre-installed in it. So if you have to manually install pandas, this is what you have to do. Open up Anaconda prompt, and then you'd have to type in pip install pandas. So once you do that, pandas will be installed. All right, so I have imported the pandas library. Now let me go ahead and create my first series object. So I'll name this object as S1, and I'll type in pd.series. And inside this, I'll basically pass in a list. So the list would comprise of the values 10, 20, 30, 40, and 50. So let me print in S1 over here. So this is my series object. So as you see over here, these are the values, and these values are of type integer 64. So integer 64-bit. And these are the labels associated with each of these values. So 0 is the label associated with 10, 1 is the label associated with 20, 2 is the label associated with 30. So you can either call these index values or the labels associated with these numbers. So now you must be thinking that, is there a way that we can actually change the index of a pandas series? Well, you can. So all you have to do is include this index attribute and then give the labels which you want for these. So as you see over here, initially the labels were 0, 1, 2, 3, and 4. Now after that, you just use this index attribute and then change these values to A, B, C, D, and E. Right, so let's perform this. So let me go ahead and add the index to this. So as you see over here, initially the labels were 0, 1, 2, 3, and 4. Now let me go ahead and change the index. So this time I'll set the index to be A, B, C, D, and E. Now let me print out S1. So as you see over here, these were the initial index values, and I have changed them to these over here. So we saw how to create a series object from a list. Now let's see how can we create a series object from a dictionary. So as you see over here, we'll just pass in this dictionary inside this series object. And one thing to note over here is, if you don't specifically set the index values, the key automatically becomes the index and the values would automatically become the actual values inside the series object. So I'll reiterate it. The keys would become the index values and the values would become the actual values of the series object. So let me create a dictionary over here. So D1, and I'll set the key to be equal to K1 and the value to be 10. Then I'll set the key to be K2 and the value is 20. Then the key is K3 and it is 30. I have created this dictionary. Now again, let me go ahead and create a series out of this. So pd.series, and I'll pass in the dictionary inside this, and I'll store this in S1. So let me print out S1 again. Right, so this is my series object which has been created from this dictionary. So as we see over here, the keys have become the index values. So K1, K2, K3 are the index values, and 10, 20, and 30 are the actual values of the series object. Right, so that was all about the single dimensional data structure series. Now we'll head on to the most important data structure in Python, which is a data frame. So as it is stated over here, a data frame is basically a two-dimensional labeled data structure, and it comprises of rows and columns. So this, what you see, so you've got 3 rows over here and 2 columns over here. And normally when it comes to a data frame, all of the elements inside one column would have the same type. So as you see, this is the name, and the names are normally strings. So Bob is a string, Sam is a string, and Anne is a string, right? And then we've got marks. So marks is another individual column. And when you look at the values inside this marks column, you see that 76, 25, and 92, all of these are integer values, right? So this is how a data frame looks like. And to create a data frame, this is how you can do it. So all you have to do is use the pd.dataframe method, and then you can create it from a dictionary over here, right? So the key becomes the column name over here, and these values become the row values over here. So let me create a data frame. So I'll name this data frame as student, and the first column would actually be the name of the student. So I'll type in student name. So this is actually the key, and then I'll give in the list of values. So the list of values would be Bob, and then we've got Sam. After that, we've got Julia, and then we've got Charles. So these are the student names, and then let's go ahead and give in some marks to these students. So I will create the next key, which would be student marks. So I'll type in student marks over here, and then I'll give in a list of values. So let's say Bob has scored 87 and Sam has scored only 13 marks. Then we've got Julia, who has scored an impressive 99. And then we've got Charles, who has scored an average 67. So I have successfully created this dictionary. Now it's time to create a data frame out of this dictionary. So I'll type in pd.dataframe, and inside this, I just have to pass in this dictionary. I'll click on run, and I have successfully created this data frame where the key over here becomes the column name, and these list of values for a particular key become the row values for that column. So Bob, Sam, Julia, and Charles are the list of values or the row values for this key student name, which is the column name. Similarly, 87, 13, 99, and 67 are the row values for this key student marks. So now that we know how to create a data frame, let's go ahead and perform some inbuilt functions on top of this data frame. So we'll be working with these basic functions such as tail, head, shape, and describe. So to work with all of those inbuilt functions, we'll start by reading a CSV file as a data frame first. So again, let me perform the basic steps. So I'll type in import pandas as pd. Now to load a CSV file, I'd have to type in pd.read_csv, and inside this I'd have to give in the name of the file. So we'll be working with this iris.csv file, and I'll be storing this in a new object, and I'll call that object as iris. So now I want to have a glance at the first 5 records of this iris data frame. So to have a glance at the first 5 records, I'll just type in iris.head. Right, so I've got this first 5 records of the data frame. Now let's understand this data frame properly. So this has got 5 columns, which are basically sepal length, sepal width, petal length, petal width, and species. So these are basically the different features of the species of the iris flower. So you've got 3 different species: Setosa, versicolor, and virginica. And for all of these 3 different species, we've got the sepal length, sepal width, petal length, and petal width. So as we already saw over here, the head function helps us to have a glance at the first 5 records of this data frame. Now if I want to have a glance at the first 10 records, then all I have to do is type in 10 inside this head function. Then we'll have a glance at the first 10 records of this data frame, right? And if I want to have a glance at, let's say, the first 100 records, then I'll just type in iris.head 100. Right, so these are the first 100 records where the index value starts at 0 and it goes on till 99. Now, analogous to the head function, we also have the tail function. So I'll type in iris dot tail. Now this tail function would give me the last 5 records of this data frame. So this starts at index number 145 and goes on till index number 149. Similarly, if I want to have a glance at the last 10 records, then I'll just pass in 10 over here. Right, so these are the last 10 records of this iris data frame. Now, these are the head and tail functions. So there is also this describe function. So I'll just type in describe over here and let's just see what it does over here. So this would basically describe this entire data frame in terms of all of these different measures. So we've got count. So this count is basically the number of records present for each of these different columns. So there are 150 records for sepal length, similarly 150 for sepal width, petal length and petal width, right? So these are basically the different count values of all of these columns. And then we've got the mean value. So this is the mean value of sepal length, sepal width, petal length and petal width. And similarly, we've got the minimum value, standard value, 25 percentile, maximum value, and so on. So these are some basic functions which can be implemented on top of any data frame. So now going ahead, we'll see how to access individual rows and columns from our data frame. So to do that, we've got the iloc and the LOC methods. So let's start with the iloc method. So first we'll give in the name of the data frame and then we'll just type in .iloc. So this .iloc basically stands for index location, and this is how we can extract some specific rows and columns from this entire data frame. So over here, what we are doing is we are extracting the first 3 records from this data frame and the first 2 columns, right? So the index values go from 0 to 3. So 0, 1, 2, and then the column values are 0 to 2, right? So 0 and 1, sepal length and sepal width. So this is how we can extract a subset of the data frame from this entire data frame. So now let me again print out the head of this. So iris.head. This is my data frame over here. Now let's say I want a subsection which comprises of the row numbers starting from, let's say, 99 and going on till 126. And I want only the petal length and the petal width column. So to do that, I'd have to type in iris and then I'll type in LOC. I'll give in this square braces over here. I'll put in a comma. Now, whatever you given on the left side of the comma, that would denote all of the rows which you would want to extract. And whatever you put in on the right side of the comma, that would denote all of the columns which you'd want to extract. So as I've said, the row numbers which I want to extract are from 99 to 126. So indexing will start from 99 and go till 127. And then the column values should be 0, 1, 2, and 3. So this will go from 2 to 4. So I'll just put in 2 to 4 over here and I'll store this in a new data frame and I'll name that to be iris1. So let me print out iris1 over here. Right, so this is our data frame iris1, which comprises of only the columns petal length and petal width, right? And the row numbers start from 99 and go on till 126. Now, similarly, let's say if I want to extract all of the records starting from row number 10 and going on till row number 20, and I want only these 2 columns, the sepal length column and the species column. So let me show you guys how it's done. So this time I'll name the data frame as iris2 and I'll type in iris dot, I will type in iloc over here, and this would go from 10 to 21. And after this, I will just give in the column values. So again, I will take in a list over here, and inside this, I will give in the index of the first column, which is basically 0. And then I'll give in the index of the final column, which is 4 over here. I'll click on run and let me print out iris2 over here. Right, so this is my subsection of the entire data frame where I have row numbers starting from index number 10 going on till index number 20, and these are the 2 columns which I've extracted. So sepal length and species. So this is how I can work with the iloc method. Then analogous to the iloc method, we also have the loc method to extract individual rows and columns. So the only difference is, instead of giving the index values over here, we given the labels of the columns over here, right? So over here, when it comes to rows, we'll similarly given the index values of the rows, and over here, when it comes to columns, I will given the names of the columns. So let's work with ilog. Now let me print out the head again, iris.head. Right, so this is my data frame over here, and this time I want all of the records starting from row number 33 and going on till, let's say, 44. And I'll store this in iris3, so this will be iris.loc, and inside this has to go from 33 to 44. And then the names of the columns which I want to extract would be sepal width and petal width. Now you have to keep in mind that you given the column names properly, right? So if you make a spelling mistake, then there would be an error over here. So I'll type in sepal width, and then I'll give in the name of the next column, which is basically petal width. Now let me print out the subsection. So I'll just print in iris3. Right, so these are all of the records starting from row number 33 going on till row number 44, and these are the two columns which I've extracted, sepal width and petal width. Right, so till now what we did is we extracted some individual rows and columns with the help of .loc and .iloc. But now we'll actually perform data manipulation operations where we'll be extracting records on the basis of a condition. So let's go ahead and do that. Now the condition which I want to specify is I want only those records from this data set where the sepal length is greater than 5. So let's see how can we do that. So first I'll give in the name of the data frame, which is iris, and I'll put in quotes over here, and then I'll give in the name of the column, which is basically sepal length. So I want to extract only those records where the sepal length is greater than 5. So I will basically give a condition that this sepal length has to be greater than 5. Now let me click on run and let's see what do we get. So we basically get a bunch of true and false values. Now what does this mean? So this means that wherever you have the true label, this condition has been satisfied, and wherever you have the false label, this condition has not been satisfied. So we have the true label for the 0th record over here, and that is because the sepal length is greater than 5. Similarly, we have a true value over here, and that is because the sepal length is greater than 5. Right? So wherever you have the true value, that is where you have the sepal length to be greater than 5. Now we've done this. Let's go ahead to the next part where we actually have to extract those records. Now we just have a bunch of true and false values. So to extract the records, again I'll type in iris, I will give in braces, I will cut this and I will paste this inside this iris data frame. So what I'm doing is I will be extracting only those records where this condition evaluates to true. I'll click on run, right? And this is what we have. Now, if you look at the sepal length column, then you'll see that all of these values are greater than 5. So what we basically did is first we started off by giving the condition, and then we put in this condition again inside this iris data frame. So this gave us only those records where this condition was satisfied. Right, now let's go ahead and perform similar operations. So this time I want only those records where petal length is greater than 2 and the species is equal to Virginica. So let's check that out. So let me cut this first. And given the condition, so the first condition would be iris, and then we want the petal length to be greater than 2. So I'll type in petal underscore length, and this has to be greater than 2. Now I will enclose this within round brackets. After that, I will give in the AND operator because I want both of these conditions to be satisfied. So I'll go ahead and give in the second condition. So the second condition is iris, and this time the name of the column is species. So this has to be equal to Virginica. So I'll just set Virginica over here. Right, so these are the two conditions. Now I will cut this out, and again I'll type in iris and paste it inside this. And I will store this in a new data frame and name that to be iris final. Now let me check the head of this. So iris final dot head. Right. So we see that we have extracted only those records where the petal length is greater than 2, right? So here you see petal length is greater than 2 and the species is equal to Virginica. So we have given multiple conditions to extract these records. Now similarly, we can give as many conditions as possible. You can give 2, 3, 4 or 5, as many conditions as you want. So let's complicate this a bit and we'll give in 3 conditions over here. So this time I want the sepal length to be greater than 6, sepal width to be greater than 3 and petal length to be also greater than 3. So let's give in all of those 3 conditions and let's see what do we get. So I will type in iris and my first condition would be sepal length has to be greater than 6. I'll put in braces and this is my first condition. After that I'll give in the AND operator and then given the second condition I'll type in iris and the sepal width has to be greater than 3. So I'll type in sepal width. This has to be greater than 3 and then I'll give in the final condition which is basically the petal length has to be greater than 6. So iris and then I'll give in petal length over here. This has to be greater than 6. Let me cut all of this. Let me paste it inside this. Alright, so I have given my 3 conditions over here. Let me cut this entire thing out. Let me type in iris over here and I'll paste it over here. Alright, I will store this in. Let's say iris random. So this would become iris random dot head. Right, so we have these records where the sepal length is greater than 6. The sepal width is greater than 3, the petal length is greater than 3, and the petal length is greater than 6, right? Now let me actually remove this head and let's see how many actual records satisfy this. So see that there are only 3 records out of these 150 records where these 3 conditions are satisfied. That is, the sepal length is greater than 6, the petal width is greater than 3, and the petal length is greater than 6. Right, so these were some different data manipulation operations which we could perform on the iris dataset. So that was data manipulation. Now we'll head on to data visualization. And to perform data visualization, Python provides us a package called as matplotlib. And with the help of matplotlib, you can create beautiful graphs such as bar plots, scatter plots, histograms, and a lot more. So let's go to Jupyter Notebook and work with these graphs. So we'll start off by importing the pyplot submodule from the matplotlib library. So I'll type in from matplotlib import pyplot as plt. So I have imported this and we also have to create some numpy arrays. So for that purpose, I would also have to import numpy. So I'll type in import numpy as np. So we have imported the required modules. So now that we have the required packages, our first plot which we'll be making is a line plot. So to create this line plot, we would require x and y values. So let me start off by creating the x values. So x would be equal to np.arange and I want the value starting from 1 and going on till 10. Right, so let me just print this out first. So I've got my x values ready. Now let me also create my y values. So y would be equal to 2 times of x. So let me also print out y. So I also have my y values ready. Now it's time to finally make the line plot. So to make a line plot, all we have to do is type in plt.plot. So this plt is basically the alias for this pyplot submodule. Now, whatever plots you're making, that all of them you'll be making with this pyplot submodule. And to make a line plot, you will be using this plot method from the plt submodule. So you'll just put in this round braces over here and then you'll pass in the x and y values as the initial parameters. So you'll type in x, comma, y over here. After that, just type in plt.show, click on run, and then you successfully have created your first visualization. Now, isn't this a beautiful line plot? So over here, what we basically have is the x-axis. This is the y-axis, right? So when you have the x value to be equal to 2, the y value is 4. When you have the x value to be equal to 4, the y value is 8. And that is what this line plot is telling you. Now, wouldn't this be even better if we add title, x label and y label to this? So let's go ahead and do that. So let me add the title. So to add the title, you have to type in plt.title. And let's say the title which I'll be giving this is line plot. Now let me give it the x-axis label. So this would be plt.xlabel, and I'll just simply put in x-axis over here. Now let me also put in the y label. So I'll type in plt.ylabel, and inside this I'll type in y-axis. Right, so we have added the title, we have added the x-axis, and we have also added the y-axis. Now let's say I want to change the color of this line. So I don't really like blue, maybe I want green color or red color. So how do I do it? So over here, so I would have to go inside this main function, which is plt.plot, and I will use the color attribute and I will set the color. So I want this to be green, so I'll just type in green over here. Right, so now I have changed this color to green. Similarly, if I want this to be orange, I can just type in orange over here and the color becomes orange. Now I can also play with the line width and the line style of it. So I'll just type in line width over here and let me set it to be equal to, let's say, 2. Let me click on run. So let me remove this underscore over here. Right, so I have increased the line width. So to make it more obvious, let me make it 5 over here. Right, so this has become thicker. So you can give it whatever value you desire. I'll give in 50. Right now this has become quite thick over here. So let me change it back to 2. 2 seems quite good for this. Now I can also change the line style of this. So I'll type in line style and I'll set the line style to be equal to colon. So when you put in colon, this is what you get, right? So you have a dashed line over here. So this is how you can basically create a line plot, right? So first you will type in plt.plot and then you will give in the x values and the y values. Now after that, if you want to describe the plot more, you can add the title, you can add the x label and also the y label. So let's say if you also want to add a grid to this, so all you have to do is set in plt.grid. So this has to be small g over here and you will just type in true inside this, right? So you have also added a grid to this. So this is how you can add a line plot. Now let's say I want to add 2 lines inside this one single plot. So what I'll do is I will actually add one more y value. So my y1 is 2x over here. Similarly, I'll also create y2. So I'll set y2 to be equal to 3x. So let me print out y1 as well as y2. Right, so this is y1 and y2. So I will be making 2 plots over here. So first is with respect to y1 and x. Next would be with respect to y2 and x. Right, so now we have 2 lines over here to distinguish them. Let me give it a different color over here. Let me change this to, let's say, back to blue again. Right, so this is the line which denotes y is equal to 3x and this is the line which denotes y is equal to 2x. So this was a line plot. Now let's go ahead and create a bar plot. So I'll type in, I'll just give in a comment over here, bar plot. Now to create this bar plot, I would need a dictionary first. So let me again name this dictionary to be student over here. And I'll have some names of students and the marks of those students. So let's say the first student is Sam again, and he has scored 30. Then we've got Bob, who has scored 50. And finally, we've got Julia, who has scored 70. So we have created this dictionary over here. Once this dictionary is done, I'd have to extract the keys and store it into a separate variable, and extract the values and store it into a separate variable. So I'll take this new variable called as names, and I will extract only the keys of it. Now, once I do this, I would need the list of the keys, because the plt.bar function only takes a list of values. I'll cut this and I'm pasting this inside this. Similarly, also extract the values. So I'll be storing that in the marks object. Again, let me do the same thing. So this will be student.values. So let me print out names and marks over here first. Names, and then I've got marks. So I have extracted the names, and then I've also extracted the marks. Now to make a bar plot, I just have to type in plt.bar. So first I would have to give in the categorical values which are stored in names, and then I'd have to give in the corresponding numerical values with respect to those categorical values which are stored in marks. Let me also put in plt.show over here. Right, so this is my bar plot. So this graph basically tells me that there are 3 students. First is Sam, who has scored 30 marks. Then there is Bob, who has scored 70 marks. And then there's Julia, who has scored 70 marks. Now, again, if I want to change the color of this bar, all I have to do is use this color attribute and give it a different color. So let's say I want to give it yellow color. So I'll set yellow over here. Right, so I have changed the color. Now again, if I want to give the x-axis label, y-axis label, and the title, it does the same process again. So I'll type in plt.title over here, and I give the title as marks of students. After that, I'll set in the x-axis label, so plt.x label, and that would be equal to names of students, and then plt dot y label, which would be equal to just marks. Right, so marks of students is the title, marks is the y-axis label, and names of students is the x-axis label. Again, if I want to add a grid, it will be plt dot grid, and I'd have to just set in true over here. Right, so this is my bar plot. There is also something known as a horizontal bar plot. So over here we have these bars stacked vertically, but instead, if you want to see these bars horizontally, then we have this bar h function from the pyplot module. So the only difference which we'd have to do is, instead of plt.bar, we just have to put in plt.bar h. And when you do this, this is what you get. So initially these bars were stacked vertically. Now when you use bar h, these bars are stacked horizontally. Now let's go ahead and create a scatter plot. Let me add the comment over here. All right. So first I'll go ahead and create 2 lists over here. So I'll name the first list as X again, and I'll give in a bunch of random values over here. So I'll take in, let's say, 6 random values. So 1, 2, 3, 4, 5, and 6. Now similarly, I'll take another list. I'll name it to be Y1. Now you have to keep in mind that you take the same number of values in X and Y, because a scatter plot, it basically gives you a point for a specific position of X and Y coordinates. All right. So again, I'll give in some random 6 values. So 9, 1, 2, 6, and 4, and 9 again. So we've got the X and Y values ready. Now to make a scatter plot, all you have to do is just type in plt.scatter and then pass in the X and the Y values. And this is what you have. Let me also add the grid. So plt.grid, I'll make it to be true. Right, so this is what you have. So this is the first point where the X coordinate is 1 and the Y coordinate is 4. Right, so this is the point which it is denoting. And then we've got 3, 2. So 3, 2 would be this point. Then we've got 4, 9. So 4, 9 would be this point, right? So this is how a scatter plot looks like. Now let's say if you want to depict two different point themes on the same scatter plot, then all you have to do is create a new list. So I'll name this to be y1. I'll set it to be y1 over here. Let me again create a new list, which is y2. Let me give in a bunch of random values again. So 4, 7, 8, 1, 2, 6, right? So I've got my bunch of 6 values over here. Let me create another scatter plot over here. So this time it'll be with respect to x and y2, and I will give it a different color. So the color would be red. Right, so I have added two different theme points on the same graph over here. Now let's head on to the next plotting, which is a histogram. So histogram basically helps us to understand the distribution of a continuous column. So for this, we'll be actually loading the iris dataset again and understanding the distribution of some of the continuous columns of that dataset. So again, I'll load up the dataset. So I will type in pd.readcsv, and now I'll give in the name of the file, which is iris.csv, and I'll store this in iris again. All right, so let me have a glance at the head of this again. So iris.head. Right, so this is our data set. Now I want to understand the distribution of this sepal length column. So for that, what I'll do is plt dot, to make a histogram, we've got this hist function, and inside this I'll just give in the name of the column. So iris, and I'll give in the name of the column, which is sepal length, and then I'll just put in plt dot show. So this is the histogram, and this shows us the distribution of this sepal length column. Now to increase the distribution of these bins over here, we've got the bins attribute. So I'll just type in bins. So let's say I want 20 bins. So I'll just type in bins. So I'll just set the bins value to be equal to 20. So the inference which we can draw from this plot is, so let's say if we take this particular bin over here, then this tells us that there are around 16 records where the sepal length of the flower is exactly around 5. Then we've got this over here. So this bin tells us that there are again around 16 records where the sepal length is 6.5. And if we take this bin over here, so there are very few records. So this would be, let's say there's just one record where the sepal length is somewhere between 7.5 and 8. So again, if we take this bin, so there would be around 4 records, or there are just 4 flowers whose sepal length is 4.5. So this is the sort of inference which we can draw from a histogram. And the basic difference between a histogram and a bar plot is, so a bar plot is used to understand the distribution of a categorical variable, while a histogram is used to understand the distribution of a continuous variable. Now similarly, if I want to understand the distribution of, let's say, petal width, so I'll change this over here. And I'll just put in petal width. Right, so this is the distribution of petal width. So there are around 34 records whose petal width would be somewhere around 0.2 or 0.3. So those constitute a lot of flowers, right? And if we take this bin over here, so there would be just one record, or there's just one flower where the petal width is 0.5. And this seems to be the maximum petal width, which is around 2.5. So the maximum petal width of 2.5, there are around 5 records. All right, now let's again understand the distribution of sepal width. So I'll change this and I'll just put in sepal over here. Right, so we have a big peak over here. So there are 25 records where the sepal width is 3. And there is just one record whose sepal width would be around 4.3 or 4.4, right? So this is histogram. So now we'll go ahead and make some box plots. So box plots are used to understand the distribution of how does one continuous variable change with respect to a categorical value. And again, we'll be building box plots on this iris dataset. So I'll type in iris.boxplot. And this basically has two parameters. So the first parameter is the column where we'll assign the y values or the continuous value. And the continuous value which I'd want to give in is sepal length over here. So I'll type in sepal length. and then I'll map the categorical value onto the x-axis. So for this, I've got the by attribute, and we've only got one categorical variable over here, right? So the species column is the only categorical variable which you've got. So I'll type in species over here. I'll hit on run, and this is the box plot which you get. So what you see over here, so this line which you see in the middle of this box, this is known as the median line. This is the 25 percentile line, and this is the 75 percentile line. Let's just focus on this median line over here. So this tells us that if the species of the flower is setosa, then the median sepal length of the flower would be around 5. And again, let's take this box over here. So if the species of the flower is versicolor, then the median sepal length would be around 5.9. And let's take this. So if the species of the flower is virginica, then the median sepal length over here would be 6.5. So this is the inference which you can draw from a box plot. Now, similarly, if I want to understand how does petal width vary with species, let me just put in petal width over here. Right, so again, we have 3 boxes over here, 1 box each for the different species of the iris flower. So over here, it seems that the median line would be somewhere over here. So if the species of the flower is setosa, then the median petal width would be around 0.3 or 0.4. Then we've got versicolor over here. So if the species of the flower is versicolor, then the median petal width would be 1.2. So the basic inference is virginica over here would have the maximum petal width, and setosa would have the minimum petal width. So that was the same case which we saw with sepal length as well. So virginica had the maximum sepal length and setosa had the minimum sepal length. If we want to make this plot even more beautiful, we can use the Seaborn library. So let me just import the Seaborn library. I'll type in import Seaborn as SNS. Then we've got the box plot method from this. So sns.boxplot. Now what I'll do is I have already loaded this iris dataset. So onto the x-axis, I'll be mapping the species column. So iris, and I'll type in species, and onto the y-axis, I will basically map the sepal length column. So again, iris. So the name of the column is sepal length. Alright, so this is a much more beautiful plot when compared to this. So again, the inference is pretty much the same. Alright, so virginica over here would have the maximum sepal length, or the median sepal length would be maximum for virginica, and the median sepal length would be minimum for setosa. So these are the inferences with respect to box plot. Now we'll go ahead and work with the final plot with respect to visualization, which would be a pie chart. So before we make this pie chart, we have to create 2 lists over here. So I'll create first list with the name fruits, and I'll just add some names of fruits. So the first fruit is apple, second fruit is mango, then we've got orange, and then we've got banana over here. So I've made the first list, and then I will give in the cost of fruits over here. So I'll just give in some random values. So 76, 45, 90, and let's say I'll give in 85 as well. Right, so I've got the fruits list ready, and I've also got the cost list ready. Now all I have to do is map these two into a pie chart. So I'll type in plt.pie, and inside this I will first map the numerical values. So I'll type in cost, and then I'll map the labels. So we've got the labels attribute over here, and for this labels attribute, I will map this list to the labels attribute. So I'm mapping fruits onto labels over here. Again, I'll just click on run. So beneath this, I'll put in plt.show. Right, so this is my pie chart over here. So this basically tells us that the maximum distribution, or the maximum percentage, is mostly of orange and banana. And that is actually true. So orange, if we see, the value is 90, and banana, if we see, the value is 85. If you want the actual percentage, we have something known as the auto PCT attribute. So let me add in the auto PCT attribute over here, and I'll put in single quotes. I'll put in a percentage symbol, and then I'll type 0.3. 2, I'll type in F, and then I'll give in 2 percentage symbols over here. Right, so we've got the percentage values over here. Now what does this exactly mean? So this 0.2 basically denotes the decimal value. So if I put in 2 over here, then this will show 2 decimal values. Let's see if I just put in 1 over here, then you've got 1 decimal value over here. Right, now I can also add a shadow to this. So I'll just put in shadow equals true. And this is my pie chart over here. So this shows us that the maximum percentage of the fruits belongs to orange. We've got 30.4%, and then we've got banana 28.7, followed by apple, and then the least is mango. Now let's see if I want to increase the size of this plot. So we have something known as plt.figure. I'll type in plt.figure, and inside this we've got the attribute fig size. So I'll give in the value 6,6 over here, right? So I have increased the size of this. Now similarly, let's say instead of 6,6 I put in 10,10, then this would be enlarged even more, right? So this is our final pie plot. Right, so guys, this brings us to the end of the visualization module.
So in linear regression, it's one of the most popular algorithms in production because it can be used for classification, it can be used for regression. It also happens to be one of the core algorithms that is used by many other algorithms. Logistic regression is a linear regression based model, right? If you take support vector machine, another very famous algorithm in data science, it's a linear model. Or if you take, if you do linear models using binned data, what you call binned data sets, then the model that you get behaves like a decision tree, right? So many of the other algorithms which are very popular in the industry, internally they're linked to linear models. You can spend your entire lifetime studying linear models. It has so much of depth and breadth that it takes a lot of time to actually get used to all these things. So today I'm going to start by introducing you to simple linear models, the core concepts, and then subsequently I'll leave some advanced discussions for the next visit where we'll be covering FMT, feature engineering model tuning. There we'll discuss some further advanced concepts of linear models. All right. So I hope these people have loaded my team has loaded the data set, everything. I'm going to give you 3 codes today, of which I'll cover 1 in the class. The other 2 is for you to go and explore further, okay? Based on what we discussed in the class. This PPT is accessible to all of you. Can you access this PPT? I think she's gone to. You can? Okay. The code is also available. The PPT, the code, the data set. You should have received 3 codes. All right. Let's start. As the name suggests, this algorithm is called linear regression. And the reason why it's called linear regression, as the name suggests, is it's based on the concept of a line, a plane, a hyperplane. We call it by these names. Okay. So to begin with, I need to ask you whether you know how a line is represented. Line in mathematics. Are you all comfortable with this? All right. So let's start. Imagine I give you 2 dimensions. This is x. X is one of your independent attributes. We call it columns in our data frame, right? So I have loaded a data from a table into my data frame, and one of the columns in the data frame, I call it x. This is my independent variable. The other column which I want to predict, the target column, I call it y. Could be anything. Y could be the miles per gallon, and x could be the weight of the car. The more the weight of the car, the less the miles per gallon, right? So y is my dependent variable, x is my independent variable. Imagine this x has 4, 5, 6. These are the units 1, 2, 3, 4, 5, 6. These are the measurements of x. And let's assume, for sake of discussion, let's assume that whenever x is 1, y is also 1. So whenever x is 1, y is also 1. That is what you're seeing in the data. You take another record, there you see x is equal to 2, then y is also equal to 2. Take the third one, x is 3, y is also 3. So when you try to draw a line, a relationship between them, you see it's a straight line. The straight line tells you the relationship between x and y. How are these two related to each other? We in data science call these things as models. Models are nothing but surfaces in your feature space. What is a feature space? Feature space is collection of your independent attributes and the dependent attribute. You're trying to explore how this y and this x interact with each other. That interaction is what we represented as models. So models are nothing but lines, surfaces, hypersurfaces in your feature space. So when you build k nearest neighbors, okay, in k nearest neighbors you have different classes of data points. Suppose these are different classes, okay, and okay, let me make it slightly more complex. What k nearest neighbor does is, we call it breaking your mathematical space into regions. It breaks your mathematical space into regions. So it says this region belongs to the circular point, this region belongs to the triangular point, and you have things on the wrong side. K nearest neighbors splits your mathematical space into regions. Those regions are called Voronoi regions. So this imaginary surface is the model in k nearest neighbor. So in linear regression, this line which represents the relationship in x and y, this line is my model. So I want to predict the value of y given the value of x. What the line is saying is y is equal to x. So the prediction is whenever x is some value, y will also be the same value. Can I write this expression as y equal to 1x? Does it make any difference? 1 into x. This 1 in mathematics, it has a meaning. This 1 is nothing but this angle that line makes with the x-axis, the tan of that angle into x. Whenever y is equal to x, this angle will always be 45 degrees. Okay? And in trigonometry, tan of 45 is always 1. Now you might be wondering, what is this trigonometry, tan, theta, and all? These are all jargons. Actually, it's all common sense. Look at this. When we studied in school, we came across trigonometry. In trigonometry, we came across sine theta, cos theta, tan theta. What are these sine theta, cos theta, tan theta? What are these things? These are names given to certain ratios. So tan theta is, tan means the ratio between, we show it as dy by dx. How much y changes whenever x changes by 1 unit? That ratio is called tan. How much y changes when x changes by 1 unit? How much y changes in this graph when x changes by 1 unit? So 1 by 1 is equal to 1. dy by dx, how much y changes by small change in x, 1 unit change in x, that ratio is called tan theta. Sounds very hi-fi, but that's what it is. Okay. So whenever both of them synchronize, whenever x changes by 1, y changes by 1, it will always happen when this angle is 45. So we say the tan of 45 is 1. So when you say tan of 45, dy by dx will be 1 by 1, it will always be 1. Alright? Let me modify this a bit. So right now this expression is represented as m. Okay, this is a standard practice where we represent it as m. So y equal to mx is the expression, mathematical expression of this line. Suppose I put a line here, okay, and it's parallel to this line. It's parallel to this line, okay, which means this line is also making 45 degrees to the line parallel to x-axis. I'm not going to show this line here, okay, just to make it less cumbersome. So I have another line here. This is L1, this is L2. Now can I say y equal to x? When x is 0, y is not 0, y is 2. Correct. When x is 1, y is not 1, y is 3. When x is 2, y is not 2, y is 4. So we add a constant to this. This constant is equal to 2 right now for this line. This constant is nothing but what is the value of y when x is 0? What is the value of y when x is 0? That is called c. It also goes by the name of intercept. Where in your mathematical space on the y dimension, where on the y dimension does the line intercept or cut the y-axis? So this is the generic equation of a line, y equal to mx plus c. It tells you how y and x are related to each other. If you look at this line L1, if you look at L1, then this becomes 0. So y equal to mx. If you look at L2, this becomes not 0 but 2. So this relation continues to remain same. In both the cases, the m is same. M is nothing but tan of the 45 degrees. We call it slope. Right? So this is the generic equation, one way of representing a line, y equal to mx plus c. So in this expression, y is given in your data set, it's a target column. X is given in your data set, it is the independent columns, the independent attributes. From this data that you have given to the algorithm has found out for you the m and the c. We call these coefficients. Coefficients of the model. This m and the c, they reflect the relationship between y and x in your data set. So the m and the c is what forms the model for you. Shall I complicate it a bit more? We'll complicate it a bit more. Suppose instead of having 1, or let me just continue with this only. So you have one target variable y, one x. In this case, tan of 45 happened to be 1. But suppose your line is like this. It's a straight line, but it's not at 45 degrees, it's at 15 degrees. Right? Then in that case also the equation of the line will be y equal to m x The reason why I'm not putting C is 0 here. C is 0. You can put C, but C is 0. And this angle M, this value of M will not be 1. It will be 1 only when it's 45 degrees. It's less than 45 degrees, so tan of 15 degrees into 1 into x plus c. This will be equation of this line. What is tan theta? Tan theta is nothing but how much y changes for 1 unit change in x. We call it tan. Okay. All right. Let's complicate this a bit more. Suppose instead of only one variable x, now you have x1 and you have another variable x2. And you have only one dependent variable y. In such case, the algorithm will find out the relationship between x1 and y, x2 and y. So it will express that relationship as y equal to m1 x1 plus m2 x2, and there will be only one constant term, because now instead of having a line, you will have a plane where the plane goes through the y-axis at some point, it cuts the y-axis at some point. So now you have two edges. One edge is on x2, the other edge is on x1. The two edges may have different slopes, different angles with x-axis. Those are reflected over here as m1, m2. The C continues to be the same C. Where is the plane cutting the y-axis? Which means, what is the value of y when x1 and x2 are 0? That is called the intercept.
So we're going to have only one plane, like we can't have multiple planes, like in case of a 3D.
In case of?
Like if we have a Z also, so then we'll be having a...
It will be called a hyperplane. We don't know how it looks, but it will be only one. Yeah. So human minds can imagine only 3 dimensions. But suppose you go beyond 3 dimensions, there also the linear models work. Those planes are called hyperplanes. Hyperplanes, how do they look? We can't imagine. So we don't know that, but they will also be one single plane. And there will be no ups and downs, no curves, nothing. It will be a straight plane. What do you mean by straight plane in 4 dimensions? No idea. It will have the same properties as the properties of a plane in 3 dimensions.
So these x1 and x2 need to be in the same plane, or it can be in a different plane, like x1 is in one plane and x2 in different plane. Is it possible?
They will be in the same plane.
Yes.
They can't be in different. Right? And
x1 is one axis and x2 is another axis, and they are like separated with some angle.
90 degrees. This angle in linear models, this is a 3-dimensional isometric view. This angle is always 90 degrees. We say that they are orthogonal to each other. Look at this laptop. Okay, in this laptop, now this is my x1 dimension, this is my x2 dimension. There is a plane. This plane is your model. This plane is making some angle. I can't make it right now. I can't, right? It will make some angle with x1 axis. It will make some angle with x2 axis. This is my m2. This is my m1. So at what angle the plane is to x2 and x1 will decide the value of y. Okay. In this case, the value of c will be 0 because the plane is touching the y-axis. Y-axis is perpendicular like this. It's touching the y-axis at the origin, the 0 point. So imagine I can remove this. If this was a yoga tablet, I could remove this. Okay, and imagine I'm putting it in some angle, cutting the y-axis at some point. Then this angle is my m1, m2. The point at which the plane cuts the y-axis is my c. We cannot imagine beyond 3 dimensions how the planes will look, but they will have the same mathematical properties as a plane in 3 dimensions. point that you should probably keep in mind, it will become useful to you down the line when you do deep learning and so on and so forth. The number of dimensions of a model. This is the model right now, the surface. The number of dimensions, how many dimensions is this model? 2 dimensions, length into breadth. The model is only 2 dimensions. The feature space is 3 dimensions. So the number of dimensions in a model will always be 1 less than the number of dimensions in the feature space. Right? All right. You can call it anything you like. That's not a problem. X, Y, Z. Okay, that's what they're saying. You want to call it Z, you call it Z. Doesn't matter. It just replaces the Z. Basically, these are independent variables. This is the target variable. So we are trying to understand how the target variable is influenced by these.
Say you have 3 x1, x2, x3. So how in that case the model dimension will be, so still the model dimension will be 2 only, right?
No, x1, x2, x3 are 3 independent variables. So therefore on target variables, no? So that makes it 4. 4 dimensions.
4 dimensions. What is the dimension of the
Model will be 3 dimension in that case. I mean, however it looks, I don't know how it will be. How will it look? It will have three edges. We don't know how it looks, so that's why we don't talk about it. But the properties of that model will be similar to properties of a plane, a line, so on and so forth.
So don't imagine, you can't.
So independent variable we have to always consider as the orthogonal in nature.
That is what the algorithms assume. All the algorithms assume that your independent variables, okay, suppose you have a data frame. In the data frame, you have multiple columns. These are independent variables, IV1, IV2, IV3, and this is my target. All algorithms assume that independent variables are independent of each other. They don't influence each other. They only influence the target. That's what they assume, but in real world, that is not true. Suppose I want to predict miles per gallon of a car, given the weight of the car, given the horsepower of the car, we know that they are related. So we can build a model, but we also know that horsepower and weight are also related to each other. More the weight of the car, more the horsepower. They're positively related, but the algorithm assumes that they are not related. This problem in linear models, it's called the problem of collinearity, where assumption is each dimension is independent of the other, but in reality they influence each other. That problem is called collinearity. Okay? This collinearity, where independent dimensions interact with each other, they are not independent. This collinearity can lead you to a problem when you productionize your models. The models may be less effective, less predictive power than required to be because of the collinearity. So one of the things that we do when building models is we see what the collinearity is between the dimensions. If the collinearity is very strong, they're very strongly related to each other, the independent variables, then we may have to resort to some techniques. Suppose this is my horsepower and this is the weight of the car, and if I plot a graph between these two, can you tell me how that will look? This is weight of the car, this is horsepower of the car. If I plot a graph between these two, take all the data points, you will see some linear trend. Okay, all of you know what is R value? Coefficient of correlation, R value. Statistics, you've done statistics, right?
Hey, go on.
Okay, R value of measurement of how these two variables relate to each other, how strongly. You will see that the R value comes very close to +1 in this case. The maximum it can be is 1. So it will be very close to +1. Okay? Which means these two variables are not truly independent of each other. But the algorithm wants all the dimensions to be independent of each other. So in such cases, we resort to a technique called dimensionality reduction. which is not simply dropping the dimension. I may convert them into a composite dimension. Both the dimensions put together, I create a synthetic dimension. And I use that synthetic dimension in my model building rather than these two.
Just a question here. In this case, the horsepower and the weight of the engine is the same, almost same. Like it's increasing at the same in one linear line. It means, well, if I put both of them, it will have the same effect in the model. Right? If I remove one of them also, then it will have the same effect in the model. The model will not change anything. Right?
If that removal is an option to you when the relationship is absolutely a line, but you will see that it's generally not a line, it's a spread, and the spread is also curved. So which one should I drop? Should I drop this or this? That depends on which dimension is more prone to errors when you calculate, when you're capturing the data. So instead of doing all that analysis, I might convert into a synthetic dimension using a technique called PCA, Principal Component Analysis.
One question. So in the previous example, we took two variables, independent variables, x1 and x2, and they are separated by 90 degrees, right?
Yeah.
So in that case, we can have only 4 independent variables. Because 90, 90, 90.
No, that's what I'm saying. That is our brain. Our brain can see only 3 dimensions. But the algorithm can work in 300 dimensions. All the 300 dimensions mathematically will be orthogonal to each other.
Don't even imagine.
Why is there a problem if these variables are actually not very collinear and they're collinear? So why is that a problem?
Okay.
You please keep this question parked for a minute. I want to cover some ground before I answer that question because that's a very important question you asked. All right, let's move on. The term regression indicates that we're going to predict some values. Whenever you build models to predict values, we use the word regression. The term linear, now you understand where it comes from. So your linear model is nothing but a combination, addition of weighted variables. This weighted variable, this is another weighted variable, you're adding the two to predict the value of y. It's a linear combination of one or more variables with weights. The weights are called coefficients. Okay, so once again I repeat, what is this M1? M1 is how much y changes whenever x1 changes by 1 unit, keeping x2 constant. What is this M2? M2 is how much y changes whenever x2 changes by 1 unit, keeping x1 constant. Okay, so this is the relationship between x1 and y. This is the relationship between x2 and y. The relationship is how much y changes whenever input changes by 1 unit. That is a relationship, and that relationship is what we call linear models. We already seen this. I'm going to move on. So before we start building our models, we actually need to analyze our data set. And what I mean by this is, suppose this is my data set. I will go and analyze between this IV1 and target, IV2 and target, IV3 and target, which one of these is strongly related with the target. If suppose IV2 and the target, the distribution is scattered all over the place. It's like a cloud. The data points are spread like a cloud. There's no trend you are seeing in that spread. Then in that case, IV2 is not a good predictor of the target. How can you say that? Take any value of IV2. Draw a straight line. For that value of IV2, you have multiple values of target. Which one should I take? I don't know which one to take. So we say that we say that IV2, independent variable 2, is not a good predictor of the target. On the other hand, if suppose between say IV1 and the target, we see the data points are scattered in some form of a trend, then we say that IV1 is a good predictor of the target. So the first filter that you will apply in your data set is, of all the columns given to you, which columns strongly relate to the target. Those columns which don't relate strongly with the target, you're going to drop them from your analysis. You're not going to build your linear model on them. Okay? So the relationship could be positive, or the relationship could be negative, it could be downwards also. I want a strong relationship. Doesn't matter it's this way or that way, I don't care. But I don't want to include any columns in my model which have this kind of a spread versus the y. Okay?
Sir, but it has to be linear. Like it cannot be a parallel or something like that. Suppose there exists a strong
Ideally, it should not be a parabola.
It should not be parabola. Linear models are built only when you see linear relationships. If you see non-linear relationships, then you might want to resort to non-linear models. Okay, linear models, they expect a linear relationship between y and the independent variables. Then your model's predictive power will be very high. However, as you will see now, those are all very perfect conditions. In the real world, we hardly have such perfect conditions, right? So sometimes, even when the relationship is not linear, we go up, build a linear model. We'll see that down the line. Okay, how do you measure the strength of the relationship between independent variable and the target? For that, we use a metric called coefficient of correlation. How these two variables, the target and the independent variable, how they correlate, how they relate to each other, which we express using a character called R. I'll tell you what this R is. This R metric can have a value of +1, -1 to +1 in this range. The least it can have is -1, the max it can have a value is +1. It cannot be beyond this range. R value can be 0. It can be 0. When you have spread like this, your R value will be very close to 0. When you have a spread like this, your R value will be very close to -1. When you have a spread in the other way, your R value will be very close to +1. Okay? So R value is an indicator of how strong the relationships are. So let's understand this R value slightly more detail. The formula for R value is this. This is a formula for R value, okay? So, shall we begin? Don't worry about the formula. Don't worry about the formula. Understand the concept. All the formulas are there in the library. We just need to call those functions and get our things done. But get the concept in place. Yeah.
So if I have different units of measurement, independent variables, how does the R value then in that case work?
Doesn't matter. R value is a measurement based on the spread of the data. Now, have you heard of scaling? Scaling? Linear model is one model, linear regression, where scaling has no impact. Whether you scale the data or not, it's going to give the same result. All of you know the formula for variance? What is the formula, please?
Square standard.
What?
Variance.
Variance. X
X minus mean
xi minus x bar, you can call it mu, the whole square n. Okay? I is equal to 1 to n. Let's keep it n, but otherwise we use n minus 1. If sample size is less, we use n minus 1. Okay? All of you okay with this? Don't worry about these things. What is this variance? That's what you need to understand, not the formula. Thank you. I know it's spread. What is it telling you?
It means how from the mean means how the data, what is the distance of the data and how it is.
I know, but what is it telling you?
How is it related with the data?
The distance between the
How it varies with
How it varies.
What is the similarity?
What is central value? What is x bar, or what is mu? What is the central value? Don't give me the formula. Don't give me the formula. I know the formula. Central value is a value which represents all the data points that you have. Okay. So if I take all your heights, add it up, divide by a number of students in the class, that will be average height of a student in this class. Now, how good this average is? First of all, why do we take averages? Why do we need mean and median and all? Why do we do all these things? There are many. That is statistical answer. Yes, you're right. But many times in data science, you will come across a situation where you have a function and the function takes as input only one value to predict something. Now, which one of the values should I put? There are 30 students in the class, each one has a different height, right? I want to say order some kind of a code for all the students in the class, a great learning stamped code. Now, what size should I tell the manufacturer? I can't give different sizes and 1 unit of every size. So I have to give some size which will represent all of you so that all of you can fit in comfortably, right? That is the idea, okay? In such situations, we need to input only one value. So what we do is we find the x bar or the mu. But the question is, how reliable is this x bar? Suppose the average height of the student in this class comes to 5.5. Some of you might be 6 footers, you might get offended, you will say, boss, I'm 6 footer, how can you say I'm 5.5?
Depends on how spread this particular, what is the difference between mean and
Exactly.
standard deviation.
So how reliable your central values is based on which you're going to do further actions. How reliable your central values is, that reliability is given by the measure of variance. If the variance is too large, the central value is not reliable, right? So the variance gives you the reliability of the central values, how reliable the central values are. So the formula for variance is this, right? Just look at the numerator. Just look at the numerator. This is the case when you have only one variable, x. Now I have two variables, x and y. I want to see how they vary together, how they influence each other, vary together. That is called covariance, which is given by xi minus x bar. We don't square it into yi minus y bar. So we find out xi minus x bar multiplied with yi minus y bar. That tells me how the data points in the feature space, they vary together. That is called covariance.
So they should not vary together to have high covariance.
Independent variables. Independent variables. Independent variables should not have covariance. Target variable and independent variable should have strong covariance. Otherwise, you don't use those independent variables. When you're building linear models, the target variable, the y, and the independent variables, IVs, should have very strong covariance. But within the independent variables, the covariance should be 0. That is an ideal situation. Practically, it never happens. All right. Now, given this covariance, now look at the formula for R. Okay. On the top, in the numerator, you're seeing covariance, right? And if you look at it carefully, the units on the top and the units on the denominator are the same. This is also xi minus x bar, this is also xi minus x, this is yi minus y bar, this is also yi minus y bar. It is squared term, but there's an under root. This is also squared term, but it's an under root. So both numerator and denominator are going to have same units of measurement, agreed? So if I have a kilogram by kilogram case, then the units cancel each other out. It becomes a unitless quantity, it is a ratio. R value is a ratio. Okay. Now, when you have a diagram, when you have a plot like this, between two variables, could be independent variables, target and independent, could be anything. When you have this kind of plot, you will see that R value is close to 0. We'll see why this happens. When you have this kind of a plot where you see a trend, but as x increases, y decreases, they are going in different directions. X increases, y decreases, they're opposing each other. then we'll have R value close to -1. Whenever they go hand in hand, when X increases, Y also increases. They go in the same direction together. Then R will be close to +1. And it's not very difficult to understand why. Let's look at this particular case closely. I'm going to look at this particular case closely. Yeah, this is my mathematical space or feature space. Both X and Y have some X bar and Y bar, the average, right? X bar, Y bar. Keep in mind, all linear models that we build, linear regression models, they will always go through the point where X bar and the Y bar meet. So the linear model that we saw a few minutes ago, this model will always go through wherever the X bar and the Y bar meet. It will be hinged onto that point. That point will act as a fulcrum. All right? There's one particular point that linear regression models will always go through X bar, Y bar. I'm really surprised and I find it very difficult to understand why this is not told. Now look at the points over here, okay? Let's look at these points carefully. Take any point, let's take this point. For this point, what is xi minus x bar? Xi minus x bar is this distance. This is my x bar, the vertical line. Xi minus x bar is this distance. Agreed? All of you agree? What is yi minus y bar for this point? It is the distance between this point and the y bar. Agreed? Xi minus x bar is positive, yi minus y bar is positive. So when you multiply these two, it is like finding the area of a rectangle. Length into breadth. So xi minus x bar into yi minus y bar for this point is nothing but the area it covers over here. This is the area. This area is a positive area. All of you okay? Let's take another point at the bottom of the screen, say this one. For this point, xi minus x bar is greater than xi, so xi minus x bar is negative. So for this point, xi minus x bar is negative, yi minus y bar is also negative. Negative into negative becomes positive. So all the areas over here will be positive, all the areas over here also will be positive. Agreed? Take this point. Xi minus x bar is negative because xi is less than x bar, negative. Yi minus y bar is positive. So positive into negative will give you negative. All these data points will have negative areas. All these data points will have negative areas. When you total this up, sigma, you see sigma over here? Sigma means sum up all the areas. When you sum up all the areas here, all the positives and the negatives will cancel each other out. The reason why they will cancel each other out is each quadrant has same density of these points. The points are distributed like a symmetrical circle. So whenever R value is close to 0, that is because your numerator is becoming 0. Numerator becoming 0 means your distribution is like this. For a given value of x, I have multiple values of y. Which y should I take? I don't know. So we say that x is not a good predictor of y. On the other hand, if you take this plot, if it becomes tighter, then positive areas is greater than the negative areas. So R value will be close to +1. It will become 1 only when all the data points lie on a straight line, which will never happen. If this plot was this way, all the negative areas will overwhelm the positive areas, then R value will be close to -1. Right? All of you okay? So this is the concept of R value. So what we do in linear models is we test the R values of every independent dimension with the target variable. We select only those whose R value is either close to -1 or +1. Any dimension with R value close to 0 that dimension is a useless dimension. How close to 0 is useless? That depends on your particular problem statement. So generally, any R value greater than 7.7, minus or plus, it's considered as a good variable. Any variable with R value between 0.5 and 0.7, it requires further research whether this relationship is real or is it a fluke by chance that you're seeing in your data set. Any R value close to 0, not worth considering.
What about the second case you told, fluke? What does it exactly mean? I don't understand. Why you said fluke?
Okay. It could be a sampling error. The way you selected your samples from the population, that leads to the R value. Okay. Now observe this. Since you asked this question, let's discuss this out. For R value to be 0, okay, if this is my X and this is my Y, this is X bar, this is Y bar, okay? X bar, Y bar. I'm not showing you the coordinates. For R value to be 0, the data points, suppose I give you 10 data points, the data points have to be absolutely symmetrically distributed for R value to be 0, absolute symmetrical distribution in all the quadrants. What is the probability that when you're doing random sampling, you'll get data points in such a way that they get symmetrically distributed around this? What is the probability? Probability is 0. That particular configuration of data points that you want from the universe, which symmetrically distributes itself around these two X bars and Y bars to give you the R value of 0, that probability is 0. It'll never happen. So even in the real world, if there is no relationship between X bar and Y bar, because of your sampling brings in some asymmetry in the distribution. There'll be some asymmetry in the distribution. You will end up with an R value greater than 0. This R value, we call it statistical fluke. So when R value is very close to zeros, it could be by chance sampling problem. It may not be a real relationship. So you have to go and further investigate whether the relationship is real, it might be real, or is it fake?
It might be possible also R value is greater than 70, but it might be a fluke.
Probability is very low.
Yeah, probably.
That will happen when your sampling is completely gone case. You have done some mistake in sampling. Then it can happen. All right. Shall we move on?
One question. So, what is the application of this? So, one thing is when we have independent variables, how they are closely related, so that we can come out with composite.
Yes. You're talking about R value.
Yeah. Another thing is finding the relationship between how independent is closely related with the target. So, in both cases, we can use.
Yeah, both cases we have to use this. We have to use for both the situations to select the independent dimensions. And within the independent dimensions, knock out those which are very strongly correlated.
So, is this the only Pearson only the way to find out?
No, there are other methods. Carl Pearson is the most commonly used for coefficient measure. There is one more available. There are many such available. But this is one which we mostly use in data science, our cases. Shall we move on? Okay. Now, this algorithm that we are going to use, what this algorithm will do is, given the data set you have, okay, suppose this is the distribution in X and Y. In your data set, you have only one independent column and the one target column. And you see, notice the distribution is like this. So this is a good predictor of this Y. But let me understand in precise terms, what is the relationship between Y and X? I see that there is a relationship, but what exactly is that relationship? Precisely, I want that. That precise relationship between Y and X will be your model, represented by a line in this case. Okay. The algorithm, what this algorithm will do is, it can find out multiple lines here. Multiple lines can be shown here, right? What the algorithm will do is, it will start with some random M and random C. Y equal to mx plus C. Y equal to mx plus C is the expression. Hey guys, I'm talking to you, not to them. Y is equal to mx plus C. So by changing M and C, whenever I change M and C, the relationship between X and Y changes, which means the line changes. The line represents a relationship. So whenever I change M and C, the line will change. Okay? This algorithm will start from some random M and random C. And it will evaluate the different possible lines before it finds what is called the best fit line. Okay? Now what is this best fit line? Amongst all the lines possible that it has checked, best fit line is that which goes through the maximum number of data points. It can't go through all of them. It goes through maximum number of data points, and at the same time, it minimizes the distance between other points and the line. The distance between other points and this line, this distance, you see the distance over here, this distance is called error. What it means is, for a given value of x, your line says the value of y should be this, but your data available in your data set is saying the value is this. The blue line here is the predicted values for the different x. Actual values are the black dots. So whenever you have a black dot above the line or below the line, that means there is a difference in prediction and actual. That difference is called error. Okay? Don't mistake the word error. Error doesn't mean anything negative, but it's used for something that you already know. I'll tell you what it is. So amongst all the different possible lines, there will be only one line which minimizes the sum of all these errors. If I sum up all these errors across all the data points, the minimum sum error will be given to you by only one line. That line is called the best fit line. The algorithm will find out for you from infinite number of possibilities the best fit line for you. It's like looking for a needle in the haystack. And to do this, it makes use of a process which is called the gradient descent. All algorithms use under the hood a learning process, a process which they make use of to find the best model for you in the given data set. That process in this case is called gradient descent.
So the errors that we're talking about, basically that will be very significant to what our alpha level is.
What is alpha level?
For example, if I'm taking that as the level of significance that I'm taking, I'm deciding for business, that I can have maybe 5% of errors there and there. And 95%
You're talking about type 1, type 2 error. That comes in classification. This is regression. However, the same concept will come into play here also in a different way. I'll tell you what that way is. Yeah. So we'll see that way. So again, once again, you have to park your question. We are too far away from those points, right? Shall I move on? Any questions? Yeah.
So the number of points is, the priority to the distance is more than the number of points, right? Listen, so there are two things you told, the maximum number of points it should go through and also the distance. But the distance is the most priority because the errors will be less.
Yeah, error will be less when the points sit on the line, no? So it has to be taken together. Both of them are equal priority, but there's only one line which is satisfy that condition. The driving condition is the error should be minimized. That is only condition, okay? So there are no two-step process here. It's only one step. So let me explain this to you. If I plot, okay, equation of a line is y equal to mx plus c. I'm going to take one simple case, mx plus c, where in your original mathematical space you have x, you have y. One independent variable, one dependent variable. Okay. So now we have two parameters that we can modify, and whenever I modify m and c, I'll get different lines. This is m1 and c1, this is m2 and c2, this is m3 and c3. I'll get different lines. Each line has its own m and c, right? But not all lines are good lines. So if I have this line, for example, this is L1. If I take the L1, L1 is made of M1, C1. I see that many of the data points are away from L1 on both the sides. So the error E1 is very high. If I take, say, the next one, L2, I'll call this L2, I call this L2. I see that L2 has its own slope, its own intercept, and it also does a lot of errors, but not as much as E1, E2. I try out various lines, then I come to LBF, best fit. Best fit line is this, which has its own M, best fit, C, best fit, and E, best fit. And of all these errors, this will be the least. E, best fit, will be the least. Now the question is, by changing my M and C, but just a small minute amount, I'll get a different line. So there are infinite lines possible, which you will have to evaluate. Out of the infinite lines, you have to find the best fit. Brute force will not work here. You can't use brute force.
So when you talk about gradient descent, right? Say I'm actually trying out or this thing. I started with a particular MNC. And slowly I moved on. I'm correcting my errors. So errors are getting reduced. All of a sudden, it again started increasing. Right?
That will not happen, right? Except for when you cross the best fit point. Okay. I'm coming to that now. Okay. So instead of looking at this mathematical space, I can actually look at another mathematical space, which is related to this. That mathematical space is between M and C, and this dimension is error, where error means sum of all the errors put together. Okay? In linear regression, this error is calculated as y hat, that is predicted value of y, minus y actuals, okay, raised to power 2 divided by n. N is the number of data points. I is equal to 1 to n. We call it squared error, sum of squared errors. Sum is sigma, squaring the errors. So the error done by model is nothing but a sum of squared errors. N is the number of data points you have. Isn't this formula for variance? So error is nothing but variance. How data points vary, scatter across the best fit line. The lesser the variance, more reliable the central value is. The lesser the variance of the points across the model, the better the model is. Same concept comes to you in a different way. So sum of squared errors is nothing but variance, variance of the data points across the model. So I want to find that model where the variance of the data points across the model is the least.
So it's slightly confusing. See, when you say covariance, right, and you said like if you have more value of covariance, then it is better for dependent versus independent. Right?
More values R.
That is not
R is measurement of degree of covariance.
Okay.
Okay. The stronger the R is, the better the predictor is.
So degree of covariance should be higher, whereas variance should be lower.
Variance in individual dimension should be low.
That is
comparing with some other box model.
That is also
always we are
We
are omitting the outliers and all. So in the data which we are collecting, we are removing the outliers. It will always in the like a group of data which is affecting the some model. So always it will be in the linear model, right?
Yeah, I didn't get your question. Come on again. Yeah, you said box plot, you identified outliers, you removed
So we are
outliers.
removing it. So we are collecting the data which is going to affect the model. So if we are plotting in the any linear regression model, it will be always in the linear model.
Not necessary. Varun, I'll take your question. I'll just hold on a minute. I'll take the question here. Within 1.96 standard deviation on this side and this side, the data points might still have noise in them, which causes a spread across the model. You're talking about outliers which is lying 1.96 standard deviation greater. So by removing that, yes, you're cleaning the data, but within the 1.96 standard deviation, still you have noise. That noise will appear as scatter around the models. It will appear as variance around the model.
But once we are omitting the unwanted data, so it will be in the like linear regression model, but with some noise.
Right. It will never be one single line kind of thing. Actually, you have asked a very, very important question, which I will just answer this because this is a very important question which will be helpful down the line. Just hold on a minute. I'll answer the question first. Okay. Now, if I take any axis, any variable x, it has a spread. Okay. This spread, variance, what you call variance, there are two types of variances. One is called stochastic variance, which means nothing but probabilistic variance. The other one is called deterministic variance, which means variance that happens for reasons that I know. I know why that variance happens, okay? That is called deterministic. But variance also happens in your data set for reasons that I don't know. We call them noise. Okay, that is called noise, all right? Now, if I have a plot like this, a linear model, and I have distribution of the data points around this, okay? For a given value of x, now look at this. Actual value is this in your data set, but the model is saying it is this. Similarly, there's another actual value which is this. Why is this variance occurring? I don't know. I don't know why that variance is occurring. This is called, I don't want to use the words right now, I'll use it down the line. This variance that you see, for a given value of x, you have multiple values of y, but they're very close, but still there is a variance in them. That variance is called stochastic noise. Okay? For a given value of x, the fact that value of y is spread around its central bar, this is deterministic. We know that this is going to be this way. All right? So when you address the outliers is something which is lying 2 standard deviations away or 1.96 standard deviation away. You're addressing the outlier, okay. But you're not addressing the random variance which exists in the data points within the 1.96 standard deviations. Those will cause a scatter of the data points across the model.
Yeah, you were talking about the real actual data point or the prediction point?
Prediction is your line. Actual is the black data points. Between the actuals and line, there is a gap. That gap is my stochastic. Unexplained variance. I don't know why it happens.
That's the actual data.
Yeah, in the actual data. Deterministic is, I already know my y bar has this spread and my x has this spread. This spread is also variance. I already know it has this spread. I know it will be like this only. I have no reason for worrying about that. What I'm worrying about is, for a given value of x, why are there multiple values of y? That is stochastic. We don't know why it happens. That is what we call noise.
Is it because of lack of domain expertise? Nothing to do with
even the domain expertise will have this problem.
So when we have a multi-dependent variables, right? So here we are talking about trying to find out the only one and then y. Okay, but maybe when we are we have to analyze it in the togetherness
Multivariate analysis.
Maybe that is creating this kind of noise because we are trying to target on a single one, right?
That can happen. That can also happen. When the different variables actually interact with each other, there's collinearity in your data set. You can have trouble with this noise. That can happen. The noise may get cancelled out, or the noise may get magnified. What can happen?
One more question. So we are looking for best fit line which give us the least error.
Least sum of squared errors.
What is the definition of least? Mean
I'll tell you what is least. That's what I'm going towards now. Okay. So I have different combination of M and C. So I moved away from my original mathematical space into another mathematical space where the dimensions are the different slopes and different intercepts. different lines, okay? Each line gives you some error, okay? The formula for this error is the sum of squared errors, which is nothing but variance across the line. Whenever you have a squared term, this is called quadratic equation in mathematics. All quadratic equations, they have a property. The property is called, they are convex functions. Convex functions means when you plot them against their independent variables, m and c, they will always acquire a bowl shape. Three-dimensional bowl. Such functions which acquire this kind of a shape, a bowl shape, in the 3 dimensions, such functions are called convex functions. They are guaranteed to have one absolute minima. Parabolic structure. One absolute minima. So for some combination of m and c, I'll get the least error. That combination of m and c, which gives me the least error, is my best fit line. So the algorithm will start from some random m and c. So maybe this is the random m and c. This is my random m and this is my random c. When I use this, I get a line, but the sum of squared errors across the line is very high. So each point here is one line in the original mathematical space. So in the original mathematical space, between x and y, if this was my L1, maybe this is the L1, it had some m and some c. That m and c is this point represents this line. This line had some sum of squared errors. The sum of squared errors is this.
So you talked about 1m, but if it is multiple m, still it will be like similar?
Still 100%, guaranteed.
Okay. But we can't visualize.
We can't visualize. Okay? All right, no kidding. Let's move on. Now what this algorithm does is, it starts from some random m and c, and it uses a concept called gradient descent. Descent, as the name suggests, we have to descend, okay? Gradient descent algorithm, which internally makes use of what is called partial derivatives. Partial derivatives. And this term partial derivatives, I'll tell you what it is. It's not a rocket science. It is dy by dx. It's exactly dy by dx. What it does is, for a small change in m in this direction or this direction, for a small change in m in this direction or this direction, from the first m, the random m, for a small change in m in this direction or this direction, dx, how much the error drops or increases. So when I change it in this direction, I'm going further up, the error increases. dy increases. Whereas if I go in this direction, I reduce my m, my dy decreases. So it notes down that I have to move in this direction. But you have taken only m right now. How about c? So do the same thing with c. If I increase the c slightly here, what happens to my error? If I see it slightly here, what happens to my error? I'll go in that direction where my error decreases, descent. So using this concept of partial derivatives, which is nothing but dy by dx applied on individual dimensions one at a time, that's why it's called partial. It finds out, it moves from this line to the next line to the next line to the next line until it reaches this point. At this point, what will happen is, whichever direction you move in beyond this, the error is only going to go up. Whether you go this side or that side, error is not going to come down further. So it realizes that it has reached the global minima. This is your best fit line.
Which is the relation between M and E plus C.
Correct. M, C and E put together. This is the best fit line. That best fit line happens to be this line, BF. So it does not evaluate infinite lines. It uses this gradient descent concept and finds out for the next best fit line, next, and reaches the global minimum.
So is there a chance of jumping that?
Yeah, there is.
And there can be local minimas as well in case of...
Not in quadratic functions.
Not so in linear regression we'll never have local minima.
You'll never have. If you use neural networks, you can get stuck in local minimas.
Okay.
Linear regression, the error function being quadratic, it guarantees you'll reach absolute minima. Okay, but in the process of jumping, there is something called learning step. Okay, we are too far away from this, so I'll just tell you the concept, which is used along with the partial derivatives. If the learning step, the amount of change that you do in dy and dx, if the learning step is too high, you might jump and oscillate. You might jump the global minima, go on the wrong side, and keep oscillating backward and forward, infinite loops. So the learning step is adjusted. As it keeps jumping down, the learning steps become smaller and smaller. There are various ways of handling this to prevent the oscillation. One of the ways is, as you jump towards your objective, the goal, the steps become smaller and smaller. This algorithm is called bold driver algorithm, which is part of your gradient descent, one variant of gradient descent. When you do deep learning, this partial derivatives will become very important for you to understand how the neural networks work, how the back propagation of errors happen. Those things will come into play. Okay, but we still have a lot of time before we reach there. So hopefully I'll spend some time on this one day and tell you what this is.
Both in bold driver as well as gradient.
Yeah.
In both we can.
Yeah, you can. Yes. But you have various other algorithms now which have come up, which is apparently better than this. Okay, we'll talk about those things down the line. Shall I move on? All of you? Okay. Your questions are still parked, right? The two questions. What are those two questions?
One is the standard deviation, like one is about error delta.
He doesn't.
So it's basically the first one was the collinearity between that got answered. Okay. Within the variables, within the set of the dependent variables, why there should be no collinearity.
Why should there be no collinearity? What happens if there is collinearity? That was one of the questions which came up. I remember that. Good. So my strategy worked. Okay, let's move on. We'll discuss those things in detail, right? Okay. So keep in mind, we are looking at these data points closely. The distance between the actuals and the line is the predicted values. For a given value of x, the predicted value of y is the blue line. The distance between the actual, which is shown by the black dot, and the line, that distance is shown by yellow dashed lines. This distance is a measurement of error. Okay. The objective is square of these errors, all these errors squared, that sum should be minimized. Okay, which is not very difficult to conceptualize once again. So if I have my linear model drawn like this, best fit line, the data points are scattered around this. You look at the data point from this angle. When you do that, you will see a spread. This variance, this is called sum of squared errors, which is nothing but xi minus x bar. X bar here is your predicted lines. So formula remains same. That variance is called sum of squared errors. That variance we have to minimize. The minimal the variance is, the better your model is. All right. So let me explain this to you, because you're going to come across these terms down the line. So let me explain this to you in slightly more detail. We're looking at this model, and the distribution of the points, the red points is given to you. The blue lines are x bar and y bar. And keep in mind, your model, the best fit line, will always go through the point where x bar and y bar meet. Always. Okay. Now look at this. Don't worry about these terms. It's all, not very difficult to conceptualize, visualize. What happened? Yeah, there you go. Now, if I take the red point is the actual point in my data set. In your data set, in your data frame, there is a record with value of x, and its corresponding value y is red, the P1. But the model, the best fit line says the value should be yellow, P2. The distance between P2 and P1, this is what we call error, the variance. This is what we call sum of squared errors. Okay, I'm showing you only one data point here, but you have to imagine there are multiple data points here. Sum of squared error applies all together. Okay, so this contributes to the sum of squared error. There is another term that we use which is called total error. Total error across all the data points put together. The total error is nothing but the difference between y bar, the expected value of y, and the actual value of y. In your data, there is a distance between the actual value of y and the predicted value, the expected value of y. Expected value is y bar. That distance is called total error. Of the total error, your model has captured this much. Your model is a regression model, hence the name given to this is regression error. Of the total error, your model has predicted this much error. Of the total error in your data set, your model has predicted this much. The difference between predicted and the y bar. This distance is called regression error. What it has not been able to explain is this. This is called sum of squared errors. Sum of squared error has another term which is called residual errors. Residuals are those things which we don't have a reason for. We don't know why they occur. They're called residuals. Sum of squared errors is also known as residual errors. So when you build these models, especially when you go to your deep learning part and all these things, you'll come across these terms. Total error is the distance between your actual data point and expected value. Okay, so if the average height of this class is 5.5, the difference between your height and 5.5 is the total error. Now you built a model to predict the height of a person in the class based on the characteristics of the person. So your model predicts some value for you. So the model predicts the height to be 5.3. Your actual height is 6. 6 minus 5.3, that is 0.7. 0.7 is the distance between, 0.7 is this distance. Your actual height minus predicted height. Right? The distance between your height and the class average, that is the total error. Okay, so you'll come across three terms: total error, sum of squared errors, and regression error. Keep in mind, regression error and residual errors, these two together is your total error. And don't mistake the word error. Error means variance. Error means variance. Of the total variance in your data set, I told you one part of the variance is caused by the deterministic. The other part of the variance is caused by the stochastic, non-deterministic. Same thing. Non-deterministic is your residual errors, sum of squared errors.
So also you told this, see, total error or regression error, what a residual, is particular to particular point, right?
No, in this case, I'm showing you only one point, but you have to imagine all the points together because this SSE, SSR, they're across all points put together. What I'm saying is what contributes to SSR and SSE. That's what I'm showing you. So you have to imagine all the points here. That becomes too cluttered. That's what I'm showing you. What contributes to SSR, what contributes to SSE, that's what I'm showing over here.
So least error is belonging to SST, right?
Yeah. Least error is belonging to SST means?
I mean, we are talking about total error.
Total error is this. I want to minimize this, unexplained error. That is what my objective is. The gradient descent works in finding the best fit line for you, where best fit line is that line where this error is minimized. Because I don't want a model which is not able to tell me why. I want a model which tells me why this error.
So you will not try to reduce the regression error.
No, we'll not try. We'll not do that. Because that is deterministic. I know why it happens.
It's because of the variance of the.
It's because of the natural variance in the process. Okay, when you're running a process, many things come into play, factors come into play, because of which the values change here and there around the expected value. That is okay with me. But for a given value of input, there are multiple values of y that I don't understand. So for given value of input, there should be only one value of y. Why are there multiple values of y? That I don't understand. That part is my unexplained error. I want a model which unexplained error is minimized. I don't want a model where unexplained error is very high. What is the use of that model? It will not predict anything.
Okay.
When you say given value of x, you have one value of y. So in this case, in this case, the P2 is that one value. That's what you're talking about.
P2 is predicted value, but you have multiple values of P1s spread around the line. That gap is unexplained. That variance is what we call stochastic, random variance. We don't know why it happens. So basically the idea is to minimize SSE, that's all. The bottom line is minimize SSE. So increase the SSR to SST ratio. That is what our objective is. Yeah. All right, let's move on. So before you build the model, you have to evaluate each independent dimension and see what is the R value. R value, coefficient of correlation, comes into play to help you identify good predictors given the target. Okay. Once you build the model, I want to see how good the model is, how reliable the model is. For that, we use another metric. That metric is called coefficient of determination. And this is represented as R square. But before you jump to it, I should caution you, R square is not always R into R. R is a coefficient of correlation. So natural to think that R square will be R into R. That is true only when you build a simple linear model between one dimension, one target. It's only true at that point. In multi-dimensional, multivariate analysis, where you have more than 2-3 dimensions, you can't say R square is R into R. Okay? So R square is just a symbol which represents another metric called coefficient of determination. How much of the total variance in your Y has been explained by your model? Keep in mind, the total variance in Y is consisting of two components: deterministic, non-deterministic, stochastic, random. How much of this total variance in your Y has been explained by your model? That measure is called coefficient of determination. Obviously, a model which explains maximal of the variance in Y, it leaves behind very small residuals. That model is the best model. So R square, it ranges between 0 and 1. 0 means your model is not able to explain anything. Absolutely useless. 1 means your model is able to completely explain all the variance in your target. There is no residual. Such models don't exist. We can never build such models. Usually R value will be between 0 and 1. The closer they are to 1, the better the model is. Because in simple linear models, it's a squared term, it can never be negative. But keep in mind, in multivariate analysis, it's not just a square term. It's something more than that. So it'll always range between 0 and 1. Are you all okay?
How much variance in Y means? Like,
if say this is 0.8, that means your model is able to explain 80% of the total variance in your Y. Total variance, which includes stochastic and deterministic. Right? So your R square should be as close as possible to 1, your model will be good. So this metric is used to evaluate the performance of the model, while R is a metric which is used to evaluate the independent dimensions when you're building the model. Geometrically, okay, if you take one simple linear model of one x and one y, okay, that's what I'm showing here. So this is where your x bar and y bar meet. Please look at this carefully. This is my y bar, this is my x bar. Okay, so there is an actual data point. Xi minus x bar is this, yi minus y bar is this. That gives us an area, rectangle. We saw that earlier, right? That area represents the total variance in your data point. The total variance in this data point, the covariance in this data point because of x and y. This is that area, the light gray area. The light gray area is this. It's behind this dark gray. Okay, the light gray area is this. That light gray area is a geometric representation of the total variance because of x and because of y in this data point. Of this total variance, for a given value of x, your model is predicting a value of y to be this. So this predicted value of y minus y bar, x bar, this dark area is the explained variance. How much of this total variance has been explained, captured by your model? R square is the ratio of the dark area to light area. What you're seeing on the top, this is the residuals, unexplained variance. So R square is again a ratio, where the ratio is between the total variance in the data points and the variance explained by your model. That ratio is called R square. Obviously, the lesser the residuals, unexplained variance, the better the model is.
So we want more R square actually.
Yes, exactly. But there's a problem. There's a problem here. The problem I can explain to you in simple terms. The problem is, go back to our discussion on R, where I told you, if there is no relationship between these two, the target and the independent variable, you have to get a perfect symmetrical distribution. But the probability of getting a perfect symmetrical distribution is 0, which means you're going to get some asymmetrical distribution. The moment you have asymmetrical distribution, your R value will be greater than 0. Magnitude, this way or that way, which means R square will be greater than 0. R square is not considered as a very good metric for evaluating the models because it is easily impacted by fluke relationship. So we make use of another metric that is called adjusted R square, which is nothing but R square minus fluke. There is a formula for this. How do you find out the fluke content? Which I am going to avoid right now because it's too detailed to discuss. In case you're interested, let me know, I can share it with you. Conceptually it's easy to understand, but the argument is very lengthy. We won't have time for that. That's why I'm going to ignore it right now. So the metric that we'll make use of to evaluate our models is adjusted R square, not R square.
But in real time, we don't calculate this fluke.
We do. It calculates, the algorithm does automatically.
Automatically. We do. Okay.
We know. The beauty of adjusted R square is, whenever in your model building exercise to predict your target, when you include useless variables which don't really have any significant impact on the target, but their relationship is statistical fluke. When you use such useless variables, R square will keep on going up and up and up. It will come closer and closer to 1. But adjusted R square will go down. It will decrease. So when you include useless variables in your model, adjusted R square will go down. It will reduce. Whereas R square is likely to go up. Adjusted R square will go up only when you include good variables in your models. Good variables are variables whose relationship is significant, strong. So we use adjusted R-square for evaluating our models. One thing that you need to keep in mind, conceptually get it clear, any attribute that you use in your model building, any attribute, that attribute will always have both the components, good R and fake R. It will have both the components. But in a good attribute, the percentage of this will be very, very high compared to this. In a poor attribute, useless attribute, percentage of this and this will be almost similar. That is why when R value is close to say 0.5, 0.6, part of it will be caused by fake R, part of it will be real R. How much is real, how much is fake, I don't know. That's why it calls for further investigation before you decide to use that in your model. When R is close to 0.5, 0.4, 0.3, we don't know how much of that is fake, how much of that is real, we don't know. That's why you need to further investigate before you include or exclude from your models.
How we get the explainability of the fake? What is actually causing fake?
Randomness in the your sampling techniques itself will bring in fake part. When you use random function to sample from population, since you asked this question, whenever you do sampling, any technique you use, clustering, layered sampling, mixed sampling, whatever you do, your sample will never be a true representation of the real population. It will never be. So its distributions will be slightly different from the distributions in the population. That change in distribution is what will introduce fake R's.
It's only sampling which introduces fake?
Sampling is the source of this.
Oh.
Right? Did I show you that video where I showed you universe to be under flux, continuously changing? It's never static, whereas your sample is a snapshot, a frame in the video.
Variance error and the error keep changing.
Will keep changing, right? Shall we move on? Okay, I'm just taking you through the concepts. I'm not telling you what is the formula for all these things. They'll become too heavy for you right now. But I will eventually take you through in case you're interested. Some assumptions that this linear regression models make. We already discussed this. Assumption of linearity. The relationship between the target and the independent variables are expected to be linear. Oh, that brings me to another point. Please be careful. When your R value is close to 0, what does it mean? Okay, I think that's what I ended up saying. There is no linear relationship between x and y. Okay, when R value is close to 0 between y and x, that means there is no linear relationship. That does not mean there is no relationship. For example, if I give you a distribution like this is x and this is y and this is parabolic, there is no linear relationship. When you find R value for this distribution, it will come close to 0. But they are related. There is non-linear relationships. So whenever you do this analysis, R value is close to 0, go back and check your pair panels, pair plots. Is the relationship non-linear? If the relationship is non-linear and you're building a linear model on that, you're doing a mistake, a fundamental mistake. Okay? Same way, if you have a distribution like this, R value will come to 0. But there is a relationship between y and x, A sine omega t. A is the amplitude. Sine theta, you know what theta is. So when R value is close to 0, that does not mean there is no relationship. It means there is no linear relationship. If you have such attributes in your dataset, then you may have to think twice before you use linear models.
So unless we draw this pair plots, right, we will not come to know that we have this kind of non-linear relationship. So is it always suggestible to draw pair plot for each?
100%. If you ask me, I'll always say pair plot is the most important tool you have in your toolbox, which you should use to understand your data.
And suppose we got some pair plots, so we should not try those attributes at all for the model.
Try a different model, maybe a non-linear model. Okay, so now that brings me to a question: what is linear and what is non-linear? Okay, now look at this. This is slightly funny and at the same time something which is actually serious. This y and x, okay, mathematicians will say, suppose this is x, this is y, and the expression is y is equal to x square. Mathematicians will say this is a non-linear function. Data scientists call this linear function. Okay, what we can replace this with some value k, so y is equal to k. So I can convert this into a linear and then build linear models on this. So when you build linear models, y equal to mx plus c, the reason why they're called linear models is these coefficients, they are not raised to the power. They're raised to the power 1. That's why they're called linear. They're linear in terms of coefficients. If I have a model like this, y equal to mx square plus c, for us, it's a linear model. Okay, so don't get confused with this. A lot of mathematicians will say this is not linear, but for us in data science, scikit-learn or R, this is a linear model. It'll show us a trend. You'll see that if you do an AutoMPG case, in AutoMPG case, MPG is the target, and your X is a weight of the car. You will see that the data points are scattered like this. You can still use linear model on this. You can still use a linear model on this.
So if R is close to 0 and if my scatter plot showing quite dispersion, so in that case I can say it's a real one. So I can remove it.
Yes.
But if R close to 0 and if there is some parabola kind of thing, in that case,
non-linear models you might have to go to. Non-linear models are models where these coefficients themselves are complex coefficients. They are not simple coefficients. They are not simple ratios. They are something like e raised to power I theta and all those kind of things will come over here.
if we have in multi-independent variable case, if one is showing linear relationship, other is in that case.
So you will have to try both, build a linear and non-linear, see which generalizes. Finally, what is the objective? Objective is it should have minimal bias variance errors. Which one gives you that minimal bias variance error? Put that in the picture. Combo is what we call ensemble techniques. In production, we never put one single model into play. We always put multiple models grouped together in a play. We always install multiple models put together. Varun, good morning. No problem, sir. That's okay. Camera is facing me, not you. It's okay. Right? Okay. But don't knock the camera off here. He is also sleeping. Right? So what we do is, have you seen this Kaun Banega Crorepati? Have you noticed that the audience never go wrong? Though the audience individually may not have very high IQ, but put together they rarely go wrong. This concept is called wisdom of the crowd. The same concept is used in data science also. When we productionize our models, we don't put one single model into play. We always put a collection of models into play. That is called ensemble. The algorithm assumes that there is a linear relationship between independent variables and the target variable. It also assumes that there is no relationship between the independent variables. That all algorithms do. There's nothing particular about this algorithm. Assumption of normality of error distribution. This algorithm assumes that the model that you build, the best fit line would be such that the variance around the best fit line will have normal distribution. What do you mean by this? If this is my best fit line and the data points are scattered around this, and when you look at it from this angle, it will have a normal distribution. This is not guaranteed. Sometimes you end up with a best fit line and the best fit line, you might see a distribution like this, more errors on the positive than on the negative. This happens when you have outliers in your data sets. This algorithm, all algorithms will go down on their knees when it comes to outliers, but this particular algorithm is prone to outliers. If you have an outlier somewhere in your data set, the best fit line will get pulled towards that. It'll get pulled towards, it'll gravitate towards the outliers. Okay? So when that happens, the best fit line that you get, the MNC that you get, that MNC may not be the right M and C for a production. So model may perform poorly there. Okay? So when you build up models, linear models, any model, the first thing we have to do is handle the outliers first. Okay? There are various ways of testing this out, whether this is happening or not. One of the ways of testing this is you do a scatter plot between the actual values of y and predicted values of y. Okay? Between actual values of y and predicted values of y, since the data is spread around the best fit line, there should be no correlation. The distribution to be scattered like this. Predicted value of y, actual value of y, there should be no correlation between them. When there is no correlation between actual and predicted, that means your data is evenly distributed across this best fit line. Sometimes you might notice there is a trend in these errors. There is a trend, some kind of a trend. In the difference between actuals and predicted, there are trends, which means there is a trend in the residuals. As the value of x increases, the residuals increase in magnitude. When you see such trends in the residuals, that means there's something not correct with your data sets. Maybe you're having outliers, maybe you're building models on non-linear data sets. Those are kind of things which will come out. I don't know whether you heard this word, homoscedasticity of errors. Homoscedasticity, heteroscedasticity, there are two things that will come across in statistics. What it means is, as you build the model, the errors should not spread out like a cone. The spread of errors across this model, for all the range that you have, the spread should be more or less uniform. Sometimes you will see that as the value of x increases for the best fit line, the magnitude of the error increases. The spread is still normal, but the magnitude of errors, residuals, for higher value of x is different from the magnitude of errors for lower value of x, the independent variables x. Such things indicate heteroscedasticity, homoscedasticity. The expectation is it will be homoscedastic. Homo means homogeneous. Okay, so the residuals, irrespective of what the range of x is, will be similar across all the range. Assumption of independence of errors. I mean, error done in one record is no way influenced by the error done in another record. Error done on one dimension is no way influenced by the error done on other dimension. The dimensions are independent of each other. That assumption is what is usually violated. But still, we go ahead and build our models. I found a very good what you call site which discusses these errors. I've given you the URL here. By any chance you've done this Durbin-Watson test statistics? You've done statistics, right? The inferential and this thing, descriptive statistics. Inferential statistics, you would have done z-score, z-test. You've done all the t-tests and all these things you've done, right? Okay. If you've done those things and if you remember those things, maybe you would like to visit this site. A lot of information. Please expand your horizons. Go beyond what we teach you in the class. It's just not possible to teach everything in the class for the time limit. So go beyond the whatever we teach, expand your horizons. Yeah, that is what will give you a very firm, sound footing into data science, and you'll be able to face situations confidently. So wherever I come across any URLs, any articles, I'll share those things with you on the slide. Advantages, we are still not out of the woods. There's still much more to come. We're not yet learned the full stuff, but we'll do a hands-on and then we'll see the other stuff. Advantages is very simple to implement, and it's easier to interpret, provided the number of dimensions is less. So when I have equation like y equal to m1 x1 plus m2 x2 plus c, I can give a physical meaning to this. I can say for every 1 unit increase in x1, how much y changes, that is given by m1. So I can physically interpret this. I can give physical meaning to this equation. You can't do this in all the cases. You may not be able to do this. Suppose you are using neural networks. You can't interpret those models. We don't know what they are. They're all black box.
Sir, what do we mean by physical definition?
I can convert this, whatever this formula is telling me, I can map it to English, right? I can tell you in day-to-day language what it is telling you. I won't be able to do that if I use, say, random forest. You're going to do ensemble where you'll do random forest. Random forest is a black box model. We don't know what it's actually doing inside. Support vector machine is a black forest. We don't know what black forest is a pastry. Black box. We don't know what it's doing inside, right? This model is a white box. Outliers can bring it onto its knees. This particular model is prone to outliers. All linear models are prone to outliers. Decision tree is not prone to outliers. And this is a very important point. Since the linear model goes through the point where x bar and y bar meet, the best fit lines, the lines evaluated for you go through where the x bar and y bar meet. If your x bar and y bar are not reliable, then your model itself will not be reliable. So if I built a model on a dimension y and x, where this is a very large spread, the x bar is not reliable. When x bar is not reliable, how will the model which is going through the x bar, making use of this x bar, how will the model be reliable? Right? So the more time you spend in selecting your attributes to build the models, the higher the quality of the attributes that you use to build the models, the better your models will be. And the last, boundaries are linear. This is a problem not in regression, this is a problem in classification. Okay, so if we can use linear model for classification also. So if you're having a distribution of classes like this, okay, and then this, and you're trying to build linear classifiers, you'll get probably a line like this as a best fit line. So above is this triangle, below this is circles, and one triangle is. Whereas on the other hand, if you have made use of non-linear stuff, non-linear models, then probably you would have got a better result. Maybe you would have gotten something like this. Okay, so if you use non-linear models, it might do a better classification than linear models. So this limitation is not in regression, it is in classification. Let's do one hands-on. Okay, the hands-on is not AutoMPG dataset as it is given here, it's the other one, which is simplistic. So we'll start with simpler ones. The other one which I've given to you is CAR. Okay, CARPy is linear regression. I've taken the dataset directly from the UCI site. It's called imports_imports-85.data. This is the name of the data file. Okay, so instead of downloading it, I'm directly reading from there. So let me begin. Matplotlib is an instruction to the Jupyter notebook to make all the plots in the notebook itself, sorry, Jupyter server. I'm importing pandas, numpy, and from scikit-learn linear model libraries, I'm importing the linear regression. You can have linear classifiers also. Then I'm reading the CSV file which is available in this URL. It's a comma separated file, and I've taken all these column names from the UCI dataset. So that gives me the data frame which I call car_df. This is my data frame. All of you okay? So this is like loading a data into a table. So let's look at two records. Transpose is not a must, but since the number of columns is huge, I put a transpose. I'm seeing first two records, record 0 and record 1. There is obviously missing data in some of the columns. And there is string data types in other columns. Fuel type, gas, it's a string data type. Number of doors, 2, it's a string data type. All right, no problem, go down. Our objective is to predict the last column. Given all these independent variables, can we predict the price of the car? Is there a relationship between price and all these variables? That is what we want to find out. What is that relationship? But before we do that, look at the data types. Many of the data types are object. Object means string. Machine learning algorithms cannot handle string data types. They have to be converted to numbers. So what I'm doing here is, I'm going to convert into numbers. But before I convert numbers, I'm dropping some of these columns. The reason I'm dropping these columns is, if you go and take a frequency count on these columns, fuel type, for example, or engine location, for example, most of the records have only one value for this. This is called low variance filter. Look at all the data provided to you. In the data you have columns, where in the columns there is not variance at all. There is a gender column. Gender column, all the data is about males. Then that column is useless. It's not going to give you any information. Such columns are called low variance columns. Though they are supposed to have multiple values, they have only single values, a few values. We remove them from the analysis. So when I did this,
So you usually do this check and get to this conclusion?
Yes. You do frequency count, very complex conclusion. What I did is I've manually browsed the data file. This is an Excel sheet, CSV file. You can actually see, let's do it now, why are we talking? Let's do this. What you do is, go to this site and let's download this data set. Control C, okay. Now, HTTPS, double quotes. Thank you. Now we'll save this down. We'll save it as. Let's save it as text document, and then we'll load it up. I'll just call it. Okay, where am I saving it? I'll save it on desktop. Okay. Done. Let's open it. Okay. Let's start Excel. Excel is running into problems with C. Oh God. Oh, okay. Okay. It's going to clash with their recorder. So I'm not going to open this. Let's get on to this code, but do this analysis. You'll find that these columns are having low variance filters. They're fit to be kicked out. Right? So then what I do is, I saw the car data types, the column data types. Most of the data types are object, string types. I dropped my useless columns. Number of doors, most of them have 4 doors. Then fuel type, most of them are giving the fuel type as gas. Engine location, most of them is front, 1 or 2 is in the rear, so on and so forth. So once I dropped them, I'm still left with some object data type. Number of cylinders is object. And any other object data type? No, only that is object data types. Single value there, we're dropping it. Okay. Which means the current price of the car is not a function of that, it's a function of other variables. Okay, look at this. Hey guys, do you understand why we drop low variance filter? The reason why we drop low variance filter is the price is not influenced by this particular column which is low variance. If the price was impacted by this column, which is low variance, then all the prices should be fixed, right? Which means the variance in the prices is because of the other columns, not this column. So that's why we drop it. Now the number of cylinders, what I'm doing here is I'm converting all this into numbers. So wherever I come across a string called 1, I replace it with numerical 1, 2, I replace it 2, and so on and so forth. You should do this with care, okay? You should do this with care. Suppose you had a column called gender and the gender was male and female, then I cannot do this blindly like this. Because if I replace a gender, say a male with 0 and a female with 1, then I'm introducing an order in that column. That's called ordinal columns. 0 is less than 1. But there's no such relationship in the real world. So if you have a gender column, then I will use a technique called one-hot coding. One-hot encoding. I will use that technique to replace my strings into numbers. That example I have given you in AutoMPG dataset. Okay, you look at that later. Okay. On the other hand, if I have a column called income group, where they have income groups like low, middle, high. Now there I can go and replace low income group with 0, medium income 1, high income with 2. Because the same order which exists between 0, 1, 2 exists in that column also. Okay. So if your column is an ordinal data type, you can go and introduce order in your numerical values. If the column is not ordinal, gender column, then you cannot blindly convert them into 1 and 2. You have to resort to one-hot coding. In scikit-learn, there is a facility function called label encoder. Label encoder introduces order in your data. So be careful when you're using that. Instead of using label encoder, use one-hot coders. All right. Everything has a part. Yeah.
Before dropping this variable, we have to convert it to level encoder or one-hot encoder.
Which variable?
We dropped all the variables.
Not necessarily. Since we're going to drop, why do you need to convert?
Then how we will check the variance of this?
I will manually check.
Frequency problem. I just did like car underscore def not really. So it showed some of the values which have the integers, which are only integer or float.
Yeah.
I didn't check the character. So that we have to convert to.
That, if you want to do it here, then
So basically you did the background job and then fine.
Shall we move on? Okay. So be careful when you're converting your object data type into numbers. Don't end up introducing any order which doesn't exist. So when you use one-hot coding, have you all seen one-hot coding anytime? You're not seen one-hot coding? Okay, I'll tell you what one-hot coding is, then we'll move on. Sorry, you have a column gender, and the gender column has male and female, okay? This I cannot use as it is in my modeling. So what I do is I convert this into numerical data types. All data types should be numerical. So when I convert into numerical, I use one-hot coding. What will happen is, it will replace this gender column with two columns, gender underscore M, gender underscore F. Okay. Wherever the record is M, you will have 1 here, 0 here. Wherever the record is female, you will have 1 here, 0 here. So this column will be dropped. In your data set, you will be left with this column. 1 and 0 will be stored on the hard disk or in wherever you're storing it as numbers. Numerical values. Okay.
In last class we had used this category.
Any other neighbors?
Yeah.
We used what?
Category or something.
Level encoder we used. We just manually converted. We didn't use that scale or category. Last time we just converted to category and then we changed it to 0 and 1.
0.
But we didn't use level encoder and 1 or encoder.
Be careful when you're doing this. Okay?
the same problem.
You see, level encoder is something like it will do a sequencing 1, 2, 3, 4, 1, 2, 3 as per the number. But what happens, if you see like cities, let's say, we count 2, 3 cities, it doesn't have 1, 2, 3. If you have like random cells,
Bore and Stokes is right now object. So I'm dropping these data types. Okay. And here car data types, let's say again, Bore and Stokes is still object data types. Okay. Here I'm converting my cylinders into numerical data types. And here I'm converting my data types into this thing, float. Okay. Guys, all of you with me on the cylinders till cylinder point. Okay. After cylinder point, what I've done here is based on the experience I had in the other data set where there were missing values. In AutoMPG dataset, you'll see missing values. Okay, so what we do is, if we come across any missing values, replace it with NaN. NaN means not a number, null values. Okay, so what I'm doing here is car_df dot replace wherever you come across with some question mark, replace with NaN. But I didn't find any question marks in this dataset. The question marks were there in AutoMPG dataset. Okay, so we can actually delete this line. We don't need it. Then at this point, what I'm doing is, there are question marks there. Oh yeah, sorry, there are question marks there. Correct. We saw it here, right? We saw it here. Question marks here. Sorry, mistake. There are question marks here. These question marks now would be replaced with not a number, null values. Okay. When you replace question marks with null values, you can do numerical Python operations on it and convert into appropriate values. Okay, that's why we did this. Move on. My data types right now are, after changing the data types here, after dropping the columns here, some of the data types are still object. Object means string data types. So what I do here is, I first convert my cylinder into numericals. Then I change my data types here. Look at this. car_df bore, I replace that with as type float. I replace stroke column as type float. So I'm changing all the data types to float. Because many of these columns, let's say which column had that question mark, normalized losses. Normalized losses. It's already a numerical column, I think. Yes, it is already a numerical column. So I don't need to change it. There you go. It's already a numerical column, so I don't need to change it. Rest of the columns which are object data types, I'm changing into float types. Till this point, is it okay? Once I've changed the data types to numbers, numerical, I know there are many missing values. So the strategy I'm using here for missing values is replace the missing values of price column with the median of the price column. I want to explain this step to you. So I have a data frame, and in this data frame I have one column. This column is called price. In this column there are many NAs. NA. Wherever there are question marks, we replaced all of them with NAs. The question mark has been left behind by the data entry operator because when he was entering the data, he did not have values for those columns, those records. Okay. So we replaced question marks with NAs, all this became NA. Because now these have become NA, I can use the function fill_NA. What this function does is, if you see that syntax, what I've done is find out the median of this column. Whatever values are available, using those values, find out the median. Replace the NAs with the median of this column. It is always safer to replace missing values with median, because means they are easily impacted by outliers. Mode is used in categorical variables. We are running with float variables. So we always replace mean or median, but we are not yet checked the outliers. All columns will have outliers. Mean get easily impacted by outliers. So if you replace these values with mean and go and remove the outliers, then these values will be completely incorrect. So replace with median. Median is not impacted by outliers, right? And the beauty of this is, in scikit-learn, I can find median of even an object column. The column is supposed to be numeric, but because it has question marks, the data frame is converted into an object data type. But you can still go ahead and find the median of that column. Why? Because median is physical central value. Mean is mathematical average. It's a calculated central value. You cannot find mean of an object data type. You can find median of an object data type. Right? All of you getting the difference? That is where the difference between Python and R comes. In R, I will have to first convert into numerical value even to find median. Sorry, what was I?
So as a thumb rule, can we say that always there is median?
Now, how do you address missing values? Okay, how do you address missing values depends on your analysis of the data and why the values are missing. The values can be missing because of some random reasons. We call it randomly missing values. Values which are randomly, you don't see any patterns in them. They're missing values in all records, in all columns, randomly distributed. Then we say that data is missing at random. There's no particular reason for it. Okay. Whereas there can be situations where the values are missing because of some reason. They're not because of randomness. For example, if you take income, usually you'll find nobody wants to disclose their income. So you'll find missing values in that income column, many of them. So depending on what is the reason for that missingness, you'll apply different strategies. If it is income column where the values are missing because of the nature of the column, then I might have to build a submodel, a model inside a model, where I predict the values of the income based on the other attributes available. So my domain knowledge will come into play, which will help me understand what are the other attributes that this income column is going to rely on, depend on. How can I guess it? So whenever I create such imputed values, as we call them, I'll create a new column, income imputed. So I will not touch the original column. I'll create a new column called income imputed, where all the data available is copied as it is, including the missing values, and the missing values are imputed from the other columns. That is one strategy. If your data is missing at random, then replacing the column with a median is the default strategy we use. Look at the spread of the data on that column. If you see long, thin tails, mean is not reliable. So we replace with median. Right? There is a package available called mice. It's available both in R and Python. In Python, it is available in another package called stats model. Stats model. Mice stands for multiple imputations through chained equations. Multiple imputations through chained equations. Yes. When you run this package on your data set, it will automatically try to replace the missing values in all the columns with predicted values where predictions will be based on the other columns. It will establish the relationship, it will see which one is strong relationship, it will go and impute. So one column's missing value might be imputed multiple times from multiple columns. Please go and read about this. It's a very powerful package. When something comes with power, you have to be very careful in using it. So read about this mice. I'm not going to cover it here, but it's a very beautiful package. You should read about this. And just to add to the confusion, apparently the mice implementation in Python is slightly different from mice implementation in R. Though they both call it mice.
Suggest a lot of things also. Low variance in automatic drop. Nice.
So these are the tools that you should be aware of, you should have in your portfolio when you start doing data science projects. All right, all of you on this, shall we move on? Once I've done this, then I go and do my basic statistics, def describe. Describe with descriptive statistics, and you know how to interpret this? All of you are aware of this? Take any column, say height of the car. First thing you should look at is difference between mean and median. The mean is 53.72, median is 54, not a very big difference. 53.72 and 54.10, not a very huge difference to worry about. Look at the distance between the length of the left-hand tail and the right-hand tail. Left-hand tail is minimum minus first quartile. 47.8, let's take it as 48. 48 and 52, that's around 4 units. 4 units. Difference between this and this is again 4 units. So it's going to be a very symmetrical bell curve. The distribution is likely to be a symmetric bell curve for height. All right, I don't see any skew to worry about. Look at the car weight. Same story repeats here. 2555, 2014. If there is any column where the mean and median are very different, then you might be having a skewed data set. Look at this one, price. Now price is the target, forget the price. Let's see if our analysis stands. Let's see whether it stands. Okay, so this is a numerical way, a statistical way of analyzing your data, but instead you can do a pair plot. In pair plot, I always prefer to have the diagonals in form of density graphs. How do you get that? When you call the pair panel, you give diagonal kind is KDE, kernel density estimates. When you do this, you get the plot like this. Now let us spend some time on this. Always keep in mind, the output of the pair plot is a square matrix. It has as many rows, as many columns it has. Okay. So this is rows versus rows comparison. So we have normalized losses, then we have wheelbase, we have length, so on and so forth. What I've done is from car DF, I have taken using index locator all rows column 1 to 16. Yeah, column 0 is my column 1 to 16. How many are there here? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I have not taken the price column here. So what we do here is, instead of doing this, you do this. You do this. Just comment this out. Okay. SNS.pairplot car underscore DF KDE. You do this. We'll do this pair plot. Now we run this. So let's let it plot. Fortunately, it's coming out fast. Yes, sir. Got it. Now I want to make sure my price column is reflected here. We're going to predict the price, right? So price column is, I think, second last or something. Cylinder MPG it's last but one. Why is it not showing to me? I'm not getting it. One second, I probably didn't. Car underscore DF diagonal. Are you able to get the price column? No, it's there in the data set. It's there in this price. There you go. Car underscore DF describe, it's there in this data set. But you guys are getting it? All right, okay. Let's look at that. Okay. the first thing that you need to do is, when you do pair plot, is first thing that you need to understand is first row and first column is same, second row and second column is same, third row and third column is same, so on and so forth. Okay, and when I do a comparison of a column with itself, if I do a comparison of, say, MPG versus MPG versus MPG, what kind of a plot will I get? Scatter plot? It will be a straight line. There will be no information here. There's no spread, nothing. So trying to do a scatter plot for a column with itself is useless. It's not going to give you any information. So whenever it comes to that point where you are going to look at a column versus itself, what they have done is, instead of giving you a scatter plot, they have given you a density curve. By default, they give you histograms. We have changed it to density curve. The advantage of doing that is, in R, if you do this pair plot, it will leave out the diagonals as blank. It will leave out the diagonals as blank. It will not show you anything there. Whereas what happens in scikit-learn is, they give you a distribution. Why leave it blank? Use it to show the distribution on that particular column. Okay, so that is why diagonals, you will see the distributions, how data is distributed on that particular column. Okay, so let's look at the diagonals. In the diagonals, in my case, first column is symboling. Honestly, I don't know what symboling is. Maybe I should have done that homework. Next column is wheelbase. Wheelbase is basically how spread the front wheel and the back wheel, the distance between them. Okay, we see a normal distribution, except for higher values. Higher values, there seems to be some kind of a tail. Doesn't look worrisome. Look at the length of the car, again almost a normal distribution, but we see some kind of overlap here between you see multiple Gaussians here, one behind the other. May not be of a concern right now because they're all kind of overlapping. Remember, which was the column where we saw a perfect match? The central values, what is the column? Bore. Height. Height was the column. This is the distribution of height. So in distribution of height, now look at this, the distance between mean and median was almost very nil. And the tails were also equally spread. We were expecting a normal distribution, but unfortunately it's not normal. What it is showing here is two Gaussians, two normal curves are overlapping each other. Okay? This is what we call the mix of Gaussians. Go to the other columns. Look at this one. This one has a long tail on the right side. A long tail. It also seems to have, but these Gaussians are ignorable. They're very small compared to the other one. Okay. So look at the distributions, and on the distribution part, on each one of the columns, some concern, but not too much to worry about. You should never expect a theoretical symmetrical normal curve in the distributions. All algorithms assume that the data on the independent dimensions are distributed normally. Okay, that's all they assume. Apparently not so, but still it's close to normal, so I'm happy with it.
Can you explain the compression ratio, that one?
This one?
Yes.
This one? Okay. Compression ratio you see here, this is compression ratio. And compression ratio, what I'm seeing here is, there are two different clusters in it. Two buckets in the data on that particular dimension. Okay. This is a clear indication of mix-up of Gaussians. When you build models, especially linear models, you should not mix Gaussians. Every Gaussian has a particular characteristic. What do you mean by Gaussians? Gaussians means distributions. Okay. So if on a particular dimension, you have two different distributions, you are talking about two different processes which have generated this data. Remember, in statistics, you would have done a t-test or a z-normal test. When do we say that two data sets belong to the same process? When they're significantly overlapping each other, the central values are not very far away from each other. If the central values are very far away from each other, likely that the two data sets have not come from the same source. If the two data sets have not come from the same source, how can we include them in one single model? What is a model? Model is predicting the behavior of the source, the process which generated the data. Right? What happens when you use mix-up of Gaussians like this is, you're going to find x bar. X bar is going to lie somewhere in between these two, which neither represents this nor represents this. But your linear model is going to go through the S bar, X bar. So your linear model will neither be good for this prediction nor will be good for this prediction. He has done some typo. Hence, a lot of typos sitting on the extreme end. This happens when you measure these terms in some fractions and he's either added one extra zero or something of that sort he's done, because of which you're seeing outliers cluttered together in one group. So I have to go and find out what are these records which is causing this long tail in this cluster. My hunch and experience tells me this is most likely a typo rather than data coming from two different sources.
Or is the graph will be good?
Yeah, yes. This will be significantly good.
How do you identify the portion?
Go and put 1.96 standard deviation limit. Yeah, this is outliers. Outliers. So I can detect anything which is lying beyond 1.96 standard deviation on this dimension. So I can identify this.
But standard deviation will be given for the complete observation, right? But that includes data of the this
Doesn't matter. As long as they are beyond 1.96, they are suspect. So when you replace those outliers with values, proper values, then your standard deviation will collapse.
I think cylinder is the best example for what you are explaining.
I'll look at this. Guys, since this point has come up, I'll discuss this. In your original raw data set, suppose it's distributed beautifully, you have outliers here. You do something about the outliers. You identify the records and replace all these values with the median. Suppose you do that. Okay. When you do that, you remove the outliers, replace all the values with median. Your curve will become sharper. When the curve becomes sharper, standard deviation decreases. When standard deviation decreases, the data points which are earlier not outliers, now they become outliers because your standard deviation is decreased. So 1.96 standard deviation for both sides has decreased. So new data points will come out as outliers which earlier were not identified as outliers. And this will continue to go on infinitely. So just handle the first level of outliers. Forget the second level of outliers. They're not really outliers. Alright? Yes.
So generally at -2 standard deviation plus 2, right? You mentioned 1.9.
1.96 because 1.96 covers 95% of the confidence level. Some people use 2 standard deviation. Some people even use 3 standard deviation. That depends on your, where it's a matter of life and death and I want my model to be perfect as close as possible. That means I want my deviations to be very tight. Where I can tolerate some errors, my deviations can be low. Okay? So it depends on your requirement. Yeah, correct. Because I have 2 different clusters which I'm seeing here. But since the size is very small, my hunch is it's outliers. And the outliers have been introduced through some manual problems. Alright.
So in this case, it is good to retrieve the outlier, or we can just remove we can remove the record. That's also one strategy.
Removing record is always the last option because you're going to lose so many other column informations when you remove those records. Row only, he's talking row. He's dropping the rows. So if you start dropping the rows for all columns where you have outliers, your data set might shrink.
Exactly. We have one in the last exercise. So what happened here, they were having a 30 attributes, breast cancer one, right? So now every column except one, every column has an outlier. So when we are removing the outlier for every column, 569 records coming down to 237.
So that's not good.
That's not good.
So dropping records is always the last option when you have plenty of data. When data size itself is restricted, dropping records is not a good option. Shall we move on? All of you? Okay, let's move. So now always start by analyzing the diagonals first, how the data is distributed on each column. This is my univariate analysis. This is what the output of DF describe is. How your data is distributed on that particular column. It's a basic statistic, it's a descriptive statistics. Next we do is bivariate analysis. In bivariate analysis, how these columns interact with each other. For example, if you look at this one, this is telling you interaction between the symboling and this one, wheelbase. By the way, in this square matrix, above the diagonal and below the diagonal, it's mirror image. Either you focus below the diagonal or above the diagonal. Okay, so let's take below the diagonal. So I know this first column is symboling versus wheelbase. What it means is, as the value for symboling increases, you see that the wheelbase trend is going down. Wheelbase is shrinking as symboling increases. Okay, but I'm also seeing a lot of noise. For a given value of symboling, there are multiple values of wheelbase. So between symboling and wheelbase, there is a negative relationship. There is a negative relationship. Okay. Look at this. This is between symboling and length of the car. Since length of the car and wheelbase are almost kind of related, you'll see a negative relationship here also, but not as well as in this case. Look at the relationship between symboling and width is almost circular distribution. No significant correlation between the two. Right? We can continue to do this analysis. Let me just look at this one. This is compression ratio, yeah, and symboling. For increasing value of symboling, compression ratio that you find is, in this range for one group of cars, whereas for other group of cars, the symboling range of symboling is very small. For this cluster, if the cluster is a real cluster, the range of possible symboling values is much less than this cluster. That's what is coming out of this analysis. Okay. Now let us look at the other columns. Let's look at this one. Look at this. This is relationship between wheelbase and length. Obviously, as your wheelbase, this is wheelbase, as the wheelbase increases, the length of the car increases. And you're seeing a positive relationship here. The R value will be very close to 7 or 8. So this is the case where you have two dimensions and both the dimensions are interacting with each other. They are not linearly independent. But the algorithm assumes that all dimensions are linearly independent of one another. Okay. So we have ways of handling this. One way of handling this is find out using your domain expertise whether calculating the length of the car is more prone to errors or whether calculating the wheelbase is more prone to errors, measurement errors. If calculating the length of the car is more prone to measurement errors, drop the length of the car. Keep the other one. However, if you're not able to take that call, you might want to run a principal component analysis, a mathematical technique, or singular value decomposition, another technique. Okay, using those techniques, we can create synthetic dimension out of this. That synthetic dimension will be a composite of these two, so I'll drop both of them and keep the synthetic dimension. I'll talk about this when we come to PCA, principal component. Right now, I'll ignore this. Okay. So in the data set, what I'm saying is there are distributions amongst columns which have linear relationship. There are distributions amongst columns which are indicating no relationship. This one, these are all no relationship. but this is negative relationship, so on and so forth. It's a mix. Some columns are related, some columns are not related.
Can you just tell us the linear one?
Cylinder one. Where is cylinder?
Last.
Oh, sorry. Where is the last? Yes. Which one do you want in cylinder?
Just
Cylinder versus cylinder.
Cylinder versus cylinder?
Yeah.
Right.
This one?
Yeah.
Okay. What is the problem here?
If you look at the cars with number of cylinders, okay, in your data set, most of the cars have 4 cylinders, 5 cylinders, 6 cylinder and 8 cylinder. Okay, most of the cars, look at this, have 4 cylinders. By the way, these data points might be sitting on top of one another. So that doesn't mean your data set has only 1, 2, 3, 4, 5, 6 records for 4 cylinders. Don't do that mistake. Your data set might have hundreds of records for 4 cylinders, but they're all sitting on top of each other. So that's why you're seeing only 6 dots. Most of the data have 4 cylinders. Some of them have 5 cylinders, some of them are 6, some of them have 8. Only few records have 12 cylinders, very few records have 2 cylinders. Now when you go to the extreme end, where cylinder versus cylinder, that's why you see a peak in 4, some peak in 5, then you'll 6 and the small peak here. None of the other have any peaks. Now cylinder is a numerical column, integer column. You can have 1 cylinder, 2 cylinder. Then what do you mean by the spread? What is a spread? How can you have a spread on integer columns? This diagram which I plotted here is called KDE, kernel density estimates. So there are 3 words in this. First word is, it's an estimate. It's an estimation of the possible distribution, density distribution, density estimate in the population. In the population, how the cars are distributed around this value in cylinder. It is a density estimate based on a mathematical function. That mathematical function is called kernel. So using a mathematical function on the available data, I'm estimating how the density distribution of this column is likely to be in population. That is why you're getting the spread. The spread is not in your data. The spread is the estimate of the distribution density in the population based on the observations in your data set. So for integral columns also, you can have spread like this. Because what the kernel is telling you is, in the population, it's likely to be like this.
If you're building the model on this data set, it's like involving is something that as to not understood what does it mean.
I actually went and studied what symboling is, but unfortunately I forgot. I should have known.
I mean, if I come to know that this is not of a very significant use, shall I not drop this?
You can drop it. Data. See, you can't do model building without domain knowledge. You have to have domain knowledge. We have to go and find out what the symboling stands for.
But in your drop statement, like we are not dropping symboling, so we should, I think.
Why do you think we should?
Because, I mean, it's also categorical value.
So what? Doesn't matter.
If a car coming from Japan versus car coming from US, the miles per gallon is going to be different. So it's a categorical variable. Origin of the car is categorical variable. It has an impact on mileage.
If you see the domain point of view, so symbolism
Drop the root on road variance with the what you gave is a limit for that. There are columns with values. So there are columns which have a couple of values and there are some with 3 values. And you decide to drop all of those. So how will you determine which one is picking?
Look at the ratio of the distribution. In a column, there are 8 values, but majority of the records is with value 1, very few percentage of value 2, then that becomes a low variance filter. That's a candidate for low variance filter. But the skewness in the distribution, suppose I have gender column, male, female. 95% or 90% of the data is males, 5% is females. So I might take a call that this column is going to be useless for my analysis and drop it. So it's a call that you have to take. It may not be 100-0, it might be some distribution, but is that distribution good enough for you to use it? You have to take a call. And that call you will be able to take both based on domain knowledge. If I know the drivers in the people who use the car is 50-50 amongst these gender in the market. I know that, but for some reason the data which I have does not reflect that. So I might drop the call.
So should we be doing this scatter plot matrix analysis before we drop that? Doing it first that way, then do that first and then.
This analysis is done on the original data set. It's not on the dropped data set. You should always, this analysis on car DF, you should always do this pair plot analysis on the original data set, always, okay? Once, because this analysis is what is going to tell you which dimensions are likely to be important, which are not likely to be important. You should always do this on the original data set. Hey, you got your coffee?
Yes.
But I think here we've already dropped it and we're doing this analysis. This is not on the original.
Hey, no, I changed it here, no? I changed it here. I asked you to.
We've removed fuel type, engine indication, all of that we've already removed and then we're doing this analysis.
No, I commented out this line. I just now did that.
But you've already dropped the columns, that's my point. You drop first and then you're doing this analysis.
Car underscore D?
Yeah.
Oh, you don't have this one.
No, about this. If you go further up, yeah. So
Oh, you're talking about these? Yeah. Okay. Yeah. You should be doing this before you do this. Before you do this. Always do your analysis on the raw data set. Okay. All right. Shall we move on?
Just one question.
Yes, please.
We did analysis on compression ratio and the second one is cylinder.
Yeah.
What we found is compression ratio have two Gaussians, so we need to treat the outliers. That's
Yes.
what is the thing.
Yes.
But in this case, we know as per the domain knowledge, we cannot treat the cylinder thing. Right?
Yeah.
Like we cannot change the cylinder 12 to cylinder 4. Just because it's kind of an outlier or something like that.
No. What you can do is go back to your data, find out what is a car model, go and refer to the manufacturing, because you have all this information, whether this car model can have 12 cylinders. That analysis will do. That is what you have to do. See, missing value replacement, outlier replacement, all these things you cannot do without your any domain knowledge. You have to have domain knowledge. When I went and studied this data set, I found out that for a given car, say Toyota, some particular, within Toyota, one particular subvariant, the data given for mileage was unreliable because the factory manufacturing label itself says the miles per gallon is going to be in this range, whereas this guy is claiming to be so high. So the data itself became a question mark. So you have to do that analysis. Okay. So when you do a real life project, when you get into capstone project, you have to reflect all these things. How did you analyze your columns? How did you handle your outliers? How did you handle your missing values? And you have to justify your strategy, why you did that. You can't blindly replace something with a median. That may not be the optimal strategy.
Right? Shall we move on? Okay.
For symbolic analysis, symbolic means cars are initially assigned the risk factors in the
Risk, yeah, correct. They are assigned a risk factor. Yeah, that risk factor is what they connect with symbolic. Can you just read out more louder?
The cars are initially assigned a risk factor symbol associated with this price. Then if it is more risky, the symbol is adjusted by moving it up the scale.
Okay, all right. So this is a risk factor associated with the car. And this reminds me, the risk factor associated with the car depends on the color of the car. I don't think we have color here. It depends on how the car has been driven, how the car is driven. These days, a lot of people, they take pride in telling that my car has so many chips. If you buy this high-end foreign brands, they all come with embedded chips. Those embedded chips, in real time, they capture the data about your driving style and pass it on to a central server, where they sit down and analyze. And the risk factor is adjusted, recalculated, recalibrated, based on how the car is being driven. The symboling reflects that. Right? Okay, let's move. Now, are you able to understand how to interpret this pair plot? It'll come through experience, but this is where you have to do it. Okay? Move on. So what I'm doing here is, from the car underscore DF, I am dropping the price because that's my target. And whatever columns I am left with, I'm capturing that into X. So I'm creating a new data frame called X, which will now have only those columns which are independent variables. The target column price will not be part of X. Then once again, I'm dropping number of cylinders here because this is the same problem. It's a low variance filter again. But if you wish, you can keep it. Then what I'm doing here is from car underscore df, I'm dropping the price. And sorry, I'm not dropping the price. I'm selecting the price column and storing it in y variable. So X variable is all columns except price. Y variable is only the price column. So if you have 1000 record 10 columns, this will become 1000 record 9 columns. This will become 1000 records 1 column. Are you all okay with this? So I have segregated the independent and the dependent variable. If this was R, I don't need to do this because R takes in as input only one single data frame and along with that a formula. Whereas in scikit-learn, I have to separate this data into independent and dependent variables. Then I'm making use of the random function which generates the training set and test set. We call it train test split. When I make use of this train test split on X and Y, I'm asking it to split the data in a ratio of 75-25, 25 for test, 75 for training. The output of this will be four data sets. So let me explain this to you because some people get confused here. So if this was my data frame df, this was my target variable iv, independent variables, target. First thing which I did is I captured the independent variables and stored them in X. I took the target variable and stored it in Y. Then on this X and Y, I did a train test split. When I do this, what happens is it breaks this X and Y both into X underscore train, X underscore test, Y underscore train, Y underscore test. This training label Y underscore train is for this X underscore train. This is my test data, X underscore test corresponding Y underscore test. Now when I build the model, what I will do is I'll call the fit function, fit, and with the fit function I'll supply these two. This one, X underscore train and Y underscore train. I'll supply these two. This is at this point, the gradient descent will come into play. It'll identify for you the best fit model. The best fit model will reflect the relationship between Y, this one, and X. This X comes from this training set. So it will be of the form Y is equal to M1 X1 plus M2 X2, so on and so forth. How many columns are there? 16. So M16 X16 plus C. This will be the model. Once the model is built, we want to evaluate it. We want to see how it performs. To this model, I'll supply the X underscore test values, which means these values. And it will give me the predicted values, Y pred. Are you getting it? So I supply the test data, the X underscore test, only the test data to this model. The respective columns get multiplied by their coefficients for every record. For every record, I get Y underscore pred. What is the predicted price for this car? In the data set, I know my actual Y underscore test is this. predicted y is this. What is the difference between these two? That will be my accuracy. Accuracy will be the difference between the y underscore test, which is actual test labels, versus y underscore pred, which is your predicted test labels. Right? So let's see this, but before we go there, yeah, I think we can do it comfortably. So let's look at this. Train test plate. I'm calling the linear regression here. This is where I'm instantiating the linear regression model. This is where this class becomes an object. And in that object, there is a function called fit. I'm calling that fit function and supplying the training set. When you run this, this is the point where the best fit line using gradient descent is found for you. Now look at this. I'm printing out the coefficients of all those, the best fit line, the best fit plane, hyperplane rather. So when I print the coefficients, these are the coefficients. Now we need to understand what this is. You said there are 16 columns. So the 16 columns have 16 different coefficients, M1, M2, M16. This is that M1, M2, M16. M1 is 88.57. M2 is 71.82, M3 is minus 93.38. All these are those M1s. So let's understand what it means. What it means is, for every one increase in symboling, 1 unit increase in symboling, the price of the car goes up by 88.57 units. dy by dx. For every 1 unit increase in the wheelbase, the price of the car goes up by 71.82 units. Whatever the units may be, dollars, yen, rupees, whatever it might be. For every 1 unit increase in the length of the car, the price drops by minus 93.3 units. Now look at this. This is where you need to be careful. We know that wheelbase and length are positively related. We saw that. Then how come one has a positive relation, other has a negative relation? But both of them should be positive, no? Wheelbase and length are positively related. But one of them is having a positive impact on the target, the other one is having a negative impact on the target. How can that be? Such things indicate to you something is not right in your data set. And one thing which is not right in your data set here, we all know that, is multicollinearity. Engine size, when engine size increases by 1 unit, the miles per gallon, price goes up by 251.74 units. Okay, that is the way you have to interpret this. But what is happening is, some of these ratios are kind of not gelling in, they're not fitting in properly. For example, we already found the length and the wheelbase, they are going in opposite directions. Okay, that is one problem. Then we have horsepower. When horsepower increases by 1 unit, your car price goes down, whereas actually when horsepower increases by units, car's price should go up. Horsepower increase means large cars. Large cars, you pay more price. Bit more considered, but this is not only negligible, it's also the wrong direction. Right? Good point. Right? So there are problems in these coefficients which are not falling in line with our domain knowledge.
So this coefficient is what we are talking about, right? So is it saying about the weightage kind of thing? Yeah. One thing I'm not able to understand is when you say 88, okay, it increased by 88 when unit change, keeping other constant. But some values is talking about 6,000 line, 6,000 scale, one is talking about 88. Yeah. If we compare among each other, it's a huge difference. Yeah. So how we are going to interpret this in after?
The reason why the 6,000 is happening is probably you have an outlier on that dimension which is pulling it, right? So we have not addressed the outliers here. One reason could be that. The other reason is if you're not able to, I mean, if these numbers are not falling in place, then we can convert them into z-scores. The entire data set can be converted into z-scores, and then we can look at this. But the magnitude of the difference, you will still see that the magnitude is still there. Okay, the difference is still huge. And the root cause of this problem that we are seeing, the root cause for this is, one, we have not handled outliers. Two, we have some kind of a, correlation between the independent variables, which you noticed. We have not done anything about that. Multicollinearity, right? So those are the core reasons which you will come across in all data set, which lead to overall model level problems. Okay. Now I'm going to take you through further down into slightly more deeper stuff. Let me see if I can cover it today. If not, we'll start with fresh minds tomorrow, because I need, that particular thing needs a lot of brain energy. Brain power.
So right now, all columns have specific units. They are not normalized. So this coefficient is on the not normalized data.
Correct.
So it's always better to normalize the things and then calculate the coefficient. Is it like that? Because otherwise you are not able to relate the coefficient.
The coefficients will not change when you normalize. It doesn't matter. By normalizing, you're just centering the data to 0. The relationship between y and x will remain same, whether it's a normalized data or a non-normalized data. Coefficients will not change. Linear regressions are not impacted by normalizations. The accuracy score, the coefficient, everything remains same. Okay, shall we move on? Yes.
So linear regression only gives the coefficient, but not the power of the x square and those things. We cannot.
No, this is simple linear model. If you build quadratic model, then it will. Right? So let's move on and let's see the intercept. This is the intercept. I'm printing the intercept. What you need to do is model.intercept. This is the model name. Model name.intercept. This function will give you the intercept. Whereas if you want the coefficients, you have to use model.coefficients. Look at this. For coefficients, it is model.coef underscore. Coef underscore will print the coefficients. Model.intercept will print the intercept. Now the intercept that we are getting is minus 1, 2, 3, 2, 3. There's an array. In that array, we are passing the index. So the first one is intercept. In the other array, we have the coefficients.
I just tried
For coefficient also you are passing 0.
Yeah, that is a different array. So I'm saying starting from 0 and all the coefficients.
Yeah, in my code, I just tried regression model dot coefficient. Just that much. Yeah. Regression, I mean the dataset dot coefficient.
Dataset.
This regression. I just typed that code. It was showing some other results. It's not showing the whole set.
No, are you sure you're getting 0 in IDX? No, you have to do this. See, this is a different array. In that array, I'm accessing all the elements of the array using this, which is why it's printing out all these things.
You have already fit the regression model with that experiment.
You have already done that. After fitting it, the output of this is best fit line. The best fit line has coefficients. All the coefficients are internally stored in an array which is accessible through this function. This function is accessing that array and printing out the results. Similarly, there's another array for your intercept. It's accessing that array using intercept. We don't know what that name of the array is. We can only access that array through this function. This point in the graph, all these coefficients in the graph are the lowest point in your error. This is error. There are multiple 16 dimensions over here. This is the lowest point. This combination of coefficients gives the lowest point in the error graph, the best fit. Right? So let us look at the performance of the model on test data. And as you can see, performance on the model on test data is 83.6%. Not bad, not good either.
So what does it mean to 83.68?
The comparison between this and this. Okay, so the 83.6%, what do you think it is? No. This is your coefficient of determination. 83.6% of the total variance in your data, test data, has been captured by your model. R square. This is not adjusted R square, this is R square.
That means 80% we still don't know why.
Yes. Sum of square errors.
X minus mean.
X minus x bar is for 2 by n. That residual error is 17%. 17% of the variance in your test data has not been explained. Alright?
So where does that intercept lie on that graph?
Intercept is one of these dimensions. Error is a function of slopes and c. Error is a function of m and c, right? So c is one of the dimensions. What I showed you earlier was only one m and c. Here you have 16 m's and 1 c. We can't visualize it, so I'm not able to show it.
That's the problem.
This 83.6% prediction is accurate.
It's the coefficient of determinant. How much of the variance in test data has been captured by your model, explained by your model. Shall we move on? Okay. Now we need to improve the performance of the model. Your first cut model will never give you the results that you're expecting, very rare. So you'll always end up in another cycle where your objective will be how do you improve the performance of this model? How do you notch it up? So there are various things you can do, but before you do that, I would like to introduce you to a library called Stats Model. Stats Model, the formula API, SMF. Stats Model Functions. Okay. What happens is, when you build these linear models in R gives you a lot of statistical information about your attributes and your models. Scikit-learn linear regression does not give you those information. But there was a lot of demand for that kind of R kind of analysis in Python. So those people who support Python, Scikit-learn, they came out with this library called Stats Model. Stats Model tries to replicate the behavior of R. Okay, and gives you similar kind of statistical analysis as you would have received or obtained in R. So let's see what it does and why is it required. So I'm importing statsmodel.formula.api, I'm importing something called SMF. SMF is a bunch of statistical model functions. And this, I'm going to build a linear model using this. But before I build a linear model using this, I have to combine my X train, Y trains into one data frame because R takes as input one single data frame. It does not take independent variables, dependent variables separately. So I'm recombining the two into one using concat function. I'm creating a new data frame called cars, which now has both the Y and the independent variables put together for training. Okay. Now look at this. When you do cars head, you get the price column on the first column and the rest of the columns. Now I make use of the smf.ols. OLS stands for ordinary least squares. Linear regression, ordinary least square. And as input to this function, I give price a formula where I say price is a function of the various columns. The plus which you see here, this plus is a field separator. It's not a mathematical plus. And at the end of it, you will see the data file name. Sorry, the data file name is cars. There you go, data is cars. So the output of this is once again the same model. But this model has been built in R, R-based, R similar to R libraries. So the model is price is equal to, I'll take the intercept later, symboling is 88.57, 88.57 symboling plus 71.82 wheelbase minus, I'll just take one more, 93.38 car length CL, and so on and so forth. The last thing being minus 123.06 or something intercept. This is your model. This is the representation of your best fit line. Now you can write a code in Java where you have a function where function takes as input 16 variables, multiply those variables with the respective coefficients, subtract this intercept from that, and give the output as your predicted price. Convert that Java code into a runnable jar file, productionize it, your model is in production. All right? So that is the model. Same model we got in scikit-learn, same model we're getting here, but here we're getting some extra results, which we did not get in scikit-learn. Do some of these things look familiar to you? R square, adjusted R square. Look at the difference between R square and adjusted R square. Adjusted R square will always go down when you add useless columns. R square will always go up. So adjusted R square will usually be less than R square. F statistics, analysis of variance. Remember these words, Fisher statistics, analysis of variance. Then you'll also have AIC, BIC. What is AIC? Hey Guru, we would have covered in stats. AIC is Akai information content, BIC is Bayesian information content. All right, forget it, no problem. Not required. Let's go straight down. Most important of these is your adjusted R square. Adjusted R square is lower than R square. 80%. Is it okay with you? You have to decide. But before I go there, I'll come down to this. Okay, I'm going to stop at this point. What is this table telling you? I'll just take one example and you have to use that example on others. Okay. Then I'll tell you why this is not there in Python. Now you take any one of these dimensions, say length. The coefficient for length is minus 93.3. We already seen that. And then it gives you standard error, t values, probability of t values. Remember your hypothesis testing? When do you reject null hypothesis? When do you accept null hypothesis? You remember those concepts? Remember we use a p-value there? Right? P-values, that is what is this, okay? Now the thing is, let's take one of these example, length. I told you to find the best fit line, the algorithm will try out various lines, okay? And it will find out the errors for each line for you using gradient descent. And I also told you that the best fit line that it finds out will always go through the X bar, Y bar. Agree? So it would have tried out various lines for you before finding the best fit line. For each line on this particular dimension length, you can take any dimension. Or for each line on this particular dimension called length, you would have had different slopes. Each line would have had a different slope, different coefficient. So those coefficients would have a distribution of their own. Those different coefficients which it tried out on the length dimension before it found the best fit line, those coefficients would have had different distributions. Of that distribution, the one given to you for best fit line, minus 93.38, maybe this one, minus 93.38, how far away it is from the central value is given by your t-score. This is minus 1.2, whatever it is, t-scores. What is t-score? T-score is a z-score. All of you remember z-scores? Xi minus x bar by standard deviation. How many standard deviations away a data point is from the central value? We use z-score for that. When you use student's t-distribution, we call it t-scores. Formula is same. Remember student's t-distribution? Okay, the formula is same. So the selected value for coefficient for length, how many standard deviations away it is from the central value for the distribution of coefficients on length, that is given by this. The standard deviation of this distribution, the standard deviation of this, which we call standard error in t-distribution, that is given by this. This is the standard deviation. This is how many z-scores away it is, your selected value is from the central value is this. You multiply these two. Multiply these two, please. Multiply these two. And tell me what is the value you get. Into minus 1.24. 73. You will get back the same value. You will get back this value. Okay? Look at this. If I am doing z-score, okay, z-score centralizes your data, converts the x bar and y bar into zeros. I take any value xi minus x bar by standard deviation is my z-score. Agreed? X bar is 0 because it centers the data. So that means z-score is nothing but xi by standard deviation. So xi is nothing but z-score into standard deviation. Here we call it t, and we call this standard error. So when I multiply t with standard error, it gives me back the value that you had over here, xi. It gives me back the xi. Okay, so that is the way to interpret this. Of all the various coefficients tried out on this length dimension, it select you this one, how far away it is from the central value. If it is too far, maybe it's not reliable. I'll do that analysis using this. The most important analysis which I want to take you to is the p-value. What does this p-value tell you? What the p-value is telling you is, I'm going to talk only for length, but the same thing applies for all. What this p-value is telling you is, probability is 0.2. What is the cutoff probability for your confidence level? 95%? 0.05, 5%. 0.2 is much higher than 0.05. What this is telling you is, even if in the population there is no relationship between the length and the price of the car, no relationship between length and price of the car, null hypothesis, and you're taking data from that population, you're likely to find this kind of a relationship between length and price in your data, which means this is a fluke relation. I repeat, what this p-value is telling me is, probability of finding this kind of a relationship between length and price in your data, even if there is no relationship in the population. In population, the slope is 0 between these two. And from there you have taken a sample, random sample. The probability of finding this kind of relationship is very high, which means this relationship is fluke. It's a statistical fluke, it's not reliable. Look at this one, p-value. Look at this one, stroke. P-value is almost 0. What it means is, if in the real world there is no relationship in Bohr and the price, and then from that population you have taken this sample, finding this kind of a relationship between Bohr and price, the probability is very low. Probability is very low. I'm talking stroke, sorry. Probability is very low, which means this relationship is not fluke. It is likely to be there in the real world. Okay, so let me put this pictorially and explain this to you. Then we'll wind up. Let's take one of these columns, stroke and price. Same thing applies to all. If suppose between stroke and price, if suppose there is no relationship between these two, then how will the scatter of the data points look? Agreed? All of you? R value will be very close to 0. The scatter of the data points will be circular. Okay. Now, what you will observe is most of the data points are near X bar, Y bar. As you move away, the density falls. That is why you get a plot like this on this and a plot like this on this. Are you all okay? When I convert this into 3 dimension, where in the 3rd dimension, this is my X bar, Y bar. If I plot the density on the y-axis, question to you is how will the distribution look? Parabola? Cylinder? Keep in mind, very close, it's very high. As you move away, the density falls. So this will be your normal curve, a 3-dimensional normal curve. A 3-dimensional normal curve is a shape of the density of distribution between 2 dimensions which don't correlate. This is the shape of null hypothesis. Null hypothesis says in your universe the data is distributed like this. Agreed? We don't know what the universe looks like, but null hypothesis says it looks like this. If so, and from there I have taken a sample, and in the sample I am finding the distribution between this core, whatever it is, say core, and price, I'm finding the distribution like this, where this is X bar, Y bar. I'm finding a squashed bell curve. I'm not finding a symmetric bell curve, I'm finding a squashed bell curve. This relationship is what is expressed as this coefficient. Now the question is, what is the probability of finding this kind of a distribution in your data if the real data is like this? That probability is expressed as p-value. If the p-value is very low, less than 0.05, that means your universe is not like this. We reject the null hypothesis. Whereas if p-value is greater than 0.5, we say that there is not sufficient evidence to reject the null hypothesis. So I'm unable to reject the null hypothesis. May not be, I don't know, but I don't have sufficient evidence to claim that there is a correlation.
Shouldn't the null hypothesis be, I mean, by default, I mean, we are trying to prove the other way, right? So
no, we are trying to establish whether null hypothesis is likely to be true or not. We can't do the other way. We can't prove alternate hypothesis is true or not. We can't do that.
So shouldn't the null hypothesis be, there's a relationship already and...
No, null hypothesis is no relationship. They're independent. It always negates your alternate. Alternate says there is a relationship. Null hypothesis, nothing doing, there's no relationship. No relationship means this is the way. Now the question is, from this you've drawn the sample, in the sample you're saying this, what is the probability of seeing this kind of a distribution if it's coming from this? If the p-value is less than 0.05, we reject the null hypothesis. If p-value is 0.05 or greater than or equal to, we say we don't have sufficient evidence to reject the null hypothesis. So we accept the null hypothesis likely to be true, we reject this. This analysis R provides, Python doesn't, and if you look at this, this is the p-values. So this tells you the importance of the attributes. Those attributes whose p-values is greater than 0.05, useless. Statistical fluke. Those attributes where p-values is less than 0.05, good attributes. Let me be a killjoy, okay? In the statistics community in the real world, there is a vertical split between the statisticians. One school of thought says p-values is not reliable. The other school of thought, which comes from the conventional statistics point of view, they say p-value is reliable. The reason why they say p-value is not reliable is, you can go and check it yourselves. Suppose I drop one of these dimensions with high p-value, symboling, and redo this analysis. all the other p-values will change. Now the question is, between your price and your length, if there is a relationship given by the coefficient, why should that coefficient change when I include another dimension, width? Why should it change? It should not change, right? The relationship should remain relationship. Why should the intensity of the relationship change when I add another dimension to it? But when you actually go and analyze this, drop the dimensions, you see that all coefficients change. Correspondingly, all the p-values will also change. The reason why they change is collinearity. They are not truly independent. Since there is collinearity and they impact each other, the coefficients are not reliable, hence the p-values are not reliable. It is because of this reason, this split between the statistics community on whether they should rely on this or not, scikit-learn guys said, forget it, we don't need this. We have other ways of establishing the reliability of the dimensions and the models. Let's use that. That is why scikit-learn does not give you this facility. But then subsequently under pressure, they came out with stats model libraries, which gives you this. Okay. Now, just to end up the show, what is telling you is p-value, and what it is telling you the 95% confidence within which these values lie. Okay. So if you guys remember 95% confidence level, area of rejection, area of, you'll see all, you'll be able to connect to those using this. I'm going to jump this, I'm going to move forward. Last one, overall probability value of the model itself. Can such a relationship between the price and the other good attributes, does such a relationship exist? P-value is very low, which means null hypothesis overall is rejected. Model level p-value is very low. So after removing all the unwanted dimensions, hopefully you will have a reliable model.
All right.
So do we need to reject or not based on p-value?
The p-value is very less here, so we should.
Lot of columns.
If you're working for people who believe in statistics and all, I mean, not that I don't believe in statistics, those people expect p-values from you, then you have to use stats model. If they don't care about p-values, don't come here. There are other ways of deciding whether a dimension is reliable or not. Ensemble techniques and all these techniques are available with us. So we use that technique.
Most influencing factor for the price. Then
Use decision tree regressor. That will list out for you the dimension, as you will see now after lunch. It will list out for you dimensions in terms of importance. Which dimensions are more important?
But don't we again use the p-values?
They use Bayesian statistics. They don't use p-values. You remember Naive? You won't have done Naive. You remember Bayesian this thing distributions? They use that for this. Some statisticians say that Bayesian distributions are more reliable than this. All right, sir. I'm going to call it an end of the day for today. For me, for you guys, it's going to continue. We'll meet tomorrow at 9 o'clock again. Yeah. So let's see what this logistic is. The name logistic regression is slightly a misnomer. It is used for classification. It cannot be used for regression. Okay, though the name says regression. But there's a reason why it's called regression, not logistic classifier. The reason is, under the hood, logistic regression uses linear models, linear regression. That's the reason. It's a classification method based on a linear regression. The response variable, that is the target variable, can be binary class, defaulter, non-defaulter, diabetic, non-diabetic, or it can be multi-class classification also. I can use logistic regression for optical character recognition. I can do that. And in my personal experience, I have seen and I have also read some papers about it. When we compare models, often logistic regression comes out on the top. If not exactly on the top, at least top few, top 2 or 3, okay, for classifications. So I'm going to start by showing you binary classification, but this can be used for multi-class classification also. Given your independent variables, what is the class likely to be? That is the objective of this model. I can also use a function available in scikit-learn where instead of defining which class an observation belongs to, a test record belongs to, I can print out what is the probability that this record belongs to this class versus this class. I can even print probabilities. Okay. This particular function is nothing unique to this. It's available in all probability-based models. Predict. You remember we use predict? We just add underscore proba. This function will print out probability values. If you go for just predict, this will print out the classes. Decision tree also has this, Naive algorithm also has this, logistic also has this. Predict underscore proba. Let's take a hypothetical situation. Don't worry about the PPT. Let's take a situation and discuss this concept. And for that, we are going to use 3 colors. You are a data scientist, you're working in a bank, and you have been tasked with, you have been given a responsibility to build a model where the model will take certain inputs and the output of the model will be, is this person likely to default? If I give him loan, is this person likely to be a defaulter or a non-defaulter? You have to build that model, okay? So what kind of data will you need to build such models?
His salary income, his student or his history of profession.
So past history in terms of
CIBIL score.
CIBIL score, okay, CIBIL score is an output of a model actually. So let's keep CIBIL score aside. You need his age, gender, income, any past loans he has taken, any property he has, so on and so forth, so many things. Now let's assume that one of the things given to you is his income. Forget it, this is a touchy subject, so let's call it age. Okay, one of the inputs given to you is the age of the people. So you have the past data with you. The bank has given you a past data set. In the data set, you have both defaulters, non-defaulters, and one of the columns in the data set is age. You notice a pattern here. The pattern is most of the defaulters, okay, most, not all, most of the defaulters are in the lower age bracket, okay? And you also notice most of the non-defaulters are concentrated in higher age bracket, but that doesn't mean there are no non-defaulters in lower age, okay? You observe this pattern. Now since there are 2 classes here, what we're going to do is, we are going to say, green class, we're going to assign a numerical value 1, red class, numerical value 0. Remember, we can't work on string data types. So the target columns will be assigned numerical types. Okay. Why 1 to this, why 0 to that? No reason, you can flip it also if you wish. But we assign a value 0 and 1. We don't assign any other value, we assign only 0 and 1. There is a reason for that. Okay. Now, your object, yeah. Now you find that the pattern over here, as income increases, you find more greens. As income decreases, you find more reds. You have done a linear model already. So what you do is, you try to build a linear model here. So you say, let the y-axis be probability of belonging to any one of the classes, let's call it 1. The y-axis is probability of belonging to class 1. You can actually take it as probability of belonging to class 0 also if you like. The 2 probabilities will be inverse of each other. So you can take any one you like. Alright? So when you build a linear model, the linear model, anybody has a black pen here? Black? No, this pen. Oh, okay. Now you'll notice that as the age increases, if this is a probability, the probability of somebody being belonging to green the probability increases linearly. Probability increases. I can represent it with linear models. If I had taken this as 0, if this was 0, then this line, how would it look? It will be reverse. That's the difference. So you can use any line. Okay. So I'm taking this as 1 for ease of explanation because you will be able to connect to what we did yesterday. So the line will look something like this. So this line, y equal to y is probability of belonging to blue class, is related to mx, x is this variable, plus c is the intercept over here. C may be 0, C may be negative. But the problem with the linear model is, linear models go to infinity, minus, plus. Probabilities have to be within 0 and 1. They can't be below 0 or above 1. So, we can't use a linear model. We use another technique where we transform this line into an S-curve. This S-curve is called a sigmoid. And it is very easy to achieve this. The sigmoid is nothing but 1 by 1 plus E. E is an Euler constant we use in mathematics, minus mx plus c. So this best fit line, the best fit line which is found for you, this best fit line is fed into this transformation, this mathematical formula. The result of this transformation is this curve. Yeah, sigmoid curve, the property is it will reach 0 at infinity, it will reach 1 at infinity. That's exactly the property of a probability distribution. Now let us interpret what this formula is saying. Keep in mind we are building the model, so which means we are in training set. So in training set we already know the labels of every record, right? The algorithm gets both the input variables and the output variable, x and y. So all the labels are already known. And the labels are shown in the color over here. Are you all okay? Shall we proceed? Now, what the models, now that I got sigmoid, I'll remove this line. I'll remove this line. Okay, this is going to infinity. We don't even need this. We don't even need this. Now what this model is telling you, let's look at that. If you take this red point, look at this, if you take this red point, what the model is saying is the probability of belonging to blue class. What is the probability of this guy? Suppose we don't know the color. What is the probability of this point belonging to blue class? It's very low, which means it belongs to the red class. So the model prediction and actuals are matching here. The model prediction and the actual label, both of them are matching. Take this green one. What the model is saying is, what is the probability that this green point belongs to blue class? This is probability of blue class, right? The probability is very high. And he is actually green. So both prediction and actuals match. Right? Hey, lady, are you with me? Sure, 100%. Okay, don't get left behind. Your expressions tell me a lot of stories. I have conducted I lost count, more than 250 sessions now in data science. So I built a model. You know what's coming, right? So looking at the place, the position people occupy in the class, I can guess a lot of things about the person. Believe me, we all follow patterns and you'll be surprised. I've noticed this pattern without fail. Based on the position people occupy in the class, okay, of course, latecomers, they don't have a choice, but people who come early, okay, based on the positions they occupy, I can draw a lot of conclusions from there, inferences from there, right? So people who are feeling doubtful but are able to ask, they're not asking. I know I can identify such people. Okay. So feel free to ask, okay? All of you, please feel free to ask. Don't get left behind. I was always a backbencher. I was always a member of the backbench society. I'm not saying anything to you. Don't look at me. If you sit in all places means? I was always a backbencher, so I know more over the backbench than the front bench. But other patterns which I observed was during the sessions, right? So a deviation from our main topic of discussion. Bottom line is, don't hesitate to ask. Okay, feel free to ask. Don't restrict. Coming back to this, are you all with me on these two discussions? Okay. Now look at this point. You see a red point here. This one. What the model is saying is, as per his income, he belongs to, probability of he belonging to blue class is very high. So the model will pass him as blue. Sorry, in this case green. Green, in this case green. So what the model surface is telling is predicting the probability of belonging to the green class. It's very high. So the model will classify him as green, but he is actually red. So model has done an error over here. Mistake. Similarly, if you look at this one, this side, the green point here, can you tell me what the model is telling you? The model is telling you the probability of him belonging to green class is very low, so he is likely to be red. But actually he is green. So the model has done an error here, a mistake. Okay? So whenever you have overlapping data sets, as in this case, in spite of the best fit line, the classification, you will find some errors. There will always be errors. These errors are called training errors. Errors in the training data. Okay? All right, no problem. Which one is minus 1? This is 0, this is 0, this is 1. And this axis in this particular picture, this axis is probability of belong to class 1. Okay, that's why your S curve is coming like this. This S curve has been built out of a linear model. If you had taken this, as probability of belonging to class 0, then it would be reverse S curve. Because your curve would be like this, the line would be like that. Oh yeah, all models have problem with outliers.
So can you explain what is the reason you have taken S curve rather than the linear?
Can somebody answer that question? Why S curve?
Because the linear was it will go to plus infinity to minus.
Hey, linear will be overfit. Who said that? What did in linear models, we don't have any boundary. They go to plus infinity, minus infinity. We don't want that. Probabilities have to be between 0 and 1. That's why they will convert into sigmoid. Sigmoid curve has that property that will always remain between 0 and 1. So we are able to map the numerical values to probability function.
So coming back to the same question, now you explained the binary thing. So same thing is applicable for the multi-class.
Yes, in multi-class classification, it will be 1 versus rest. Suppose I used this logistic regression for OCR, optical character recognition. So you'll have one S curve for A versus others, one S curve for B versus others, so on and so forth. So in your mathematical space, you'll have multiple S curves cutting each other. One is for A versus others, the other one is B versus others, C versus so on and so forth. All these algorithms, decision tree, naive Bayes, support vector machines, neural networks, logistic, they all break your mathematical space into compartments. They break them into compartments, pockets, where one pocket belongs to this object, the other pocket belongs to that object. All of them do that. You done decision tree yesterday? Which data set did you use? Diabetes data, PIMA diabetes data set, okay? That is a binary classification actually. And so when you make decision trees, okay, this is the structure you have of decision trees. what you're doing here is, this entire mathematical space is your root node. The entire data set, all data points put together is your root node. Then you find out one particular column on which you break the data into two. That is like putting a vertical boundary here. So these two now are these child nodes. But you have not achieved your what you call homogeneity. Your Gini index is still very high, or entropy is very high. It's still not pure leaf. So what you do is you again find a column here in this data set and break this into two. That means you're drawing a vertical boundary. So this and this is a child node here and here. So decision tree also breaks your mathematical space into pockets such that each pocket becomes homogeneous at leaf level. So right now I've reached the leaf level. Hopefully at leaf level, each pocket is become homogeneous. Now I know what are the conditions under which somebody belongs to this pocket. That is called the rules of the decision tree. All algorithms break your mathematical space into pockets, including logistic regression.
For this
You treat A as
for
class
phase
1.
For this family, the default is
This is binary class classification. If you're in multi-class classification, optical character recognition, then you treat at one point in time all data belonging to class A, alphabet A as 1, and rest of them are zeros. See what is the boundary. Then treat all the records belonging to class B as 1 and rest of them zeros. Then redraw the boundary. So you'll have multiple boundaries cutting each other.
This is like multiple variables affecting a particular attribute that we're trying to tell. For example, if a customer is fraud or not, if I'm considering age as a factor, I'm also considering gender as a factor. I'm also considering
That will be hypersurface. Hypersurface. But multiple hypersurfaces for A, for B, for C. You'll have that, right?
So will that be a consolidated single mathematical space?
Yes, 100%. Yes. The whole model will be a composite of all these surfaces. Okay. Let's move on.
So multi-class is always 1 versus A here, best.
Multi-class classification, most of the algorithms give you OVR. OVR means 1 versus rest. Some algorithms give you a facility of replacing the OVR with Bayesian probabilities. Okay, you can actually go and modify that in your hyperparameters. But most of the algorithm by default will give you OVR. Right? Some algorithms like support vector machines, OVR is not very efficient, so they give you another technique called Bayesian probability based. Shall move on? Okay. It has a gradient descent algorithm working under the hood to find you the best fit line. Right? The linear model uses gradient descent algorithm. Do you remember gradient descent discussion we had yesterday? See, the gradient descent is to find best fit line. I'll quickly summarize this. I know it was too much in one day to cover. Your error function will always have this form, not very difficult, guys. If I give you equation y equal to x square, for any value of x, y will always be positive. It's a squared term. If x is -1, -1 into -1 becomes +1. This is called a convex function. So whenever you have any function raised to power 2, it will always be convex. Right now this is single dimension. This x can be multiple dimensions. So if I take 2 dimensions m and c and plot the error, this will be a bowl shape. Right? Now in this ball shape, we have to reach the global minima. It's guaranteed you will have only one global minima. You won't have any other. For quadratic error expressions, you will always have one global minima guaranteed. Okay. So we start with some random MNC. That random MNC gives us some error. The same concept applies in logistic because logistic is also a linear model. Right? From that MNC, it will come down to this using your partial derivatives. Concept, okay? There's a lot to discuss in this. I'm not going to discuss all these things at this point, but you will need this if you're going to do deep learning, neural networks and all these things. Right? At that time, we'll take it up in detail. Same concept will apply today in logistic because logistic uses linear model under the hood. So it finds for you the best fit line given the spread of the data points in mathematical space or best fit plane or a hyperplane. Once that plane is found, that plane is sent through the sigmoid transformation and it's converted to S curve, right? Now the driving force behind this, here in this case it was quadratic. In this case, the S curve which is formed, the S curve can be shifted forward, backward, upward, downwards. Let me see if I can show this to you, okay? What happens is, insert, if I take this S curve, I hope it works. Yeah, it works, okay? Now this S curve, you can move it up by changing the C in y equal to mx plus C, or you can move it down. You can flatten it. To flatten it, what do you think we'll use? The slope, m of the line. By changing the slope, I can make it vertical or flatten or move it up and down using C. So by using these two parameters m and C, I will find out which sigmoid surface I get is the best surface. And to find out which is the best sigmoid surface of all the infinite possibilities, it uses a function. That function is called log loss. This is just like your gradient descent, okay? Don't worry about this function, it's actually very easy. Looks dangerous, but actually it's very easy. Now let us look at the log loss function. Looks very dangerous, but it's actually simple, very simple, okay? So forget the sigma and all these things, just take the expression yi into log of pi, okay, plus then 1 minus yi into log of 1 minus yi into log of 1 minus pi, correct? Just look at this expression. What is this y? Y is the target variable. Target variable. We know the target variable ranges from 0 and 1 only. 1 is for green and 0 is for red. So this yi can take a value of 0 or 1, okay? Now let us look at 4 situations. I'm going to show you 4 cases, and the 4 cases we're going to discuss here. Where is the 4 cases? These are the 4 cases. Look at the first case. In your data, the first test case, these are 4 test records, okay? The first test record has this income. The model is saying the probability belongs to blue class is very high and is actually blue class. No error, 0 error, right? 0 error. Come to this. What is the y value for blue class? 1 into what is the probability? Very high, almost close to 1. Log of a very high number, when log comes close to 1, this is 0. Log of a very high number is 0, close to 0. 2 raised to power 0 is 1. So this is log to the base 2, okay? So log to the base 2 of a very high number means close to 1, will always be 0. Come to this term. This becomes 1 minus 1, we don't even need to evaluate because this is 0. So when you do correct classification for the blue points, your error is 0. Let's take the next case. The next case is this red point. Let's take this red point. Let's take the case number 3. Or let's take case number 2, the second case. Okay? As per the model, given his income, the probability of him belonging to blue class is very low. Which means the model is predicting that he belongs to the red class. As per the income group of this person, the model is a blue line. It's saying probability of him belonging to blue class is very low. Anything below 0.5 is very low. So the model is predicting that this guy is going to be red, but actually he is blue. So let's see what the equation says. He is blue, value is 1. Probability is very low that he belongs to blue class. The model is saying probability is very low. Log of a very small number is a very large number. So this is into a large number. Okay, since he is a blue class, this expression we don't even need to evaluate. It will be 0. So whenever you do misclassification of the blue, you get a very large error. All right. So the more the blue class is on this side, larger the error will become. So in technical parlance, what we say is, more confident this algorithm is about a particular classification, which we know is wrong, more the error it does. Right?
So if the probability is less, because in this PI, if it is goes lesser, then the larger bracket becomes more large.
Yeah, correct.
The error will go more. If you go down, it will still further.
So for this blue point, where the probability of him belonging to blue class is almost 0, this error will be very high.
So what we are saying is more error we do on this side.
For blue class.
For blue class, then loss is more.
Yeah, exactly.
And upper side, even the error is there, but loss is less.
We'll come to that. We'll first discuss only the blue class. The more blue points are on this side, in this case, the more the errors will come out. Larger the error will be. Okay? Now look at this, the red one, the fourth one. Or let's take the third one. We know that this guy is a defaulter. The class is red. The model is given the income, the model is predicting he is going to be defaulter. Come to this equation. What is the label value for this guy? Class red, 0. So this expression becomes 0. We don't even need to evaluate. Come to this guy. 1 minus 0 is 1 into log of a very small number. Number minus 1 becomes almost 1. So this expression turns out to be 0. Log of a very large number, okay, is 0. So this expression comes too close to 0. For red classification, we use this part of the equation. For blue classification, we use this part of the equation. Take the last case where the red class is misclassified. The model is saying he belongs to blue class.
So one question. So PI is the probability, right?
Of belonging to blue class.
Belonging to blue class. That's why it is 0.
Yeah. See, the model, the surface is probability of belonging to blue class.
Okay. That's why it is 0.
Yeah, exactly.
For the right.
Exactly. Look at the last case. Last case is the fourth case, where the fourth case is misclassification of red. So when you do misclassification of red, this expression is not for red, so forget it. Come to this. This is 1 minus 0 into log to the base 2. This is a very high probability which your model is predicting. So this becomes a very small number. Log of a small number is a very large number. So error is very large. That's all this equation is. So you sum up the errors done across all the data points, those which are correctly classified, those which are not correctly classified, sum it up, you will get the total error across the entire model. Sum of squared errors, same way this. So the objective is to minimize the sum of squared errors by finding the right logistic surface given the classes.
And so the gradient distribution will say that. So suppose it's a high loss, and it will go in a direction where it want to reduce that loss.
Reduce the total loss. Correct. Yesterday, the sum of squared errors was driving the gradient descent. Here, this will drive the gradient descent.
So it does gradient descent first to get the linear equation and then does the second to get the sigmoid.
Right, sigmoid curve. Both happen together actually, both happen together. It's not one after the other, both happen together simultaneously.
What is the range for this plot? Specific to the data?
0 and 1. All 100% is your complete loss. Which will happen when you have all the red 7 classified as blue and all the blue 7 classified as red.
Logic sheet always places 0.
Yeah, for classification, always even. All right, shall we move on? Extension of linear model that we saw yesterday. The beauty of logistic regression is it makes no assumption about the distribution of classes in the feature space. Many of these algorithms, linear model especially, if you're building linear classifiers or linear regression, they expect Gaussian distributions. You understand the term Gaussian distribution, all of you? No? Okay. When you build any model, expectation is if you take this attribute, the data will be spread around the central value of this attribute with some standard deviations. Same way, this attribute will have a distribution with standard deviations. When you plot this together in the mathematical space, they will look like, if they are independent of each other, they will look like this. We already discussed this. This kind of a distribution is called Gaussian. So in 3D, it looks like a bell curve. All right. This algorithm does not make any such assumptions, but keep in mind, if you have outliers in your data set, even this algorithm will fall on its face because it is based on linear model. So those outliers have to be addressed. What will happen if you have outliers? If you have outliers, you're likely to have outliers for, say, for example, what do you call them? The class 1. If you have an extreme outlier here, then you're in trouble. If you have outlier on this side, no problem. If you have outlier on this side, you have a problem. So more extreme it is, more severe the outliers is, more the errors will be. Right? Okay. You can do multi-class classification using either binomial distribution in this case or multinomial distribution also is possible. You can also print out the probability values if you're not interested in the class, but I want the probability values. What is the probability belongs to this class or that class? Quick to learn because it's based on linear model, and you have gradient descent to help us out to find the best fit line quickly. Fast in your test data also. In test data also it's very fast. And as I said, many times I have personally seen logistic regression stands out among the top few in many of the situations. Resistant to overfitting, because as a simple linear model, linear models cannot be very complex shapes. It is resistant to overfitting. Okay. Resistant to overfitting does not mean resistant to bias errors. It means resistant to variance errors, right? But we have another one to deal with. And you can print out the coefficients, the probability values, and interpret the probability values. So the model is not a black box, right? Disadvantage in classifications is it uses linear boundaries. What it means is, if the distribution of the classes is something like this, then the model will suffer. Right now we took a linearly separable this thing, but what if the distribution is not linearly separable? Then logistic regression will suffer. If the distribution was like this with overlap, but it was like this, then it will do well. But if the distribution like this on the attribute you have decided, you see the difference? The difference is, if I plot the density graph, okay, in this case, the two density curves are overlapping. Your t-test, analysis of variance, and all these things will tell you that this record belongs to this class, that class, 50-50. It will not be able to classify. On the other hand, if I look at this situation, your overlap is there, but the central values are shifted apart. So when we have distributions which are linearly separable, may not be 100%, then logistic will do well. But you have distributions like this. I don't know whether you noticed, PIMA dataset is like this. That is why in PIMA dataset, you will not be able to get accuracy beyond 70%, 76%. Do whatever you can, right? It will not give you beyond 75. When the data distribution is like this, none of the algorithms will be able to help you out.
When we start building this model, we need to check what our data distribution is like.
100% you have to know your data before you start building the models. You have to know your data, which means you have to know every attribute, how the data is distributed if you're in classification, how the classes are distributed, which dimensions or which attributes are able to linearly separate the two classes. Use only those for your classification models. You have some attribute where both the classes are significantly overlapping, including the central values. Using such attributes for building model is useless, and PIMA Indians, you will see all the dimensions are like that.
So this is what we can do actually. We can't do anything. No other algorithm.
No algorithm will work. Okay. What human brain cannot do, an algorithm cannot do. So you have to have at least one attribute, as you will notice in another data set that is called bank.csv. There also the data overlaps on all the dimensions between the two classes, but there are few dimensions, 2 or 3, where the data central values are separated apart. Based on this 3, it gives you 96% accuracy.
So for our model, we should consider only those.
Only those, yeah, correct. You don't need to include all of it.
What is the name of that bank.csv, that two attributes? What in the
some attributes, some, I'm just randomly taking.
What is that gross error?
This is scatter plot. This is scatter plot. Now you find out how the density of the plot changes when you move from this direction to this direction. You will see that the density is very low, very low, very low, increases very high, highest, then it starts falling. So when you convert this into 3D, it becomes a normal distribution. In 3D, this becomes a normal. That is called density distribution, 3D.
So can't we switch the axis for analysis in this case?
Can we?
Can't we switch the axis for analysis?
Switch means?
Say y-axis becomes x-axis so that you are distributing.
What you're basically saying is, no, I'm comparing these two with this over here. This axis is not there. I'm just saying, if you have a distribution like this, your logistic will do well. If you have a distribution like this, your logistic will suffer. Any algorithm will suffer. Okay? But what you're saying is, can't we switch to this axis where the two classes are separated out? That's what you should be doing. So if you have two axes, two attributes, on one attribute they are not linearly separable at all, but on the other attribute they are linearly separable, use the other one. That's what I'm saying. Yeah, alright.
In 2 dimensions, you can see like this. You can change to 3 dimensions. You can see some of the data are up.
So use that dimension, which is helping you to separate out the two. Don't use this dimension.
Can we apply one model on one attribute and another attribute?
That is what random forest does. Random forest, every node of the forest is constructed using randomly selected features from the data set. Yeah, it internally does that. But random forest is the only one which comes close to what you're asking. No, it doesn't do that. It randomly picks up. It doesn't see whether these are the best attributes. Alright? Okay, let's move. Let's do a hands-on. This is the same data set. PIMA Indians diabetes data set. Same data set. Shall we do a hands-on on this? Okay. Alright guys, are you all ready? Okay. So if you have access to the code, the first line is matplotlib. We already know what it means. I'm importing from scikit-learn linear model logistic regression. Yesterday we had imported linear regression. Okay. Then I'm importing Matplot, SPLT, Seaborn. I use Seaborn libraries for my plots, especially pair plot comes out very well in this. So I'm going to use this. Train test plot, you already know what it is. Numerical Python. And to measure the accuracy of the model, I'm going to use metrics. So whenever you're doing classification, one of the most important tools for evaluating your model is your confusion matrix. Okay, so that comes through this metrics library. We'll see all these things down the line. Earlier, this PIMA diabetes used to be available in UCI dataset, but now I think it has been removed or archived. So it's not available, but I downloaded it from kaggle.com, another site. I'm loading the dataset over here. It's a data file, it's a text file. While loading the data file, I'm feeding the column names here, which I got from the original source, the column names. So the column names are, the first column name is pregnancy, how many times, by the way, this particular test was done amongst Pima tribes, a tribe in South America, where apparently the ladies are prone to type 2 diabetes very early in age. So this research was done by this university where the objective was, can we build a model and predict who is going to have type 2 diabetes by the teenage? Okay, for that they did research on that community. Some of them were diabetic, some of them were not diabetic, and the characteristics that were captured are these. The first one is number of times pregnancy reported by the subject. The next one is plasma level in your body. Plasma is a component of the blood. Then we have blood pressure. This is diastolic blood pressure. This one is diastolic blood pressure. Then we have skin, where apparently people suffering from type 2 diabetes in that tribe, they have some kind of skin folds. This is measurement of that. Then they do some testing. This is called fasting sugar test or something. That is this test. Body mass index. PEDI is another test. Some pedigree test they do, I think. It's another test related to blood sugar. Age. And the last one is your target column, whether this person was diabetic or non-diabetic. Diabetic means 1, non-diabetic is 0. Now the whole thing, that the objective is, we are trying to find out, is there a relationship between the independent variables and the target variable? What is that relationship we are trying to find out? That relationship we assume exists in the universe, in the real world. We are trying to find out whether we can discover that relationship. So for that, we are building this model. And I always do this based on the experience on CAR-MPG dataset. When you look for this head, okay, when you look for some sample records, you see all numerical values. But what is a guarantee that there is no record further down which has some non-numerical values sitting in the numerical columns? What is the guarantee? How do you identify that? To identify that, we can use this method. What I'm doing is, I'm using a numerical Python function isReal. This function is a binary function, it's a Boolean function. It will give true or false. This function, I'm applying it onto, look at this apply. I'm applying it onto all the rows, all the columns of this. This is the beauty of Python, where you have to do minimal coding. If you had to do this in Java, you'll probably write a for next within a for next over here. So all that thing is taken care of. So what's happening is, I'm going to apply this function isReal on all the rows, all the columns of PIMA-DF. Okay, and you see this tilde over here. This is a NOT operation. I want only those records where it returns a false. Okay, fortunately there are no records where it returns a false, which means all records, all columns are numericals. What is the other way of finding out whether any such non-numerical characters have come into the data?
Data types.
DF types, that's it. DF types, when you do, It will return the data types of all the columns. If there is any non-numerical value in any of these columns, it will return it as object. That is easier than this, DF types.
So what we do if there is a problem?
What we do if there is a, we have to go and identify the record, convert that into n, numerical. Then you can replace with median, mean, whatever replacement strategy. We don't have any such case right now, okay? But we have nothing to be happy about because we're seeing a lot of zeros. And zeros in blood pressure is surprising. It can't be, not possible. Zero in plasma is not possible. But you have zero values in blood pressure, you have zero values in plasma. So missing values are there. The missing values will cause problems. We need to address the missing values. Okay. Let's move on. Do a describe how the data is distributed on the various dimensions. Univariate analysis. If you don't like this, don't do it. Do the pair plot. Pair plot also gives you visually the same univariate analysis. Okay. So I'll quickly tell you one. Look at the difference between, for the test data, the test attribute, look at the difference between the mean, 80, almost 80, and the median, 30. The mean is drastically shifted away from the median on the higher side, which means there is going to be some long tails on the right side, on the higher side. Mean gets easily impacted by outliers. So some outlier is pulling mean towards the right side. How do you confirm that? Look at the distance between the third quartile and this. Look at this. Correct. Look at, you're like me, you don't want to calculate? Can you tell me how long is long? The right side tail, look at the length and compare that to the left side tail. Left side there is no tail. 719 units. So is this possible or is this a typo? We need to go and check. Maybe this is a typo. We don't know. Okay, right, I'm going to move on. The next thing that you have to do is first understand how the data is distributed on your various dimensions. If you think there are outliers, we need to address outliers. We already know we have missing values, we need to address missing values. The next thing you need to do is, since you're in classification, how many records are available for each class in the data set? Look at that. The number of cases for non-diabetic, 0, is 500, whereas the number of cases for diabetic is half of that, almost half. You are preparing for your board exams, and most of the questions that you solve, practice on, is calculus. A small part you do it on trigonometry. Obviously, you're going to flunk in trigonometry, right? Why? Because the pattern of questions that come to you in the exams in trigonometry may not have been reflected by the patterns that you have used. Which means you have not gone through all the possible patterns in the trigonometry questions. Same thing will happen here. To the model, I have given only 268 of the diabetic cases. Maybe this 268 does not reflect all possible permutations that lead to diabetes. So the model will perform poorly in predicting the diabetic cases. It will perform relatively well in predicting the non-diabetic cases, but I want the reverse. The objective is the reverse. Okay? And keep in mind, whenever you're in classification and the classes are skewed like this, all algorithms are biased towards the higher represented class. All models, the objective is to minimize the overall misclassification. So their focus will be on the higher class. So this is another source of bias which comes into the model where the algorithms themselves are biased. So how do you handle this? Make find it too? Yeah. We call this strategy upsampling, downsampling. Okay, there is a strategy called upsampling, downsampling, which I'll refer to, which I'll take you through when we do FMT, model tuning, but right now we're not going to do that. There is a package available, it's called InBlearn. But right now we're going to live with this. There's another way of improving the the classification, performing better in the underrepresented class. That is called modifying thresholds. Thresholds. In logistic regression, naive Bayes, any other probability-based model, the cutoff is 50%. If the probability of belonging to blue class is 51%, the data point will be classified as blue. If the probability of belonging to the blue class is 49%, the data point will be classified as red. So the boundary is at 50%. Okay, I can modify the boundary. Though none of the algorithms allow me to modify the boundary directly, I can build wrapper class around the algorithms. I build the model. Around the model, I write my own class where I modify the threshold. Okay. Once again, I'll cover this in FMT, not now. It'll be too much. So we can play around with the threshold, modify the thresholds to improve the accuracy of the underrepresented class. We can do that. Okay. How do we do that? We'll take it later. But whenever you see in classification skewed distributions like this, be ready. There's no way you can achieve a very high accuracy for the underrepresented class unless you play around with these two techniques. Let's move on. So this is my pair plot. Okay, I don't like this. So let me quickly redo this. All right, I'm going to come into, I'm not going to do all this, I'm going to come straight to this where I'm going to say SNS pair plot, comma, dag underscore kind is equal to KDE, kernel density estimate. Since these are numerical values, it makes sense to have this. And hue means color, is equal to the last one, what we call it, target class. So hue is equal to class.
You haven't treated outliers
Not
or
yet.
the zero values. So you just
Yeah, on the raw data. It'll take some time. It's past actually. Yeah, there you go. Now let us understand this pair plot. All of you have it? Let's look at the very first dimension. The first dimension here is pregnancy reported. Okay. The blue is non-diabetic class and the red one is the diabetic class. The orange is the diabetic class. Okay. If you look at it, the two distributions are overlapping with the central values. They're overlapping. Very small separation over here. Come to the next dimension. The next dimension is your plasma. Plasma, you see long tails on the left side with a small bump. This is their outliers, the zero values. But otherwise, both the classes, the blue class is perfectly, looks like almost like your normal curve. And the central values are overlapping. The central values are eclipsed. So once again, not a very good attribute, but at least we have some differentiator here. Look at this one. Even the outliers are overlapping. This is your blood pressure. These are the zero blood pressure cases. They are also overlapping. Yeah. So there is no way your blood pressure will be able to separate out. Based on blood pressure, you cannot distinguish diabetic versus non-diabetic. There's no way you can.
But if you correct those zero values,
still, whatever technique you apply will be the same technique. So both of them will shift together, right? So we have a problem there. Look at the next one. This is even more surprising. Almost gone. Skin color, not skin color. This is skin fold. Yeah, you see the same problem here also. Every dimension you look at it, every dimension has this problem. on none of the dimensions except for a few dimensions where you see small difference in the two classes, none of the dimensions are separating the two classes out. So even if you put all these dimensions together and build a model, we are not going to have anything. Yeah, it's overlap, almost this case, the previous case, this one. And that's what we are seeing here. The two classes are overlapping on every day. They are not shifted like this. Let's go ahead and build a model. Let's not be very hopeful about this. Any model will give a problem here. So what I'm doing here is, this is not required. It's not required to be done. All algorithms can take as input the data frame itself. But earlier I used to do this as a practice, where I'm converting the data frame into an array. So data frame minus the column headers is called an array, okay? And that array, I'm taking the independent attributes into X and dependent attribute in Y. And then I'm splitting this X and Y into train set, test set. Is this part okay with you people? All of you with me on this? All of you, Sairam? You're also on this? Great. Now look at this. I'm instantiating the logistic regression model. You can call it anything you like. I'm calling it model. I'm doing the fit. This is where the best fit line is found and convert into your sigmoid curve. The fit. Once the model has been found, then I make use of the predict function of that object on test. So these are my predicted labels, diabetic, non-diabetic. The actual labels are Y test. Okay. Some people get confused here, so I'm going to stop it. Don't look beyond this. Just stop here. I'm asking you to just look at this part. Till this point, everything is fine? Okay. Now what I can do down is, I can, for the time being, I'll remove this, okay. I'll put a, yeah. For the time being, just ignore this. Control X. We'll put it over here. Insert cell below, and we'll put it here. All right. I'll uncommit it later. I'll do that. Okay. Now look at this. Have you seen confusion matrix before? Yeah. All of you agree it's exactly what it's called? It confuses people a lot, right? Confusion matrix. So what I do is, as a practice, when I make my confusion matrix, I always keep the actuals on this side. Actual diabetic, non-diabetic. And the predicted, the output of the model on this side. Diabetic, non-diabetic. This is my practice. You can follow the other way, but whichever way you follow only one. How do you control this? Since again Y test first, this is actual, it goes to the rows. Y predict next, this is your predicted values, goes into the columns. If you flip this, you'll flip that. Now what it's saying is, of the 147 diabetic cases in your, sorry, this is non-diabetic, not diabetic, this is ND, non-diabetic, this is diabetic, ND, D. Awfully sorry. If you go and read the source of the data, they're very clearly told 0 is non-diabetic, 1 is diabetic. Of the 147 non-diabetic in your test data, 132 have been classified as non-diabetic. No mistakes. For this class, true positives. Of the 147, 15 have been identified as diabetic. Incorrect classification. These are those values of red lying on the extreme end, values of blue lying on the extreme end. Look at the diabetic class. 84. There are 84 diabetic cases in your test data. Of this 84, 46 have been correctly classified as diabetic. 84 minus 46 is 38. 38 have been misclassified. Okay? Now look at this. Now look at this. What is the overall accuracy? 77%. Looks decent. But let's look at accuracy in diabetic class. Okay? We call it recall. Recall is, the formula for recall is true positives by true positives plus false negatives. Looks very hi-fi, but what it means is true positives divided by row total. So the recall is 46 divided by true positives plus false negatives. This is false negatives. For this class, this is false negative, right? So yeah, so it is 46 plus 38 back to 84. That comes to around 55%. Hey. It's coming like 55, 54%, right? That is like tossing a coin, heads or tails. You don't need a model for this. Right? So to get this kind of accuracy, you don't need a model. You can just toss a coin and say diabetic, non-diabetic. That is what this is. So overall looks great, but don't get fooled by this. What is important is this, but this is what we expected because this is represented very poorly, the diabetic class. This is important for us. Look at the recall for the non-diabetic class. Non-diabetic class, the recall is 132 by 147. This will come very high, 90%, 80%, 90% roughly round. So the recall for the non-diabetic class is very high. Recall for the diabetic class is extremely poor. But that's what you should expect. We wanted the reverse. So that's what will happen when you have situations like this. Okay? There is no way you can get a very good model when the individual attributes are poor attributes and the classes are underrepresented. You can't do it. So the magic happens in the data. How do you prepare your data for analytics? That is where the magic is. It is not in the algorithms. Okay? It depends on data preparation. 80% of our project estimated effort in data science goes into preparing the data. Running the algorithm is matter. Then rest around 15 to 20% goes into fine-tuning a model. It goes into that. All right, let's do, there is a function called score. Instead of doing this, I can directly call score, but don't rely on this when you're doing classification. What this function does is, it regenerates the model and then tests it on this test data. It regenerates the model, then compares the test data and this automatically and gives it the score. Okay, so this has nothing to do with confusion matrix. You can actually run this and say remove the hash, run it. It should give you the score. Model is not defined. Why? What spelling mistake? Oh, I have not executed. I'm just showing you this. Okay. I have not executed these lines. So it gives you overall score, but overall score is not reliable, so don't depend on this. Shall we move on? You need to learn the tricks of identifying good attributes. Feature engineering, feature selection, and that is where the core lies. 100%. Domain. If I want to predict the time taken to travel from A to B, then I should have the domain experience of what are the factors that can impact the time. That's what the attributes they collected are useless attributes. It's not good attribute. I don't know, but the fact is it's not good data set for classification.
Here, I mean, you see the diabetic class was all your models were biased to
Non-diabetic.
So we cannot use because of synthetic data.
That is what this imlearn does. Upsampling, when you create upsamples, it actually creates synthetic data out of the underrepresented class.
Is it a acceptable practice to do that? Or
You have only one choice. Either accept it or stay with this. No, I'll tell you. On a serious note, it is an acceptable practice. It is an accept. Finally, what is important to me is the model should generalize in production. That is important to me. So when we release models into production, the models are not immediately used in production. They are put into alpha test, beta test. If after jacking up the data, if the model is performing poorly in the alpha and beta, I will not release it.
Just like pre-prod.
Yeah, it is.
Just because you don't have enough data in
It's allowed. Synthetic. See, I'll tell you quickly what happens in upsampling. Okay, upsampling uses k nearest neighbors. So what upsampling does is, if you have two classes, this is underrepresented class, so diabetic class, triangles, and non-diabetic. Most of them will be non-diabetic. Okay, and there is some overlap here. Okay, most of them are non-diabetic class. What this upsampling using imlearn does is, it tries to generate synthetic data out of this. Just one thing, let me finish this. The synthetic data generated is such that it does not disturb this overlap region. It creates synthetic data in these regions. Yes?
But by doing the upsampling, are we not introducing the bias error?
100%, guaranteed. So we are, by introducing the bias error, we are taking away the bias in the algorithm, which is towards the higher class. We are trying to cancel that bias error by upsampling.
So actually upsampling and downsampling is adjusting the bias.
Correct.
We are actually trading the bias.
We are trading off the bias which exists naturally in the algorithm towards higher class.
Are they exact duplicates or?
No, they are not duplicate. They are synthetic data generated using k nearest neighbors. So I take a random point here, then k nearest neighbors. If you use k nearest regressor, for example, you'll sum up these three and give you the average.
In this case, if you use k-nearest, all our stars will not circles.
No, all are stars, but what we'll do is, it's k nearest regressor. So it's going to take the blood pressure of all three, find out the average, give the average to this new point.
So that can be circular.
That can be?
That can, so there are two classes, star and circle. So if you don't.
It works only on the underrepresented class. It generates synthetic data only for the lower class. So in this case, it will generate synthetic data only for the diabetic class.
So in this case, like if you take this sample and if you decided to upsample our data, at what point we should stop? Like these many samples would be enough. We should not go further.
It will bring both the samples to 100 same level.
So 50-50 you mean this?
50-50. It will bring you to 50-50.
Can you give us some pointers?
imlearn. Go and search for imlearn on Google. You'll find that package imlearn. You'll see a lot of reading materials there. But we will cover in detail in FMT.
Okay. So when you do downsampling, it will reduce the records of
non-diabetic. It'll delete those.
So either we can go with that approach.
Don't do your manual approach of deleting the data. Don't do that. That will be the worst thing to do. Anyway, coming back to this. So what the next thing which you're going to try is, since all data is numeric, let's convert all this data into what is called standard scale. Xi minus x bar by standard deviation, right? And that's what I'm doing here. From pre-processing library, I'm calling the scalar function. So it converts every record, every column of this data frame into scaled data. Same with test record also convert into scaled. On that, I rebuild my model and relook at my scores. As I said, sometimes we expect miracles to happen, it never happens.
Which type of scaling does it use? Which type of scaling does it use?
This is Z-scores, central values. Yesterday I told you, Scaling does not impact linear models. So you won't see any impact. There's nothing else we can do. It converts into z-scores, x minus x bar by standard deviation for every column. Centralize the data to 0.
So we have a few ways. One is either we do up sampling or down sampling. But right now we don't know which is okay.
Correct.
So we need to try with both and see.
Exactly.
But will that really affect if we do an up sampling?
100%. It will affect the accuracy of the recall for the diabetic class. 100%.
No, I mean doing an up sampling or down sampling. I think we can go for either choice. Or compulsorily we have to go for both the choice and then.
That depends on how your data is distributed. It depends on that.
Both and see whichever will be more accurate.
It depends on that. Okay, it's a very subtle relationship with the data distributions in the various dimensions.
So the only solution is
And the threshold management, changing the thresholds. 50% is the threshold, no? So I can say whenever probability is less than 30%, it belongs to red class. Above 30%, it belongs to blue class. I can change the threshold. Right now, by default, it's 50%. If probability of belonging to red class is less than 50%, that means he belongs to blue class. Right now, it's that. So that 50% can be changed to 30% by building wrappers around this model. The number of records is what you have in your data. Threshold is in your sigmoid curves, okay? Sigmoid or any probability-based algorithm. This is my probability dimension, 0 to 1, 0.5. Whenever a function, this sigmoid function says the probability is greater than 0.5, 0.55, 0.56, then it will automatically say that this record belongs to the blue. If it is below 0.5, it will say it belongs to the red. So I can bring down this threshold and I can put it over here, 0.3. Anything over 0.3 belongs to blue, anything below 0.3 belongs to red. So by changing the threshold, I can control the misclassification of the diabetic cases. No, it's not a parameter. You have to build a wrapper around your model. There's no automatic way of doing this. So I'll use a function in scikit-learn. It's called binarize. In case you're very impatient and you want to know what it is, please go and explore this function binarize, B-I-N-A-R-I-Z-E. How using binarize we can control the threshold, explore that. If you're not able to find, I'll tell you how to do that in FMT. Which models are suitable for time series? When you talk about time series, automatically only one model comes to the mind, ARIMA, A-R-I-M-A. It's a time series based modeling, which is basically linear regression applied on a time dimension, right? So you'll explore that. You have anything on time series to be done?
No, because I don't know IoT being the most.
Oh, then you'll have to learn.
My focus on subject studies.
Yeah, ARIMA is linear regression on time dimension.
But that is mainly on forecasting. Suppose I want to have optimal probing use case.
Optimal what?
Probing.
What is that?
Probing network.
Okay. That is basically to look for intrusions and all these things, kind of things.
So at one point of time I want to do a network.
Or network discoveries. I am not able to put any particular algorithm there. Probably we'll discuss this further and design. You bring it up. We'll take it up. All right. Let's quickly start and summarize what we did. Okay. We started yesterday by discussing about linear model, linear regression. Okay. In linear regression, the algorithm was used to predict the values. The output is the target is values running numbers. Okay. And for that, we discussed how it is important for you to first analyze your data and check which attributes are strongly related to the target attribute. Select only those. Amongst those attributes, drop the attributes which are redundant, that is, they correlate with each other. Remember this discussion we had yesterday. Same discussion continues today also. But before I come to today's topic, we also discussed yesterday that in linear regression, the algorithm finds out for you a needle in the haystack, the best fit line from infinite number of lines using the gradient descent concept. Okay? So the objective is find the right kind of M and the C which will minimize the sum of squared errors. All algorithms have some objective to achieve. In mathematical terminology, we say that all these algorithms are optimization functions. Optimization means minimize something or maximize something. Okay? By using these optimization functions, it identifies for you the best fit line, and the methodology is called gradient descent. Right? Then the linear regression, today we saw how it is used in classification. This is not the only way. There are various other ways in which linear model can be used for classification. When we come to support vector machines, we'll talk about that also, support vector classifiers. Using linear model for classification based on probability values, you have a challenge. The challenge is linear models extend to infinity. And it makes no sense to have values beyond 0 and 1. So we convert the linear models into sigmoid surfaces. Okay? The sigmoid surface will come to you again and again many times in many different algorithms, especially those who are going to do neural networks. You'll find that neural network uses by default sigmoid to bring in what we call non-linearity. We'll talk about those things later. So a linear model is used for classification in logistic regression, where it is transformed into an S-curve, a sigmoid curve. Right? But all the rules of data analysis use only the right attributes. Within those right attributes, there should be no collinearity between them. All those things continues to hold here also. Okay. Now I'm going to introduce you to one more model called Naive-Bayes.
Before we go there, can you just give me a brief distinction between covariance, collinearity, and correlation?
There's no difference. Covariance divided by standard deviation, measured in terms of standard deviation, is called correlation. Okay? So if you have xi minus x bar into yi minus y bar, okay? When you divide this by standard deviation of x and standard deviation of y, we measure it in terms of standard deviation units. This is called correlation. If you don't use this, it's called covariance. And whenever two dimensions have a very strong covariance or correlation, they are called collinears. That is called collinearity. So same thing coming in three different ways. Linearly separable is that distribution, okay, whose data points in the feature space have some kind of a gap between their distributions. So I can represent this gap using a linear model. So when I use a linear model for classification, the model is trying to not represent the data points, but it's trying to represent this gap. I'm trying to model this gap between the two. Such distributions are called linearly separable distributions. They may not be linearly separable on one single dimension. There might be overlap. Even on this dimension, there is an overlap. But put together, they might become linearly separable. Question? Shall we move on? Yeah. So I'll extend this discussion a bit further. Here we see the red ones. Okay, this is the distribution of the triangle. This is the distribution of the circles. Same way, distribution of the circles, distribution of the triangles. Okay. The two distributions are overlapping on individual dimensions, univariate analysis. But when you put them together, the two dimensions together, the two distributions get separated out. They become linearly separable. Yeah. So even if I have weak dimensions in my pair plot, I see very weak dimensions. They're very significantly overlapping, but the central values are slightly away from each other. Maybe combination of these weak dimensions put together will give me this. But unfortunately in PIMA diabetes, none of the dimensions give me this.
I don't understand the point. You told that two dimensions are overlapping each other.
In two dimensions, the classes are overlapping each other. Okay. So in PIMA diabetes, if you see the diagonal, all the classes or central values are significantly overlapping. If you have even a single one, which is central values are shifted away. Okay. Maybe another single one where the central values are shifted away, not significantly shifted. Maybe these two together will be able to give me linearly separable classes. But unfortunately, PIMA diabetes, all the dimensions, if you observe carefully, the central values are sitting on top of each other. Analysis of variance uses the difference between central values to tell you what is the probability that these two belong to different class. So as long as the central values are overlapping, there's not much you can do. The body of the distribution overlapping is still tolerable, but central values are overlapping. That is the problem. All of you okay? Shall we move on?
But what we analyze is just one. So we didn't analyze two different variables together.
We did not. We saw in diagonal. Look at the scatter plot also. Scatter plot also, they're all sitting on top of each other. They're eclipsing each other. Scatter plot also, the blues and the yellows are eclipsing each other. So the centroid of the blue cluster and centroid of the yellow cluster, they should not be eclipsing each other. All right, let's go on to this new one, naive Bayes. This is purely statistical model. It's based on the Bayes theorem, which I presume you people have already covered in the statistics class. Don't say no. Right. Okay, so let's see what is this Bayes theorem, how is it used in modeling. This model, this algorithm is based on the Bayes theorem. It is used for classification. Again, it uses probability values to decide which class a test point belongs to. This is the only algorithm which gets this term associated with it called naive. The term naive is not a very good thing to be associated with. Okay, but this algorithm is the only one which gets associated with that. Very unfortunate, because all algorithms are naive as per this definition. The reason why it's called naive is this algorithm assumes that all the variables that you're going to use to build the models, those variables are independent of one another. The independence assumption is often violated. We already discussed this. But then this is true for all the algorithms. It's called naive due to the assumption that the features in the data set are mutually independent. They don't interact with each other. But that's what every algorithm does. So this is the only one which gets the cap, the hat, whatever you call it. But the beauty of this algorithm is, what this algorithm says is, howsoever weak predictors your features may be, don't drop them. Consider them. Take into account the information given by each feature and build your model based on probabilities. So it doesn't advocate you from dropping any of the features. Howsoever significant the overlap might be, use them. That's what this algorithm says. To understand this algorithm, we have to understand what is probability, we have to understand what is joint probability, and we have to understand what is conditional probability, three of them. So let's quickly start. What is a probability? How do you define probabilities? Okay, chances of some event occurring. So in the definition, you have an event, and then you have something called chances. What is chances? How do you find that out? How do you find the chances of something happening? So what involves the experiment? What is there in the experiment? Trials and proportion, right? So if I ask you, what is the probability that today it will rain? And you might be surprised, just a week or 10 days ago, there was news in the web where in Kerala there was snowfall. Have you seen that? In Kerala there's a hilly, what do you call, hill spot? Munnar, right? There they had snowfall and the temperature was -3, right? So such events can happen. So if I ask you, what is the probability that today it's going to rain at 5 o'clock? Why did you say 0? Who said 0? Yeah, why 0?
Sunny.
So
I don't see any clouds.
So
Never happened.
Check my
don't check the weather, just talk. So what you've done is you've taken your past experience into account. On this particular date, month of January, almost middle of January, how many times in the past did I see rain? That ratio, how many times you saw this event of interest versus your past records, the number of trials. This ratio is called frequentist approach to probability. So the probability is a ratio where it's a ratio of the events of interest to you, how many times they have occurred, out of the total number of trials, how many times the event could have occurred. That is a ratio called probability values. Did you know that probability values can be calculated in another way? Have you done Poisson distribution in statistics? Poisson distribution, very convoluted formula there. If given the state I am in, what is the probability that I'll be in a different state, the next state? That is a function of how many ways you can reach that state. Okay, so that is another way of finding probability. We are going to use the previous definition of probability, which is based on frequencies, ratios. Okay. Now that you know what is probability, the next thing you need to know is what is joint probability. Joint probability is probability of multiple events occurring together. Okay. So what is the probability of, if I give you a deck of cards and I ask you to pull a card out of it, and I ask you, what is the probability that this card is going to be a red king?
1 by 52.
1 by 52 is red.
No, you never played cards.
2 by 2
You have 52 cards? Red king.
2 by 52.
Red king is 2 by 52? So there are two colors, red and black, 52 cards. So 52 cards, you have 2 red kings, hearts and diamonds. So the probability of this joint event of red king is, red is 1, king is 1, the probability is 2 by 52. Alright? Now when you're pulling out the card, somehow you come to know that it is a red card. Somehow you come to know it's a red card. Now what is the probability this is a red king? Now you know it's a red card. So your scope is now limited to only red cards. 2 by 26. 2 by 26 is 1 by 13. So you have taken into account an evidence, an information that you captured that it is a red card. The moment you get that information, you recalibrate your probability of red king. That concept of recalibrating your probabilities based on the information that you're gathering, that concept is called Bayes' theorem. So what Mr. Bayesian said is, start with some probability, the default probability values, but keep on recalibrating those probabilities the moment more and more information comes to you. Howsoever the information may be, howsoever weak the information may be, don't ignore any information and recalibrate your probabilities. That is the philosophy or reasoning behind this Bayesian theorem, Bayesian models. Are you all okay? So for this, to understand this, we need to know probability, joint probability, and your what is conditional probabilities. Conditional probabilities, what is the probability of king given it's red? We know it's already red card. So now only the event left to happen is king. So what is the probability that this card will be a king given it's red? That concept, which you call 2 by 26, that concept is called conditional probability. So we started by joint probability. What is the probability it's a red king? Because we didn't have any information. It was 2 by 52. The moment we came to know it's a red, then we switched to conditional probability. What is the probability is king given it's red? Right? Conditional probability is invalid if joint probability is 0. If probability of two events occurring together is 0, we don't talk about conditional probability. What is the probability of drawing a green king? There is no green king possibility. So don't even talk about conditional probabilities. So we talk about conditional probability only when we have joint probability greater than 0. All right. So let's see how all this was put into build a model. We already discussed this. What is probability? What is joint probability and what is conditional probability? We already discussed this. So I'm going to jump these slides. This is the model. I'm sure you would have seen this formula. Looks very familiar. Wow, man! You should put it on some kind of board and put it on. Looks so like you're going to launch some rocket. It's very easy. Okay, so what I'm going to do is I'm going to jump all this slide back. I'm going to explain with some animations. This blue box represents all the flight information I have captured from my experience. All the 100% flights which I have taken, I'm representing it by blue box. The dimensions of the box are inconsequential. They don't matter. When I look at my past data about the flights which I have taken, I notice that 20% of the time there was flight delay. 80% of the time the flight was on schedule. In mathematics in school, you would have done this as Venn diagrams. Okay. I also noticed from my past information, past data, that 5% of the time there was fog at the airport. Now it's natural for us to quickly link fog with the flight delay. Don't do that. We are not here to say that the flight delay was because of fog or fog was because of flight delay. We are not here to establish that link. Naive-Bayes algorithm assumes that these two events are independent of each other. Whatever the reality may be, the algorithm assumes these two events are independent. They have nothing to do with each other. Okay, but we know through our experience that they are not really independent. But the algorithm assumes they are independent. Okay, and we know that if I mark this as flight delay, no fog, this is fog but no flight delay, this crescent. This is the case where flight delay and fog occurred together. That does not mean flight delay led to fog or fog led to flight delay. We don't know. We are assuming that they are independent. What's going to happen is, the lesser the overlap, more unlikely they are linked. The more the overlap, more likely the two events are linked. They influence each other. But I repeat, we are not here to establish any causal relationships. We are assuming that the two are independent.
You mean to say, suppose there is a strong relationship from our intuition that for a particular use case, we found that there could be a strong relation, then we should not use naive-Bayes in that case.
Correct, we should not use naive-Bayes. All algorithms are like that. All algorithms show you the independent variables orthogonal to each other. That means they are independent of each other. Mathematically, when two things are independent of each other, they are shown at 90 degrees. If two attributes are very strongly influencing each other, you have to replace them with one synthetic dimension, PCA, or drop one. You have to do that. Same thing applies here also. Shall we move on? Okay, now look at this. Let's look at this region closely. This region is the intersection region, okay? Probability of flight delay and fog, the two events, the joint probability, okay? Now I told you I want conditional probability. Now that I'm seeing fog at the airport, now that the card is a red card, what is the probability there will be flight delay? Now that it's a red card, what is the probability it's a king? So what happened? Your base, which was earlier 52, it shrank to 26. Same way here. Now that I'm seeing fog at the airport, what is the probability the flight will get delayed? So the base becomes fog. And the numerator is this area. So probability of flight delay given fog, the conditional probability is this intersection area divided by the blue. So if this is red cards, this is red king, these are the other cards. So what is the probability of red king? It was 2 by 52. But now that I know it's a red card, that means this is not my base, this is my base. What is the probability it's a king? Numerator by denominator. Alright, all of you okay? Okay. Let's move further. I'm going to write this equation on one side and play around with this equation a bit. Caution, be ready to slip. So P A condition B, this I'm showing it here as P A intersection P by PB. A intersection B by PB. All of you okay? Can I rewrite this equation and rewrite this equation 1 as P A condition B into PB is equal to PA intersection B. Can I do this? Can I do this? All of you okay? Okay. Look at this PA intersection B. Does it make any difference whether I write this as PA intersection B or PB intersection A? Does it make any difference? Okay. If P intersection B is this, then PB intersection A, where the denominator, the numerator is changed and denominator is changed, it becomes PB given A into PA. Okay? I take this expression and I put it over here. So this conditional probability becomes P intersection B is PB given A into PA divided by PB. This is your Bayesian model. I'll tell you what it means. This is all algebra, but let's understand what it means. What is the probability of a person being diabetic given the conditions? So this is the class diabetic, non-diabetic. These are the independent variables, the BP, the plasma and all these things. So what is the probability a person is diabetic given the conditions? What Mr. Bayesian said is, instead of building models, go back to your data, from your data pull out all those records where people were diabetic. How many of them had these conditions? This is called likelihood ratio. Go back to your data, from the data pull out all the diabetic cases, how many of them had this condition? So instead of building models, do this, likelihood ratio. Multiply that with what is the probability of anybody in the population having diabetes. So this is my base probability. What is the probability is rain today? 0% based on past experience, and this is that probability. Recalibrate this using this likelihood ratio. What is the probability of red king? 2 by 52. We modified that into 1 by 13. That is recalibration. That is what this numerator is doing. So this is called likelihood ratio. Prior knowledge, you already have knowledge about this ratio in the universe. And this is called evidence. I'm seeing this occurring. Given that it's a red, I'm seeing that occurring. This is evidence. So the argument which Mr. Bayes put is very simple. He did this 200 years ago. He said that instead of trying to build a model for this, go back into data, pull out all the cases which satisfy the condition, which are diabetic, belonging to that class. How many of them had this conditions which you're seeing today? That's all to this model. So this model, this is called likelihood. This is called prior. This is called evidence. And whatever you come out with, this is called posterior. And we do this in common sense. I'll give an experiment to you. Are you all ready? We actually use Naive in our day-to-day life. Lakshmi, is it going to be male or female?
Lakshmi Kant is
Lakshmi is the evidence now. Is going to male or female? So what you're doing is you're going back to the past. How many times you have come across this name where it was a female versus where it was a male? So you're pulling out all the past Lakshmis that you have in your mind. How many of them were males, females? In how many of that's Bayesian probability. I have a friend called Lakshmi Narayan Babu. And this one particular name I'll not forget because there was one class which I was supposed to attend and the class was being taken by Lakshmi. Every door I opened, there is a male standing there. Every door I opened, there was a male standing there. So it took me some time to understand that this guy's name was Lakshmi. So I did a wrong interpretation. Lakshmi means female, but there are people, males with name of Lakshmi. Right? So what you've done to answer this question is Bayesian probability. Right? So it all looks strange, but we all use it day-to-day life. Shall we move on? Okay. Any questions on this? Yeah, this one will give you that. That reminds me. Okay. So before I move on, when you read about these algorithms in books and articles, you need to be slightly careful. So let me explain what the problem is. So what happens is, what is the probability of A given B is equal to probability of B given A into P A by PB. All right. Many of the authors, okay. What is the probability of not A given B? So whatever this probability is, 1 minus P A given B. Okay. So this I can write it as, all of you understand what I'm doing? Probability of A given B, probability of king given red. What is the probability of not king given red? That's what we are doing here. So this I can write it as P B given A into P A by PB, which can be further written as PB by PB. Agreed? All of you okay? So whether you're finding probability of A given B or not A, I'll put it as like this, not A given B, both of them have in the denominator PB. So it is not PB which is going to decide whether this is going to be class A or class B. What is going to decide whether it's going to be class A or class B is the numerator. The numerator. If this crosses 0.5, he's going to belong to class A. If this crosses 0.5, he's going to belong to not class A. Get my point? So what decides your class is the numerator, not the denominator. Denominator is same in both. So many of the authors, they don't reflect this. They say that this is the Bayesian model. And you will keep wondering, where did the PB go? So the reason why they don't show PB is that it's the numerator which decides the class. However, in case you want not the classes but the probability values, then you'll have to divide by PB. All right? And the reason why they don't show PB, they often say that PB is a constant. What the hell? What do you mean by PB is a constant? PB is a constant. Some people say that since this is an evidence has already occurred, this is 1. Probability of an event which has already occurred is 1. So they use that argument also. But the argument is, mathematically, for classification, PB is not important, so it's not shown. All of you okay? Okay.
In this diabetes, so the PB of A is doesn't go in diabetes, what?
given the evidence, given what you see.
EA is already.
Sorry.
What is PA in this?
This is, anyway, how many people in the population are diabetic? Yeah. No, diabetic. Which symptoms we don't know. In the population, how many are diabetic? What percentage? That is this PA. How many are diabetic with these symptoms? Likelihood ratios. Okay. Now I'll go back to the slides which I jumped, or should I go forward? Just 1 second, let me check. Yeah, I'll go forward and then go backward. So I have a data set. This data set is 100 records. You see 100 in the bottom right. Total number of records is 100. Of this 100 records, 80 records no flight delay, 20 records flight delay. That's what I showed you in the Venn diagram. Okay. 20 times when there was flight delay, I noticed 4 times there was fog at the airport, 16 times no fog at the airport. This is that overlap between fog and flight. I also noticed that 80 times when there was no flight delay, 79 times there was no fog, 1 time there was fog. This is the same Venn diagram which you saw earlier. Okay, if you are getting confused, this area is no flight delay, no fog. This area is fog, no flight delay. This is 1 time which is occurring in my case. Yeah, this the blue left out region is no flight delay. No flight delay and fog. This crescent which you see here is this one. No flight delay and fog is this. This is the crescent. Okay. We convert this into ratios. 4 by 20, 16 by 20, 1 by 80, 79 by 80. We convert into ratios, the likelihood ratios. Now, once you convert into ratios, you can use any permutation combination to find the probability. This is what we have seen earlier. Okay, you can put those ratios over here and you see the calculations. Okay, what I want to show you is I can extend this argument. I can extend this argument to include multiple parameters. Once again, I have only 100 records. 80 times no flight delay, 20 times flight delay. Okay, and these are the various events which I have captured from the past. These are my attributes. So 20 times when there was flight delay, 4 times there was fog at the airport, 10 times there was technical snag. Oh, what is this? Oh, this, okay. Yeah, 0 times there was pilot fatigue. Okay, so these are all my observations which I convert into likelihood ratios. Keep in mind, these don't have to total up to 20. They can be overlapping regions in the Venn diagrams. They don't have to total up to 20. What I mean is, in the Venn diagrams, these regions might be overlapping each other. Okay? So I convert everything into likelihood ratios. Now look at this. Probability that flight will be delayed, given that I am observing fog at the airport, but no technical snag reported. How do you find the probability that when I see these 2 events occurring? Use the formula, treat the event of flight delay as A and the combined event as B. So it's again probability of A given B. Okay, PA given B is nothing but probability of flight delay given these 2 conditions. You know how to handle this. It becomes PB given A into PA. You're going back into your records and seeing how many times flight delay happened, how many times these 2 events occurred together in that records. That is what this expression is.
So the likelihood is B given A, right?
Yeah, likelihood ratio. Table, correct. Likelihood ratio. So PB given A, B is a compound event right now. So P given A is this. PA continues to be PA. That's nice. Who did that? Okay, divided by probability of B, PV. So you can form any permutation combination of these events and substitute into this equation over here, the likelihood ratios, and it'll tell you the probability. What is the probability of flight delay now that you're observing these events? So you can keep on recalibrating your probabilities. Forget flight delay. What is the probability of an intrusion, network intrusion, given that I'm seeing this IP, I'm seeing this login ID from this particular geographical location? So you keep on recalibrating your probability values. The moment you see such events in the log files, the moment the probability value crosses a threshold, you send your alarm. Right? But there is a problem. We have time, so we'll discuss the problem. What is the probability of flight delay given fog at the airport and say buffaloes grazing on the runway? I don't have any data about buffaloes grazing on the runway. So this algorithm will give you the probability is 0. Okay, this comes from experience. Earlier in Delhi, we used to have Palam Airport. Palam Airport had no boundary. So you can see a lot of buffaloes coming from the villages and grazing sitting on the runway, right? So what is the probability of flight delay given fog and buffalo at the runway? The algorithm will give you 0 because you don't have any such information with you. So for that, we use something called Laplace smoothing factor. So Laplace smoothing factor sounds very hi-fi, but it's actually adding one small to the numerator, adding one small 0.0005, a very small number. You're free to add any number you like. This very small number prevents the numerator from becoming 0. When those rare events occur, for which you don't have data. Okay? Since the event is very rare, we give it a very low value. There's a lot of technical discussions behind this, but this is called Laplace smoothing factor. By default, it's a very small value of 0.00005. Any outlier, any event comes in the test record, which you have never seen before. So at that time, the probability should not become 0. It's a probability very low value. That low value comes because numerator is very low. So any rare event for which you don't have any training data, when it occurs, this expression will become 0. But this will prevent it from the numerator from becoming 0. So the probability value will be conditional probability will be very low. Generally, it's a prefixed constant, but you can change it if you like. Any other question on this? Shall I go back to the slides which we jumped? Now those slides which earlier looked like hieroglyphics now will make sense to you. So this is where we jumped. Is it okay? So posterior probability is this, which you're trying to find out. Not prior, this is my likelihood ratios. It's also called conditional probability. I mean, this can also be called conditional probability, but this is posterior, this is likelihood, this is prior, this is my evidence. Some books, some authors will reflect it like this, but it means the same thing. So the class that will assign to a test record will be whether this numerator is greater or this numerator is greater than 0.5. That is called argmax. Okay, so whichever numerator is higher, accordingly the class will be assigned to the test label. So that is indicated by this. The technical name that we use for comparing the numerators are argmax. Which one is maximum, higher?
You've been whether PB is greater or PA is greater.
Now, whether this numerator, and there was one more numerator here, right?
1 minus.
Oh, okay.
So let me rewrite the numerator here. So this is PB minus PE given B.
No, B given.
Correct.
It's opposite.
1 minus, no. So this will be 1 minus P A given B is this, given A into P A by P B. So what this will become P B, and this whole thing will become P B. So now argmax compares this with this, whichever is greater than 0.5, that class will be assigned to the test label. Then important thing, too much of words, but let me tell you in a brief way, because this algorithm assumes all these different events to be independent of each other, they don't influence each other. In probability theory, you would have seen when events are independent of each other, we multiply their probabilities. See, I told you. So when events are independent of each other, we multiply those events. Remember that in probability theory? So in the base, since the events are independent of each other, we multiply these events. What I mean by this is, look at this example. Look at this example. This is my numerator, this is my denominator. Probability of fog, no technical snack. Probability of fog, no pilot fatigue, no passenger delay. If you want to find all those things out, just take individual probabilities and multiply each other out. Right? I'm not showing multiple things over here, but you can just multiply the individual probabilities over here to find the PB. B is the condition. So in diabetic case, it was this represents blood pressure, it represents plasma, it represents something else. So I can say numerator, where I'm using it, what is the probability of your diabetes given blood pressure? What is the probability of diabetes given plasma into what is the probability of diabetes given this, that? So just multiply those events because they are independent events. That is what the numerator will become, right? Same thing is shown. You will come across this expression. Don't get scared with this. This is what it means.
The same equation we will repeat for each of the.
Yeah, each of the attributes. Multiply.
Class.
Yeah, W is a class. Which class it belongs to? All right. There is actually a lot of depth and discussions on this, Bayesian probabilities, which I'm assuming you're done in statistics. I'm going to move to the hands-on. Before I go into hands-on, advantages, disadvantages. Just like your logistic, it's very fast both in training and testing. K nearest neighbor is very fast in training but very slow in testing, because it has to find so many distances to find the K nearest neighbors. Does well with noisy data is what you will see in many of these books and articles, but noisy data means there is a lot of jiggle in the universe from where you are taking the snapshots, which means 2 consecutive snapshots will have different distributions. Okay, so you have to take this with a pinch of salt. Any algorithm will find it difficult with noisy data sets. Requires few examples for training. Again, something which we need to actually take with a pinch of salt. As long as the few examples are a good representation of the universe, but otherwise no. We can convert our class into probabilities. Sometimes probability is useful. Predict underscore proba. So we make use of the probability, predict underscore proba, the probability values, to actually change the thresholds using binarized functions. Okay, we'll talk about that later. Biggest disadvantage is the assumption it makes, but then that is the assumption made by all the algorithms. When you have too many numerical variables, first it will convert these numerical variables into bins, boxes. Okay, it will categorize them, create bins, and then calculate the probabilities. People have said that the estimated probabilities, conditional probability, is usually less reliable. It's not reliable That is true because these probabilities, assumption is the attributes are independent of each other. But because attributes are not independent, these probabilities have to be further jacked up. That is the same problem that you saw in p-values. Between MPG and horsepower, if there is a relationship and there's a p-value, why should that p-value change when you use, along with horsepower, the weight of the car also? Both the coefficients and the p-values for the horsepower change when you add some more dimensions to your analysis. That happens because of the collinearity between horsepower and the weight column. So this is true for all the cases. Estimated probabilities are, so estimated coefficients are usually different from the coefficients in practice. If you come across a rare event, then the numerator can become 0, but we can handle this using that Laplace factor.
So one more regarding disadvantage. See, you are considering all the attributes. Say you have huge number of attributes. So will it be slightly slower these days because you are considering?
It will be relatively slower to less number of attributes. Yes, it will be, but it will not be visible to you. It will not be significantly different. However, you need to be aware of curse of dimensionality. You should be aware of curse of too many dimensions, too less records. Then this any algorithm can end up in curse of dimensionality. Shall we try this on the PIMA indents dataset? Okay. Okay. Before I proceed, in the UCI dataset, have you seen the UCI repository? To my knowledge, there are 512 datasets. Pretty rich source of data. I might cover in the class PIMA diabetes datasets, but nothing prevents you from going and building these models on the bankdata.csv, where you predict defaulters versus non-defaulters. Just go ahead and practice this. Don't worry about the accuracy and all. How do you tweak the accuracy to a further higher up level? That will deal in feature engineering model tuning. But first thing that you should do is get used to the libraries that you need to call. Second thing you need to learn is the basic syntax of scikit-learn. Third thing, by the time you become comfortable with all these things, then we can go into model tuning. Okay, so that will bring in continuity in your, I know many of you are on jobs, you'll find it difficult for the continuity to be there. This is one way of ensuring continuity. Yes, sir.
Why was not suitable
It's a ratio, so the ratios will have to be, first it will have to bind. Do you know that even decision tree does that? When you use it for classification, it has to bind. So if I have an attribute called plasma, it will bind first, equidistant bins will be created. So if you have too many numerical variables, it will take time to do that. But however, we will not see all these things because we have today modern computers which are very fast, powerful. This algorithm was 200 years ago.
But the problem was with slowness, not with the accuracy.
No.
It was only with the performance.
Performance.
So decision tree also making conditions.
They are all under the hood. They are all related. Decision tree also creates based on entropy and Gini index, the homogeneity. That is another way of maximizing Bayesian properties.
So the question was different. We are testing this condition, decision tree.
Yeah.
These also make use of conditional probabilities.
They are conditional probabilities. Absolutely. What is the probability of class A given income is this, age is this, and this is that? That is what the path is. Yeah, they are using a different loss function. So all algorithms do the same thing in different ways. If you understand this, you will not have problem in learning any algorithms. So decision tree is all the conditional probability. The path is the condition. Based on the condition, what is the probability of finding this class?
I don't know whether it's rigorous or not. Can we do like that? Let's say 0, 1, 0, 1 we have. Can we predict whether the next value will be 0 or the next value will be 1?
What do you mean by that?
And
this is the sequence, like regression follows the sequence. What is the pattern of the data?
Yeah.
In that way, it says, let's say the next value will be, there might be a possibility that the next value will be something, whatever. Can we do it that way? Like, let's say we see 1, 0, 0, 1, 0, 0, 1. Okay, this is the pattern going on in some data, and we will run a prediction model. Can we predict the next value?
Predict what's the next value going to be?
Seeing the pattern of the whole. Like in 10th or 12th exam, we see 8, 2, 8, 9. There is a pattern inside, let's say. Can we do it that way?
Only if you see a pattern, you can build models. If you don't see any patterns, you can't build models. He brings me back to one more very core issue, very core point that you need to be aware of. We build models only when, this process P, it takes as input something and output, okay? This output that it generates, this output should be, usually it's, say if it's a numerical value, it should have some kind of a distribution. The distribution will have a central value and some spread and so on and so forth, the characteristics of distribution, okay? Only when you have well-behaved, well-defined processes like this, whose outputs have some well-defined shape in terms of the central values and the spread, only then we can build models to represent this process. If the output of this process is going to be random in nature, we don't know what it's going to be. Sometimes it's 10, sometimes it's 40, sometimes 9, random outputs. We cannot build a model to represent this. You can build models only for those processes which are well-defined processes. So coming to your requirement, if the output, the 1, 0, 0, 1, 0, whatever you're seeing, it's an output of some process. If the process is outputting this in some patterns, the pattern could be in form of Gaussian distribution, so on and so forth, only then you can build a model to represent that process and predict what's next value going to be with some confidence levels. You can't model a random process. If that 1, 0, 0, 1 and all is coming out randomly, then you can't build any model. Yes?
You understand what is the PA with condition A, right? The standard formula is called. So now we are actually calculating PAB by putting PBA condition. So yeah, we are getting an output, but what is the need of doing that? Is it that previous numerator values is not calculatable or?
No, you are depending on past data. What is the probability of now a patient walking into my dispensary? I want to classify him as, does he have benign or malignant, cancerous or non-cancerous? Instead of building a model which is where input is the attributes of the patient and building a model to predict that, go back into your data set of the past patients, those who were cancerous, how many of them had these conditions? If majority of them had these conditions, then likely this guy is going to be cancerous. If the past data shows that amongst cancerous patient, this kind of attributes was very low, then maybe he will not be a cancer. So I flip the argument and go back to my past data and see what is the likelihood ratio given the past.
We can do same thing in this Prima case because here also what we are saying is.
That's what you're going to do, correct? That's what you're doing here. That's what you're doing. So shall I get in the hands-on? Okay. It's the same data set. So all of you know what the problem is. Okay, we have the wine data sets, this thing, but we can do this on, would you like to take this as homework? Apply this Naive-Bayes algorithm on PIMA data sets and see what is the result. You have to give me overall accuracy and class level accuracy. Right, all of you okay? Would you like to give it a shot? Okay, then let's go through this wine data set. Naive-Bayes wine. Okay, this data set has come from Italian wine brewery, wine farm. Okay, this is a real data set. Apparently, there are 3 different.
Wine data set, we don't have it. We don't have wine data set, that wine.csv.
You don't have data set?
Yeah.
Okay. Don't worry, I'll pass it on to you. It's there on the pen drive, she'll pass it on to you. This is wine.csv, not red. But you can try it on red also, it doesn't matter. They're the same, this thing. Source is the same. All right, now the requirement is there are apparently 3 different classes of winemakers. Okay, and the situation is the way the wines are classified. I wonder if you people know how it's classified. You have specialized, skilled people who actually taste the wine and they give the classification, the quality of the wine. Yeah. So this is one of the most unenviable jobs, or rather enviable jobs, where you get paid for drinking on the job, right? So the requirement is, can you build using data science a model which takes as input the various parameters of the wine, and it tells you what the class of the wine is going to be. So I can replace these people with automated systems. That is the objective, okay? So if you look at the data set, these are the columns available in the data, which I have noted from that UCI data set. The cultivator, alcohol levels, malic acid, ash, alkalinity. Honestly, I have no idea about these things, but these are the various parameters available. So when I load this data set and do a df describe once again is used to identify the tails. Look at any of these columns. We'll just look at one. Take your, okay, look at this, interesting. Look at the cultivator is a categorical variable, so don't look at that. Look at alcohol. Mean is 13, median is 13. Malic acid, mean is 2.3, it's almost 2. Ash, 2.3, 2.3. Alkalinity, 19.49, 19.5, almost same. So every attribute, the mean and median are almost coinciding. So there is that, to that extent we are safe. Look at the tails. This tail is, sorry, start with this. This is almost 1 unit. Yeah, it's 1 unit, and the left hand side tail is also 1 unit. This is 2 units. This is almost 2 units. This is 2.5 to 3.5 units. This is 1.3 to 2.2, almost 5 plus units, 0.7 units. Every dimension, mean and median are coinciding, and the tails on the both sides are almost equal size. So looks like most of the dimensions, there is not much long tails or skews. Only one dimension you will see, which is magnesium. Mean is 99, this is 98, a difference of only 1 unit. Central value is no problem. Look at the tails. 10 units. Sorry, this is 18 units. 18 units versus 55, 54 units. Yeah, this tail is very long compared to the left hand side tail. So this is when your central values are overlapping, 98 versus your 99, central values are overlapping, very small shift. That means you have only a few outliers, very few outliers on the right side. Otherwise, the mean would have been drastically pulled to the right side. So 1 or 2 records seem to have outliers on that one particular dimension.
So should we go ahead and do
all outliers have to be handled.
And then means like
replace them with some different values. Dropping records is the last option. You may have to, but it's last option. The visual way of seeing this is pair panel, and this is the pair panel. I'll come back to this code. I'm looking at the data types here. But I'll come back to the code. Look at the distributions, and I want you to compare this distribution with Pima distribution. So let's compare this with Pima, okay? There are 3 classes and hence 3 curves. And look at these curves. They are overlapping. They are overlapping, but you see the difference? What is the difference? Central values are separated apart. The means are not overlapping. And that makes a huge difference in your ability to distinguish the classes. In Pima, the problem was even the central values are sitting on each other. So the body is significantly overlapping, but central values are separate. So we are in a better condition than we were in Pima. Look at this column. The blue and the orange are overlapping, even the central values are overlapping. But at least the green is away. So all the columns, this is, I think this is the worst column we have. This is in your data sets, where all the 3 columns are absolutely sitting on top of each other. This one. And this is ash. Okay. Ash, all the columns, all the classes are sitting on top of each other, including the central values. However, because I have other attributes which can help me segregate, I can ignore this. Right? There you go. So in many of the dimensions, 2 classes are overlapping, but as long as the third one is away. So this is what I was saying. If you have a dimension in which the 2 classes are significantly overlapping, small change in shift, but when I combine this with another dimension, the 2 Gaussians, they become linearly separable. So I'm seeing this distribution this way, I'm seeing this kind of overlap. I'll redo this. I'm seeing this kind of overlap. When I use another dimension, in the other dimension also I'm seeing an overlap. But when I put them together, in that mathematical space, the 2 Gaussians become linearly separable. Because of that, linear separability now possible amongst the classes on the dimensions. Look at this dimension. This one, I don't know which one is this. This one is not going to help you separate the orange from the blue. Doesn't matter as long as I have this dimension with me, which separates orange from the blues. So one dimension will compensate for the other dimension. So overall, these weak predictors put together become strong predictors. Exactly. Overall, these weak predictors put together become strong predictors, and as you will notice when you go down the line, let's look at the data types. We don't have any non-numerical columns here. Everything is numerical. Keep in mind, all algorithms need numerical columns only. Numerical columns could be categorical or real numbers. Come down. So I'm separating out the X variables, independent variables. The target is the cultivator. I'm splitting my data into training set, test set. I'm splitting my data into training set, test set. Yeah, all of you with me on this? Okay. You can actually download the dataset from UCI if you wish to. This dataset you can download from UCI and run the code. Very good. I'm instantiating the Gaussian Naive here. There are different variants of Naive. This Naive assumes that the dimensions are Gaussian on each one of these, the distributions are Gaussian on each one of the dimension, and we meet that requirement very well. On all the dimensions, the classes are distributed in almost Gaussian ways. Gaussian means looks like normal distribution. So a perfect case for Gaussian Naive. So I'm calling Gaussian Naive here. There are other variants like multinomial Naive and other Naive which you can make use of. So I'm instantiating the model here. I'm going to do the model fit here. This is where our Naive likelihood ratios will be calculated. And then I look at this. On the training set itself, I'm doing a testing. It's giving me 97% accuracy. Why am I doing this? I'll tell you in a minute. While I can also do this model on the test data. Here I'm running the model on the test data. Okay. And in metrics, there is a function called classification report, which gives me all these metrics, recall, precision, everything in one shot. If you're interested, you can separately print the matrix also, confusion matrix. Now look at this confusion matrix. Look at this. Look at the class level recall. Look at the class level recall. Any problems? Hey, Mohli, any problems? From SQL and import Gaussian. Okay. All right. Now look at this. There are 3 classes here, 1 to 3. And look at the class level recall. What is class level recall? Accuracy at class levels. Almost 100%. 1 means 100. 95%, 100%. So each one of the classes, it's able to accurately classify with a degree of, this is what we wanted in PIMA diabetes. It's giving us accuracy in a wine data set. Okay, I'll talk about this micro average and all these things down the line. We'll talk about this later. Right now, just look at this recall matrix. I've not told you what precision is. And look at the confusion matrix. Actual number of class A in your test record is 23. All of them have been classified as class A. Actual number of records for class B in your test data is 19. It has correctly classified 18. 12, it has correctly classified 12. You are able to achieve this kind of a score in this model, even though the dimensions are overlapping, the classes are overlapping on all the dimensions, because of some dimensions which come together to make strong predictors. So you should understand the difference between PIMA diabetes and this. In both the cases, the classes are overlapping, but there's one very important critical difference. And it's that difference which is making this. Right? So you can run the same algorithm, Naive, on PIMA diabetes and see what is the score you get there. Your job here is to select the right attributes.
But here we are not taking all in.
That this is, you will never get data on a plate when you're doing real life projects. This is only classroom. But when you do sit down and do real life projects, your customer says, suppose a simple example, can you use data science to improve my customer CSAT rating from the current 3.5 to 4.5 out of 5? Can you do something using data science to help me improve my customer rating in my technical support? These are the kind of requirements which will come to you. Data will never come to you. So now your job is CSAT rating, customer rating for technical support. What kind of data you need? Not decide. You have to first guess what kind of data I need. Your domain expertise will help you. If you don't have it, you'll need to have domain experts. So for CSAT rating in customer tech support, what kind of data I'll need? Can somebody go back to the past tickets? Okay, go back to the past ticket. What kind of data you need? Go back to the past tickets. From the past tickets, you collect what kind of ticket, P1, P2, P3 tickets. I need to find ticket classes. Then whether the ticket belong to hardware, software, or something else, I need those things. And various other, you will decide what kind of data you need. The next challenge will be, where will you get the data from? Some data will be available within the organization. Some data will be available outside the organization. Some data will be available with the customer. So getting these stakeholders to give the data to us will be such a challenge. So all your soft skills will come into play. Right? So once the data comes in, you have to first establish the reliability of the data. What if the tech support department has given you data where customer is very happy? They have not shared with you the dirty data. Your model will go for a toss. Those are the challenges which you will face as a data scientist. Once the data comes to you on those various attributes that you have, you will do this analysis using pair plot and other techniques. Is this column good or that column good? Which column should I use to define customer satisfaction? I come from the IT world just like you do, many of you do. We people have done a lot of projects in Java and C and all those things. The project starts with customer requirements, which we turn into technical requirements, that we turn into design requirements, that turns into code specs, coding requirements, that turns into unit testing, integration testing, and finally, then we go for acceptance testing. In acceptance testing, usually it bombs, right? The reason why it bombs is we look at data only in the last stage. Where we come to acceptance testing, we ask customers to give us some data. In data science projects, your project will start with data, the project will end with data. Data is the core, you will be revolving around the data sets. So 80% of your effort, estimated effort in data science project, you will see that when you do the capstone project, will go in getting the data itself.
So it's usually start with data-driven approach and end with data-driven.
100%.
And end with data-telling stories.
Yes, 100%. Visualization and storytelling from the data. That is what data science is.
So in between that data analysis.
In between the data analysis, feature engineering, feature selections, model tuning, all these things come in. Hey, so please don't make this assumption. In this hands-on exercise we are doing in the class, you're getting all the data from, right? This will not happen in real world. That's why when people come and do capstone projects, many of them want to do self-driving cars. So we have to take them out separately and tell them, hold on. At least a decade of research has gone into building those self-driving cars. You can't do it in 4 months. So when you come to capstone project stage, you're very far away from that. Please sell it to capstone projects with care. Right, guys? Okay. What I'm going to show you is one more thing. Okay. Though this is kind of doing very too early in this for you, but still let me do it. When you build these models, okay, we need to understand how the model is likely to perform in production. Because I'm going to put the model into production, which means I'm going to disrupt many of the processes in production. So the stakeholders in production are going to ask me, what is the performance you expect from this model in production? Suppose somebody asks you this question, what is your answer? Okay, it completely matched with this, what I'm going to cover, because how do you prevent this from happening in production? So when somebody asks you this question, what is the performance you're likely to have in production? We never give point estimates. We never say my model is going to give 78% accuracy or 80%. We always give a range estimate. My model is likely to give me accuracy between 80% to 95%. The moment you give range, that means you're not 100% sure. The moment you're not 100% sure, statistically you're supposed to associate with a confidence level. How confident are you in this range? So usually the confidence level is measured at 95%. So we give a confidence level of 95%. 95% confident that my model is going to give me accuracy between X and Y. But to be able to do those things, find the 95% confidence level for your estimates, we use a technique called bootstrap sampling. In statistics, it is known as sampling with replacements. Okay, and we also use a technique called k-fold cross-validations. So I'm showing you this k-fold cross-validation, what it means, but we'll do this in detail down the line. Look at this. From scikit-learn, import cross-validation score and cross-validation predict. These two functions are available already. Let me explain to you first what is cross-validation. I have this data set with me. Okay, suppose k-fold CV, that which I'm going to use, k stands for an integer number, just like k nearest neighbors, an integer number. Suppose I say k is equal to 10. Usually we take 10. as reliable. What it's going to do is, it's going to break your data into 10 pieces, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. It's going to break your data into 10 equal pieces. Then what it's going to do is, for I equal to 1 to 10, where I is an index, I equal to 1, 2, 3, 4, 10. For I is equal to 1 to 10, fit using 9, test or predict using the left out. So first time when I is 1, it'll take some 9 data sets, do the fit, and it will test on the left out. Then when I becomes 2, it will take some other 9, maybe this 9, do the fit and do the left out. Then it will take some other 9, do the fit, left out. It will do this 10 times because you have taken 10, k is equal to 10. Because you have taken k is equal to 10, it's going to break your data into 10 pieces, train on 9, test on 1. And it will do this 10 times. Train on different 9s each time, test on a different left out each time. When you do this on this particular data set, so I have imported these two. Cross-val score, I have supplied the model to it, the model which I built up, the training set test label, and CV is 10. When I do this, look at the scores I'm getting. First run, it gave me overall score of 92.8. Second run gave me 92.8. Third run, it gave me 1, 1, 92.3, 92. This is all the scores you have got. Average of all these scores is 96.12. So you can expect your model in production on average to give you 96% accuracy. However, we want to give a range. To get the range, you can find out this distribution, 95% confidence level of this distribution, or resort to bootstrap sample. We'll talk about that later in detail, right? So we make use of this technique to find out overall how the performance is going to be in production. 96% average accuracy score I can expect from this model on this data set.
In this model, when we do model scores, we did train set and train
yes.
Right? And we got accuracy of 97%.
On the
train set. But do you think this accuracy is not correct? Because we have.
No, I'll tell you why we did that. No, we did subsequently testing also we did. Look at the line, we have done on testing also. Okay, why did I do the evaluation on training and testing? Let me tell you this, okay? With that we'll wind up. This is a very important point, and you should learn this trick now itself, and if you reflect all these things in your projects, it'll be good. Oh, there it is, okay. Remember we talked about overfit, underfit? Okay, what is underfit? How do you define underfit? Huh? Sorry? Loosely coupled with less dimension. Straight line, curve line, what the hell, hey boss? What is going on? Using what? I want to reach a sweet spot. On the left side is low, underfit. On the right side is overfit. But how will it know whether a model is underfit or overfit? Okay. Guys, let's. Very good, thank you. Huh? Hey, no, enough. Underfit is that case where in training set, accuracy is very high. Okay? I'm sorry, accuracy is very low, and in test set also accuracy is very low. Overfit is that case where in training accuracy is very high and testing accuracy is very low. All right. Right fit, this is overfit. Right fit is that case where training accuracy is equal to, more or less equal to, test accuracy. All right. So if I plot a graph of errors, okay, and this is my complexity, then you will see that my training error comes to 0. Especially decision tree will give you training error 0. But this is my training error. I call it training error, TRAINING error. As my complexity increases, training error comes to 0. But you will see that this is my complexity, okay, I'm increasing complexity in this direction. You will see that the test error is usually higher than the training error. It also comes down, but after some time it deviates back up. You'll notice that the test error also comes down to some point. After that it backs up, it peaks up. This difference, okay, this difference where the training error starts deviating back up, you should stop here. Below this, it's underfit. Above this, it's overfit. In this situation, your model has absorbed all the noise in the training set and become very complex. And when you take that model on the test data, it bombs. Error is very high on test data. Okay? So this point is what you want to check. So whenever you build model, run the model both on training set and test set. If on training set and test set, training is 80% accuracy, test set is 60% accuracy, you are in this region. If training set and test set, both of them are similar to each other with very few difference here and there, then you are probably in this region. Training is also poor, testing is also poor, you are in this region. Underfit region. Oof. So much to discuss. I know it becomes a bit of overwhelming with so much of information coming in such a short span of time. It'll take time, don't worry about it. Take time, take your own time to sink all this in and keep practicing on the UCI datasets. But don't get miscarried by the UCI datasets, as Birendra pointed out. In reality, you'll never get such datasets readily available. Never. If you get, you have to suspect it. Okay? That reality will hit you when you do the capstone project itself. The idea is to teach you that reality. All right. So I'm going to stop here. I'm done for the day. Any questions, feel free to shoot. We're stopping a bit early today. But yeah, that's, yes.
You explain the pair plot and what are the inferences we can do?
Pair plot? Yeah, sure, why not? We can do that. For this data set? Okay.
Actually, I have done this project based on that
Scores have gone down, right? Overall, what is accuracy? Overall accuracy. Yeah, that is what is 76.
Overall 74, the training set is 74.
That's okay. 74, 76, that means it's an underfit region. Both of them are very close to each other. And class level accuracy, diabetes class, recall, what is the recall? Hey, diabetics class, 88. 62 for diabetic class is 62. 55% and 62% is a big jump actually. It's a big jump. So for diabetic class, this NIBASE is doing well because, can you tell me why NIBASE is doing well for the diabetic class?
You told multiple, if it's overlapping, maybe the different attributes can be
Weaker or weaker will go.
In diabetic class, in PIMA diabetes data set, you notice that there were 3 attributes on which there was a very small separation between orange and the blue on the 3 dimensions. those weak predictors are helping the Nye-Bayes algorithm over there. Right? So the lesson that we have from this is, which we'll revisit tomorrow anyway, given data set and given problem statement, we never rely on one single algorithm. We always build multiple models. Each model might be different algorithm, and then we average out. That concept is called stacking. If you use the same algorithm multiple instances, that we call ensemble. So in production, we always put an ensemble or a stack, and the ensemble or a stack will give you a much more reliable result than individual instances will. Okay, let's move on. So let's see this pair plot. There you go. For always first look at the diagonals. Okay. In the diagonals, the first column is the category, the target column. So we can ignore this. This is category of the 3 cultivators, people who cultivate. The next column is the alcohol. Look at the diagonals. This is alcohol versus alcohol. So it makes no sense to give you scatter plot here. So instead, they have given you density distribution on the alcohol dimension. Since we have used this hue color, which means give me separate colors for separate classes, it's showing you the 3 classes. And what is coming out of this is, between classes there is overlap. But fortunately, the central values of these classes, they are not overlapping.
So that is basically alcohol versus cultivator.
No, this is alcohol versus alcohol. This is just distribution of the classes on alcohol, univariate. This analysis is univariate analysis. It's not comparing the dimensions.
But we are given U is equal to cultivator.
So it's giving you a distribution of cultivators from class 1, class 2, class 3 on this dimension. How the values of alcohol for class 1 is distributed, how it is for class 2, how it is for class 3. So what this is telling us is the alcohol dimension can be used to separate out the 3 classes. Okay, go to the next one. If you observe carefully, malic acid, what it's saying is the class 1 is distributed like this, the class 1 malic acids are distributed like this, class 2 malic acids are distributed like this, and class 3 is the green one. What we are seeing is outliers here. For the blue class, on this particular dimension, there seem to be outliers. You see a small bulge over here. Similarly for orange. Also we are seeing bulge. The problem we are seeing for the green one, there seems to be huge range on both sides. Yeah. So green one also seems to be having some extreme values on both sides. That's why the distribution itself is stretched out. So I have to go back to the records and see on this malic acid for each class, what is the problem? What are these outliers and need to deal with it? But right now, in the raw form, the green stands out separately from the orange and the blue. But the orange and the blue class are overlapping. So this dimension may be very useful in separating out greens, but may not be very good in separating out orange and blues. This dimension is your ash. It's relatively the most useless dimension in this set.
Malic acid, if you have the outlier, suppose if you take the outlier, so you have very less spread. So it means that it's a very good predictor for the blue this data.
No, the predictive power base is the predictive power is a function of how cleanly these separate out the distributions. The predictive power of a dimension is a function of how cleanly these distributions are separate out. Suppose there was no blue class. This is a very good dimension to separate orange from the green. If suppose there was no green class, this is a weak predictor for orange and blue. This ash, it's a very weak predictor for all 3 of them. Okay. This alkalinity, if you see, if you look at, if suppose the blue class was not there, then we are in Pima diabetes case. But at least it's a good separator for green and blue. right? So individual dimensions may be weak predictors, but when I put them together, they might be able to segregate the three classes properly. And that is what is happening in the data set. You asked the question, right? How to interpret this? That's what we're doing. The scatter plot makes no sense because we are not building any linear models here. Okay. So scatter plot I'm not referring. So diagonals is important for us. Any other question?
Based on this, we can drop the variables which are less important, right?
100%. So, but maybe by dropping that ash dimension and reducing the curse of dimensionality, I might be able to get more than 96%.
So if you drop the ash and again rebuild the model, you will get more.
I don't know. I've never done that, but you should try it. Maybe you will get it. Handling the outliers might help you in classifying, because outliers, hey guys, all of you this side please. All of you this side. This is a Gaussian naive Bayes. Gaussian naive Bayes expects your data to be distributed like this. But wherever your data distributed like this, if you handle these outliers, you might get better results, right? So if you handle the outliers, both logistic and naive Bayes will give you better results. Because outliers increase log loss in your logistic. So if you handle outliers, both logistic and naive Bayes will give you good results.
But if the cost will come after like one standard
Treat it means? You're talking outliers. Okay. Don't remove the outlier. Don't drop the records as much as possible. Unless you're lucky guy, you're given terabytes of data. Right? So usually you'll find yourself in a situation where we don't have the luxury of dropping the records.
But in case of breast cancer and all, we don't know the cell radius. If we replace it with median values or something, that's domain specific.
You have to take, yes, good point. You have to have the domain expert with you to tell you whether calculating the radius is prone to error or the perimeter is prone to error. Right? Because there is a strong relationship between perimeter and radius. That's why you're saying that. So it depends on the domain expertise you have. All right. Okay. There's one point which I wanted to say. Okay. This is called data leaks, and guys, with this I'm going to stop. I'll not go beyond this. Be careful about data leaks. I'll tell you what data leaks is. In your exams, if the question paper gets leaked out, obviously we'll score very high. Right? But we might not have the real knowledge with us. Same thing can happen in modeling. So in modeling, we break our data into training set, test set, right? And we build our model, model dot fit. We do this using training data. There are various ways in which the test data can leak into the fit function. One of the simplest way you can do this mistake is where you first take the data, you convert this data into z-score, and then you split this data into training set, test set, build your model on this. Why? Because z-score is xi minus x bar by standard deviation. Xi minus x bar by standard deviation is a z-score. This standard deviation is a result of all the records put together. Right? Now, when I break this data into z-score data into this, the test data has already been influenced by the training set. But the test data in no way should have been influenced by the training set. They are not independent of each other. This is a very common source of data leaks. In the classroom, it's okay, but you cannot do this in your projects. Then what will happen is, your model will perform well on test, but it will bomb in production. That is one very common way of data leaks. So whenever you do transformation of your data from raw to this, if the transformation involves all records put together to find your standard deviation, something of that sort, don't do that. Always break your data into training set, test set first, then do the transformations.
I think we did this for this.
Which one?
First Python notebook which we did.
We'll do this mistake in entire all the Python notebooks. But you please be aware of this, don't do this in your projects. The second thing I'll tell. Second problem statement is, we talked about one-hot coding. We talked about one-hot coding, right? Look at this. You have in your data set a gender column which has male, 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 females, females, okay, males. Always convert the one-hot coding first so that it becomes gender male, gender female. This will become 101010010101. 10, okay? All of you got it? Then you break your data into training set, test set. This is okay. Training, test. The reason why this is okay is, this record has not been influenced by any other records. The records don't influence each other. The transformation of records from here to here is independent of other records. So this is okay. Okay. If you do this transformation after breaking your data into training set, test set. I told you in Z-score, you first break your data into training set, test set. Okay. Then first do Z-score on training, then do Z-score on testing separately. If you do this one-hot coding after breaking your data into training set, test set. Now I break this into training set, test set. What's going to happen is, in your training set, you're going to have only one column, GM, 111. In your test data, you're going to have two columns, GM and GF. This will be 010110. So your training data and your test data will not match in terms of the attributes. So whenever you're doing transformation, if the transformation is something which is done record-wise, do it first, then break your data into training set, test set, especially one-hot coding. Otherwise, you'll end up in runtime problems. If you're doing any transformation which involves all the records put together, like calculating standard deviations, then first split it, then transform it. Otherwise, your data will leak.
Here, the number of observations will get changed.
Second mistake is score.
Yes, yes, you are. The moment you add dimensions, you're going towards higher complexity of your models. So you're decreasing the bias error but increasing variance errors. So if you create one-hot coding out of a column where the cardinal values, the distinct values is 50, you're going to end up with 50 new columns. So imagine from lower dimensional space, you're going to such a high dimensional space, and your data points is also not very high. You'll end up with a very complex model. So you'll end up in overfit zone, variance errors.
So why we need this? We can still use 0, 1 as the value for...
Algorithm will think that 1 is greater than 0.
Here, if we have three categories, A, B, C, and we do level encoding first. So it will convert to 1, 2, 3. In this case, it might think that C is a higher priority than C.
It will.
So what will do? It will do one-hot encoding.
Yes.
Now it will convert to 0, 0, 1, 0, 1, 0 as per the sequence. So in this case, if we drop one of the variables, the variance will also decrease, and we can predict that if it's 0, 0, then maybe that variable will be 1. Yeah. So we can use that way also to reduce.
Yeah. Okay. One last point. Last test point. This we have been saying since last 3 points. whenever you create one-hot coding, for example, in this case, you're creating collinear columns, columns which influence each other. The presence of 0 here tells me that this column will be 1. So I'm able to predict the value of the other column based on this column. So you're introducing collinearity over here. To address this collinearity problem, when you create one-hot coding, we might drop one of the columns. So 0 means male, 1 means female. So I get that information from here itself. I don't need this. So when you do one-hot coding, you're introducing multicollinearity. When you bring multicollinearity, you know what problems exist, what problems happen, you know that. So we might have to drop some of these one-hot coding columns to remove the multicollinearity. We do that.
Again, we have 0, 1. Again, same issue. One is
And the purpose of one-hot coding is?
One-hot coding does not introduce any order. It just stores it as a label, 0 and 1.
So we can also convert the gender column as the category column and 0.
Unfortunately, when you do that, when you use pandas data frame categorical function, it actually says that it is ordinal values. It has order in it. Discuss the steps and then we'll move on. We'll use a new data set on which I'll run KNN, regressor, then linear regressor, and we'll compare the two. See, unsupervised learning methods, okay. There are two broad categories of algorithms. One is called supervised methods, one is called unsupervised methods. Supervised methods, we already know what it is. It is all those techniques put together where we create our models. Unsupervised techniques are all those methods that form an integral part of your exploratory data analytics. You don't actually build any models here. You make use of these techniques to understand what the data is telling you. And based on what the data is telling you, that will give you a head start, or that will give you the direction in which you should go while you're building your supervised models. So the value of unsupervised learning methods is in exploring your data and trying to find out, are there some interesting stories hidden in it? Stories, what do you mean by stories? I'll tell you in a minute. Okay. The two broad subcategories in unsupervised learning methods is clustering, and the other one is PCA, SVD, LDA, all these things, a family of techniques which are basically mathematical techniques which try to again give you some information hidden in your mathematical space amongst your data points. Okay? So I'm going to quickly go through this clustering methods. Now I'm going to go quickly. That doesn't mean you shouldn't ask questions. Okay. If conceptually something is not clear, just put a break on that. So clustering is primarily understanding whether in my data are there any kind of segments, are there any kind of clusters or groups. When I identify these groups, I will show you one particular application of this in one particular data set which you have already seen, that is called car-MPG datasets. What is the accuracy scores you got in the car-MPG datasets? Somewhere around 80, between 76 and 80. Best of the best model would have given you 76 to 80 in car-MPG.dataset. When you do the exploratory analytics on this using unsupervised methods and you discover the hidden structures inside, then you will realize why you are getting such a poor performance in these models, and what you could have done to increase the performance beyond 80%. That information will jump out at you when you apply clustering techniques to that particular data set. And the same thing can be done on any data set. It's not just this one. All right? So when you do your capstone projects, we expect you to do your unsupervised methods on your data sets first. Are there any hidden information in it? Can you make use of that and build your models based on that? Yesterday, I was attending a capstone project presentation in Chennai, where some of people were jumping into building models given the data set. That is not what you're supposed to do. In none of the presentations, I took 4 presentations. None of the presentations I came across anybody telling me what they did to find out whether there is any information hidden in the data. They just took the independent variables, dependent variables, started building the models. Don't do that. There might be some useful information hidden, which could help you create better models than what you have done right now. So that is the idea of unsupervised method. When you talk about clustering, we are looking for, are there any kind of groups such that within the groups, the data points are very similar to each other, but across the group, there is a lot of difference. The whole objective of clustering is, I want to find out clusters which are the tightest and the farthest in the mathematical space. When I find such clusters, and if they exist, that tells me that there are some records which are very similar to each other in your data frame, but they are very dissimilar from other set of records. Now the question is why? Why is it so? When you try to understand why is it so, that will give you insight into what kind of algorithm should be used, what kind of dimensions should be used to build the models for each one of them. You remember we did a credit.csv, a bank credit data set, where we're trying to predict a default or non-defaulter. We built one single model. You may not probably remember the accuracy scores of the defaulter class. I'm now into classification. In classification, if you remember, the accuracy score, overall accuracy score was very high, defaulter, non-defaulter. But within the defaulter class, the accuracy was very low. It was around 55-56%. When you're building classification models, right, that particular class of interest to me was the defaulter class, and on that particular class, the model was giving me 56% accuracy, overall was 76%. Why do you think that happened? We used all the algorithms, decision tree, Naive, logistic, we used all the algorithms. None of them giving good results on that particular class. Why? The reason why? You may not remember this. If you remember, the type of loans.
That was unbalanced data actually.
Unbalanced data, class imbalance, number of defaulters was half the number of non-defaulters. So there was a class imbalance, that is definitely a case. The other problem was the type of loans that people had applied for. Student loan, housing loan, then business loan, right? Furniture loans. I remember I asked you this question in the class. Do you think the characteristics of defaulter who's defaulted on business loan will be similar to the characteristics of defaulter who's defaulted on student loan? Should we be building one single model then? Clustering, if you had done it on that data set, would have brought out this difference to you. So instead of going down the path, building all the model and struggling with accuracy and then coming back, use clustering first, find out what is there in the data. If need be, build separate models for separate clusters. That is the objective of clustering. So that prevents you from wasting so much of time, effort, and energy. So we always use clustering as a lead into classification, or as a lead into modeling. Modeling can be classification or even regression. Shall we move on? Okay. Keep in mind, the clustering that we are going to start with is k-means clustering. Within clustering, he would have covered how many types of clustering techniques are there?
Right. K-means cover. Hierarchical is not.
Yeah, clustering, there are two types, flat, hierarchical. I use both. Flat clustering, we have k-means, and we have dbScan. I never use this, though it is used in social science and all those things. But in data science, we always end up using k-means or k-medoids and its variants. Hierarchical, we have agglomerative and divisive. Okay. A lot of research has gone into agglomerative techniques. Most of the implementation of hierarchical clustering you will see will be agglomerative, bottom up. I have not come across any implementation except in research papers of divisive. Divisive method is similar to your decision tree. In decision tree, the driving force is to reduce entropy or Gini. Here it is to reduce the variance. Okay, so methodology is same, approach is different. So we'll be looking at these two, k-means and this. All of you okay? So I'm going to start with k-means. The objective of k-means is to break your data or mathematical space into clusters indicated by C1 to Ck. K is number of clusters you look for. One of the biggest challenges in this technique is how do you know how many clusters to look for in the first place? K means clustering. K stands for a number. How many clusters should I look for? We'll talk about that. When you do this clustering, sum of all these clusters, union of all these clusters gives you back the entire data set. Your data set has 1 to n data points, has 1 to n number of records. This we call data frame D. This data frame, when you put it into a clustering algorithm, it converts into mathematical space. In the mathematical space, it finds clusters. Union of all these clusters will give back the data frame to you. Any two clusters, the intersection of the two clusters will be 0, which means these clusters don't overlap. Which means every data point in your data frame is assigned to only one cluster. It can't be assigned to two clusters. So if this is my mathematical space, if I have multiple clusters here, no two clusters will overlap. The boundaries might touch, but one data point will not belong to more than one cluster. That is a property of your k-means clustering. Why am I telling you all these things? The reason I'm telling you all these things is when you do k-means clustering, you have to be very careful. It's actually very easy to implement, but very difficult to get results from. Very difficult to get the results out of k-means clustering. It requires a lot of expertise to use this. The reason I'm telling you this is our objective is whatever clusters are found in our mathematical space, feature space, our objective is we should minimize within cluster variance. So my cluster should be as compact and as tight as possible. That is what will reduce the within. W stands for within. Within cluster variance, I want to minimize this. They should be as tight as possible, right? Now take this class example. This is a two-dimensional mathematical space. In this two-dimensional mathematical space, if I go for two clusters, I have one cluster sitting there, other cluster sitting here, right? If we do a variance of this cluster, the total variance of this mathematical space is going to remain constant. Whatever it is, it's going to be constant, right? Suppose I ask for two clusters, I get 1, 1. Instead, if I had asked for 3 clusters, then this would have formed one cluster, this would have formed one cluster, then the variance in that cluster plus variance in this cluster, variance in this cluster would have reduced. So when I draw a bigger boundary, to make a loose cluster, I'm adding variance into my clusters. So I want to go to that situation where the sum of the variances of data points within a cluster, when I total it up across all the k clusters put together, they're minimized. So if I go for 4 clusters, 1, 2, 3, 4, that will give me even tighter clusters because there's a gap here between the clusters on these 2 dimensions. Why do you want this? I want tightest clusters which are farthest from each other. When you find such clusters, they tell you that, okay, for certain range of values on x and y, I have these people. For certain range of values on x and y, I have these people. So why is that there's a gap between these people on these 2 dimensions? What causes the gap? Why the data points are not continuously scattered in my mathematical space? Why are they coming together? Why are they gravitating towards some centroids? If I explore that and find out, that will throw out richer information to me. But the problem is, I don't know how many clusters are there. I can't see it. I have 50 dimensions and thousands of records, millions of records. How do you know how many clusters are there? So unless and until I find the tightest and the farthest clusters, I will not be able to make any meaningful information out of the clustering. and all the effort will go waste. And worst, it might give you misleading information. It might even give you misleading information, take you in completely wrong direction. So this particular technique has to be implemented with great care, and it might require a lot of iterations. And these formulas, don't get hassled by these formulas. These formulas you already know. There's a variance formula, xi minus x bar raised to power 2. Remember variance formula? What is variance formula? Xi minus x bar raised to power 2. If you want average variance, divide by n. Same way, same thing, where this Ck is number of data points in the cluster. Okay? So what this is telling you is, what this particular formula is telling you is, the variance, if you take a cluster 1, what is the variance in that cluster? If you take cluster k is equal to 2, what is the variance in the cluster? That's what it's telling you, xi minus x bar. How does it find out? Simple. Say if these are the data points in this cluster, project it down. They have whatever the values are here, do sum of all and divide by n. You get the x bar. This is my centroid on this axis. So you find out xi minus x bar raised to power 2 by n, variance on this axis. Similarly, you find variance on this axis. So that gives you the cluster variance. So j is equal to 1 to p. P is parameters. Parameters are dimensions. So on every dimension, to find out the variance, sum it up, that gives you the cluster variance. So the optimization problem for us is, this is variance within a cluster. I have k clusters. So for k is equal to 1 to k, I want to minimize the variance within the clusters. I want to form my clusters in such a way that the variances, sum of all the variances across the clusters, they minimize it. That is the optimization problem. This is the driving force behind clustering. So k-means clustering, what it does is, it iterates through your mathematical space, builds clusters, removes them, builds clusters, remove them, until it reaches the point where this is minimized. That is a metric to decide the quality of a model. But what is a learning algorithm in linear regression? Gradient descent algorithm in linear models, right? Similarly, in this, the driving force is to minimize or optimize this function. However, there's a problem here. I'll tell you what the problem is. Okay, we'll see the problem. So more concept. If I indicate now the variance of all the data points in the class, you're all data points. Okay, you're not going to move. You're going to remain where you are. So I can calculate a variance on x-axis and the y-axis. I can project you onto the x-axis, all of you. I can project all of you onto y-axis. I can find out x bar over here, y bar over there. I can calculate the variance on the x-axis and the variance on the y-axis. So that variance of the entire class remains fixed. That is a property of your mathematical space given the data set. That variance is called T. Let's call it total variance. Let's call it total variance. Okay. Now, within cluster variance, we know if I break my data into this mathematical space into two clusters, one cluster here, one cluster there, I can find out the variance within clusters, right? So that is called variance within cluster, W, that is shown as WC. Variance between clusters. The center of gravity of this cluster was the center of gravity of that cluster, xi minus x bar, raised to power 2. Divided by n, n is number of clusters. That is your between cluster variance. Now, can you understand that total variance will be sum of within cluster variance and between cluster variance?
So all the clusters and cluster A, B, C, D.
Between clusters is, yeah, all the clusters put together, what is the variance between? Treat each cluster as one data point. So this is one data point, this is one data point, this is one data point. Okay, the data point is nothing but the center of gravity of those clusters, the centroids. What is the variance between them? So find out their x bars, xi minus x bar raised to power 2 by n. That will be between cluster variance. Hey, did you get it? Okay, great. I heard a voice here.
We are trying to minimize the within cluster area.
Yeah, yes. Now watch this. Come on.
I think I just wanted to tell you that it's not like a pairwise. It's like A and B. It's not pairwise.
Okay, let me repeat that again. Suppose we have gone for 2 clusters or 3 clusters. Okay, 1 cluster, 2 cluster, 3 cluster. There is a centroid for every cluster. Okay, project the centroid on the x-axis. Project the centroids on the y-axis. Calculate the variance between these centroids on x-axis variance. That is between cluster variance. Okay. All right. Now, why am I telling you all these things again? Our objective is to minimize WC within cluster variance. We want those to be as tight as possible. So if you look at the formula, to minimize this, T is a constant. You can't do anything. T is a constant. It's a variance within your data set. So to minimize this, I have to maximize this magnitude-wise. Magnitude-wise, as BC increases, WC will go down. So either you look for tightening the clusters or maximizing the distance between the clusters. Both of them will achieve the same thing. Unfortunately, both this, whether you want to find the tightest cluster or farthest clusters, both these approaches, they don't have a well-defined algorithm. They belong to a class of problems in mathematics called NP-hard problems. Non-deterministic, polynomial time problems. They don't have any well-defined solutions, which means if I want to find out the 3 best clusters, let's assume there are supposed to be 3 clusters in my dataset based on domain knowledge. But if I want to find out the 3 best clusters in my dataset, there is no algorithm which will find that best 3 clusters for me. K-means clustering belongs to NP-hard family of problems which don't have a solution. So K-means clusterings, they usually end up in local minimas. And that's what causes problems. If you're not aware of this, and you go ahead and do your clustering, you might completely go in the wrong direction and all our alternate hypotheses may be misleading. So this technique has to be used with great care, and a lot of thought process has to go into this. Which dimensions should I include in my clusters? Right? We'll see how to kind of tackle these problems, but nothing is guaranteed here. So I might end up with suboptimal solutions. The biggest problem is if I give you 30 dimensions and 1,000 records or 10,000 records, whatever it is, the first problem is, how do I know how many clusters to look for? Once I know that, then I can talk about where those clusters are. So how do I even find out how many clusters are there likely to be there? Right? So that's what makes this a challenging technique. But the technique itself, if done properly, can throw out a lot of rich information at you. So let's move. It's used in various places. You probably have already seen this. Applications are plenty, clustering. The most common application of clustering is anomaly detection. Anomaly detection is basically outlier detections. You swipe your credit cards, many times you would have got a message, did you make this transaction? There is a clustering running for you. All your past behavior, transactions done on the credit card, have been accumulated by the service provider, and it has been mapped to your clusters, which cluster you belong to. And now you make a transaction where the data point somehow is not falling within the cluster. It is far away from the centroid of your cluster.
But anyway, that data point will be grouped into one of the clusters. No?
It will be, but it will be far away from the centroid more.
How do you identify that?
It's an outlier.
No, how do you identify that as an outlier?
You have already got a cluster from your training set. It has a centroid. You already know the variance. That means you know the standard deviation. A new query point comes in which is closest to this center. A new query point comes in. but the query point lies 1.96 standard deviations away from the centroid, then that query point is an outlier for that cluster. Mukesh Rao is doing this transaction, card number is known. So Mukesh Rao's cluster I know, but he's lying more than 2 standard deviations away.
But let us not forget that there are outliers in the clusters already.
Outliers are marked as suspect. They may not be suspect. That's why they ask you, you did the transaction. All right, let's move. 2 broad categories, I'll take you both of them. I'll take you through both of them, hierarchical and this. The beauty of hierarchical techniques is beauty and danger point both. It's dangerous as well. Is that it shows you the internal structures in a visual way. Okay. So before we start talking about clustering, hierarchical or non-hierarchical, before we start talking about clustering, how do you decide which points are similar in nature, which points are not similar to each other? So there has to be a way of measuring similarity, right? There are different ways of measuring similarity. Those different ways of measuring similarity, they're called distance functions. Yeah.
Sir, I have one question regarding this anomaly detection. So let's say when I'm creating the model, so I will treat the outlier also. I need to treat the outlier for any kind of modeling most of the time.
That is in your training set. We have put it into production. Now in the production, a query point is coming in, which is 1.96 standard deviations away from the centroid. Suspect.
No, so in training, I have already treated my outlier. So maybe that was available in my training set, but I have treated. Okay, now if something is coming, but my past behavior, it was there, but I had treated. So I mean, it is little...
Yeah, you're right. Good point. What she's saying is, maybe this outlier which you're seeing here has already occurred in the past, was there in your training set also, but the data scientist thought it was an outlier, he handled the outlier, he did something. No, that's why my answer to that question, both of you, is it's question mark, it's a suspect. I'm not saying it's fraudulent, I'm saying it's a suspect. The reason why you handle the outliers in the first place is that point should not be there. That's why you handled it, right? So it's a suspect. That's why they ask you, did you do this transaction? If yes, then it's all right. You go to your Gmail, go to your this thing, what do you call the place where you go and do your computers? Cyber Cafe. Go to Cyber Cafe, which I never visited, open your Gmail account, it will immediately send you a mail. You'll immediately get a mail, suspect, right? So that is anomaly detection. Okay, so we need a way to find out the similarity and dissimilarity between. So we use the distance calculation methods, and you probably have already seen this. This is your Euclidean norm. Only thing, please keep in mind, k-means clustering supports only Euclidean. It doesn't support any other methodology. No Manhattan, no Jaccard, no Mahalanobis, nothing. K-means clustering supports only Euclidean. Because k-means clustering uses the concepts of centroids. Centroids is a concept borrowed from the world of Euclidean space. Okay, Euclidean space means flat and homogeneous space. So we can talk only about Euclidean distance when we talk about k-means clustering. All right, and all of you know what Euclidean distance is. Shall we move on? Okay. Only thing is, before we move on, keep in mind Euclidean distance is xi minus x bar, or x1 minus x2 minus x1 raised to power 2. Isn't this variance? x2 minus x1 raised to power 2, isn't this some kind of a variance? Variance on x-axis plus variance on y-axis. Keep this in mind. Other Euclidean, non-Euclidean distances are available, which are used in hierarchical clustering, but not in k-means. When you're using Euclidean, we need to be slightly careful here. It is impacted by the scale that you're using on each dimensions. So many times you'll be advised to convert all your dimension to z-scores or some kind of scales to remove the units. The technique is a safe technique, no doubt, but sometimes it can have an adverse effect. Instead of giving you good clusters, it can end up giving you bad clusters. Scaling. So when do you scale, when do you not scale is a very important thing that you need to be aware of. The reason why we ask to scale is those dimensions which are larger scale, they tend to overwhelm the calculations of the distance. Right? So if suppose this was a larger scale than this one, then the total distance calculation will be more impacted by this scale, this dimension than this dimension. That is why we convert them into z-scores or some other scaling, normalized. But I will advise you a caution here because I'll show you down the line what can happen if you do scaling in the wrong place.
Actually, even if we do the z-score, if the x values are all very small compared to the y values.
So when you convert as z-scores, then all of them become z-scores. They all become same units, same length.
Because we have done it on the z, on the x and y separately.
Exactly.
My question is, so we have the data which is transformed to z-score. So after transformation, we are finding out the centroid.
Okay.
So that centroid is not equal to the centroid of the original data set centroid.
Okay, just hold on. All of you heard the question? What is your answer? This will need a drawing. So we have two axes, okay? These two axes right now are raw dimensions. They have not been scaled. They have not been scaled, they're raw dimensions. Let's call this, say, age, and this is some, say, income, something of that sort. Sorry, I can't think of any other right now. Creativity is very limited. Given these two dimensions, or any two dimensions, his question is, if I do clustering on the raw dimensions, okay, I might get clusters where the centroids of the clusters are this and this. Suppose I'm looking for two clusters. And when I scale it, when I convert into z-scores, then he says the centroids that I might find in this space will be different from this centroids.
Mathematically, it will be different, but it's a property of shift of origin actually. So it will just shift.
So when you convert into z-scores, this one and this one, the formula is xi minus x bar by standard deviation. Yeah, this is the formula. So this is the formula for this, yi minus y bar by standard deviation of y. This is the formula for this, x. Right? When you do this, essentially what you're doing is you are shifting your data points to the center. So this is my data points. All these are my data points here. These are my data points. Project them over here. So these data points, the x bar suppose is this point. This line is my x bar. And these data points, when you project it on the y-axis, this is my y bar. This is my x bar. So xi minus x bar, these will become positives, these will become negatives. Yi minus y bars, these will be positives, it will be negatives. So what you're essentially doing is, you're shifting your origin to the center of the mathematical space. This is what z-score does. So now in this new mathematical space, your centroids in terms of z values, definitely they're different, but their position in the mathematical space remains the same. So instead of measuring height in meters, we are measuring height in feet, something of that sort. So physically they are the same, though the measurements change, the units change. Your question?
My question is, so let's say for example, I have got one transaction, which is that I want to find out the anomaly.
Yeah.
So for that also I will have to treat the same way, and then only I can do that.
Okay.
So every time I go to the transformed data and do the analysis.
Yes.
So, but when I look at the data for the analysis purpose or EDA, so I wanted to have the reverse transform. Then only I can look at the data and find out what are the findings, all those things and all that. Because when transform data, it is only useful for me to do the modeling, not for any other purpose. Because that will mislead many times because of actually, the transformed in nature. So that's what we spoke while back.
So when we are transforming here, please keep in mind, we are not changing any kind of distributions, nothing. We are not changing any distribution, nothing. We are just measuring it using different scales. That's all we are doing. However, when I put this into production, a new query point comes in, it has to undergo the same transformation when you have to build anomaly models. However, when I'm doing EDA, exploratory data analytics, I always do it on the raw data. I always do it on the raw data first, and that's where I am telling you this point is valid over there. Many times you'll be advised to convert your raw data into scaled data before you do new clustering. I want to demonstrate to you here today that you need to be careful there. You can't do it blindly. Many times when you scale your data, your clusters might go wrong. A lot of times in the raw data, we have attributes which naturally lead to clustering. They naturally bring in some kind of clustering on them. And by scaling those dimensions, we dilute the clusters there. The natural tendency for clustering on that dimension is diluted when you actually scale it. So let's see what happens. So when you talk about clustering, we'll talk about a way of measuring the similarity, dissimilarity between 2 points, xi and xj. Xi and xi dash on the jth dimension, j is the dimension, xi is 1 point, xi dash is another point. You can call it x1, x2 if you like, right? So we need to have a distance calculation method. Fortunately, when you're using when you're using hierarchical, when you're using k-means clustering, only Euclidean distance is allowed here. So this is what I was telling, impact of normalization. You'll always be told this. You will always be told to normalize it, but what I'm saying is be careful. Look at this. I generated some data, and then on that data I played around with it. I'll share the code with you. It's simple stuff. This is my data set where I have created some data points. We can visually see there are 2 clusters, but actually we won't know how many clusters are there. Right now in this case, visually we are seeing 2 clusters. On these 2 clusters, when I run my k-means clustering, without doing any normalization on the raw data, the 2 clusters I get are the red and the blue. As you can see, that is misleading clusters. When I normalize my data, look at the scales. This is z-scored. Look at the difference here. Look at the difference here. This is z-scored. It gives me the right clusters. Are you able to see the difference? However, look at this distribution. Here also we see 2 natural clusters. When I don't normalize it, I get the 2 natural clusters. When I normalize my data here using z-score again, look, do you see the change in clusters? They're diffusing. So whether you should normalize or not, it depends on your understanding of the distributions of the data on the dimensions which you're using for clustering. Somehow, unfortunately, most of the articles, books, authors I come across, they all suggest that you normalize your data. Agreed, most of the time it works, but not always.
Yes, so here it's not clearly understanding, like this is, like in second example, yes, how we know this is correct or.
That's what I'm saying. That's what I'm saying. You'll actually have to, don't take that thing that normalization will lead you to good clustering. Not necessary. It might lead you to poor clustering.
But when we can decide, like if you have categorical data, some columns, those.
No. It is how the data is distributed on the various dimensions. For example, here the data distribution on this dimension, what is the difference of this dimension and this dimension on this clustering? Can somebody quickly tell me what is the difference you're seeing here in terms of the quality of the dimensions to create clusters? This is a poor dimension for clustering. It is unable to segregate the 2 clusters. Compared to this dimension or this attribute is able to segregate the 2 clusters. So in your pair panel, in the diagonal, you'll see 2 Gaussians in this dimension, whereas in this dimension, you'll see only 1 Gaussian. When you have 2 dimensions, on both of them, you're able to see clusters, 2 Gaussians separated out in the pair panel, you need to be careful. Should we be applying z-score there or not? Right? So it depends on your analysis of the data. There's no straitjacket answer to your question. Your understanding of the data on the various dimensions is very important.
So one of the example in last external lab we were having, where car and van and those is already given. We know this is the 3 cluster we have. So normally those type of data we have to remove those and then to check. Or so if my example is like in my data itself, I am seeing some categorical data which is already giving me hit. This is the so how to that time?
So they gave the target variable actually. We did some analysis, but while doing the clustering, we removed it actually just to understand. But still, what are the clusters we got? It is actually not matching the target variable. There's a lot of difference between the target variable values versus what the clusters have formed actually.
So those type of data, how to replace what?
In fact, when you're doing clustering, there is no concept of independent and target variables. All dimensions are equal. Okay. However, if I'm very clear that there is a categorical variable which is going to act as my target variable in supervised learning methods, I should remove it because I really want to understand the relationship between dimensions, independent dimensions. Are there any clusters on those dimensions? I need to remove them. Otherwise, the target variable will influence your clusters.
That's what we have done.
No. In addition to that question, same question onto. So actually, there is a data point which is classifying as car, but the moment we do the clustering, it has become a bus. But the actual count of car, bus, and other thing van is the same. So the data point has moved to some other.
Okay. The reason for such things happen. In fact, this is a very valuable analysis. Where with including the target column, the clustering, without the target column, the clustering, the clusters are coming out different. The reason why this happens is noise in the data. The reason why this happens is there are probably some outliers in the data sets which are not handled. In the clustering where you included the target variables influenced the cluster creation, so everything was fine. But when you removed it, the outliers are pushed into another cluster. Now they belong to this cluster.
But in the same question, what happens that the K value, we don't know, I got it, but in that question, it was told that there are 2 cars. We were given a set of cars, and they were told that there are only 2 groups. But when you apply K-means, that elbow method, it would come about 3 or 4 categories.
Four.
So because it's given that there are only 2 groups, then K-means is giving us 4. That was
there was 3 actually.
No, actually there were 3, but when you draw the K-means, that elbow graph, it is showing 4, but we can't apply 4 because already the target variable is defined as 3.
So we try to force fit like a 3 and say how it is. That's what we are doing. Actually, it's not the same. So we have to force fit for having the 3.
We are forced to take only 3.
Right. You're talking about AutoMPG data set.
Yes.
Because I remember seeing this elbow.
Vehicle, bus, car, and van.
Yeah. Okay. You're talking about that data set. In that data set, the difference between 3 and 4, we know there are 3 categories: mini, sedan, and large cars.
Right? Here it is car, bus, van.
So this is a clustering example where
car, bus, van.
They have bus, they have car, and they have van. But they have 3 categories. But they told that in car there are 2 more groups like Saab 9000 and one was Opel Manta.
Oh my God! What is all this?
So they wanted to segregate that among cars. What are those 2 categories are?
Okay.
Which one is Opel and which one is Saab?
Okay. So finally, what's the question?
The question is that K means gives us that there are more categories, but business as per business there are less categories. So how we can then
that means there are some subcategories hidden inside one of the larger categories. Though your business says there are 3 categories, what it means is inside one of the 3 at least there is some subcategories over there. So that is where you should apply your hierarchical clustering and see what are the subcategories. Are they valuable enough to be treated as separate clusters? The one cluster. Yeah. You can do that also. So you're free to explore, but this answer to this particular question is You have been told business-wise there are 3 categories, but K-means is telling there are 4 categories. That means one of the business categories has sub-clusters hidden in it. That's what it means.
Or maybe in our modeling we have done something spurious. That's why it's no.
This is a clear indication. K-means clustering, the elbow method, is a very good indicator of how many clusters are likely in your. Because scikit-learn implements what is called K-means plus plus. So K-means plus plus tries to overcome this problem of getting stuck in local minima. Now it is not guaranteed that it will not get stuck, it tries to. So that elbow method is quite reliable. And especially car-MPG datasets, I have seen this elbow, the elbow actually peaks or sharpens at 4. At 3 also there is a bend, but the 4 is larger bend. That's what I have noticed. So that's clear indication of subcategories hidden inside your larger categories. Shall we move on? Okay. So keep in mind, I've kept the code here. The code is there on shared on this. He will share it with Olympus. You try to play around with this code. Generate your own random sets and see how scaling can have negative impact on your clusters. Let's move on. When you're doing hierarchical clustering, the choice of distance matters. We'll see this in hierarchical clustering. The choice of the distance matters in the definition of clustering. In flat clustering, K-means there is no such option. We have only Euclidean distance. Knowledge of the distribution of the data is very important. The pair panel is very important for us, at least on the dimensions that we're going to include in our K-means clustering. We should know how the data is distributed, whether we should apply z-scores or not. Okay. All the attributes that we're going to use, unfortunately, we don't have, we call them independent attributes, but they're not really independent attributes. They're going to influence each other. So that impacts clustering also, quality of clustering. Yeah? So clusters, instead of become spherical, they become elongated. And K-means clustering assumes that all the clusters that you have are spherical clusters, Gaussians. We call them Gaussians. Yeah? The Euclidean distance is the most commonly used, and this is what we're going to use. It has its own limitations. Keep this in mind. We don't have any other option. Move on. Okay.
So, question again.
Yes, please.
Can we overwrite what is there in the scikit from an Euclidean standpoint? Because if there's a cosine similarity or what it is, can we overwrite something? Because they're showing some in the net like we can overwrite something.
Oh, people have written it, but scikit-learn doesn't give any option. I can't call a function.
That's what
hierarchical I can do that.
Okay.
Not in case. So the biggest challenge that you will face is how do you find out how many clusters are there in the first place. Suppose somehow you find it out, all the data points were allocated to so many clusters. Okay, final output of K-means will be, for every cluster you will get 3 things as output, 3 important properties. Every cluster, okay, has 3 important properties. The first property is the position of the centroid on the various dimensions. Cx1, this is cluster 1, C1. So I call it C1x, C1y. The position of the centroid you will get for the clusters. So you get the label. This is called cluster label. This is called, these two are called cluster centroids. C1x, C1y. And then you will get what is called inertia. Inertia is nothing but the variance inside the cluster, within cluster variance, W. Right? So every time you do clustering, for every cluster you will get 3 things. One is the centroids, one is the label, and the third one is the inertia of the cluster. Using these 3, we have to extract information. Computationally extremely intensive. K-means clustering is very intensive computationally, but once you clusters, we don't need the data points. So K-means clustering, once I find my clusters, suppose these are the 2 clusters, I don't need any of the data points in my mathematical space. I just need these 2 points. So I store these 2 points in an array along with the standard deviation. So I create an array. In this array, I store the two centroids, C1x, C1y, C2x, C2y, and I also store the standard deviation of 1 and standard deviation of 2. This is all I need to implement this in production. So in production, a new query point comes in. I find out what is the distance between these two. Which centroid is closest to this query point? And then suppose it's closest to this centroid. Is it within 1.96 or 2 standard deviations? If it is, then it's a normal data point. If it is not, it's a suspected data point. So when you build your clusters, once you've done that, all you need is the centroids and associated properties. And that's why in production, especially in real-time analytics, k-means clustering is often used.
If there was like the ones that come on the boundaries, if it was one of those points, it will still only consider C1x and C1y. Like it will only consider xy, not the standard deviation, because if it falls in the other standard deviation of 1.5, though it is farther from there, it's just a question. I don't know the answer.
No. Well, what you're asking is, correct me if wrong, what you're asking is...
It's closer to the other point, but falls in the standard deviation, and it's...
Good point. What he's asking is, there are two clusters, okay? The centroid of this is this, the center of this is this. Even though, how do I show this? Let's assume that means one of the clusters is loose clusters, something of that sort. Okay, it's a very big loose cluster. The centroid is here. Even though centroid, okay, let's do this. It's a loose cluster. Okay, one big large cluster and one small cluster, and a new query point has come in. The query point is very close to this centroid, but it is very far away in terms of standard deviations. That's what you're asking, right? So is this an outlier of this centroid? Or does this belong to this centroid? That's what you're asking. That's what you're asking. I'm asking you. Okay. Yeah, this can happen when your clusterings are not right. That is why we said in k-means clustering, the objective is tightest clusters and farthest clusters to avoid this situation. So when you're doing clustering, one of the things that we'll need to do is, as we will see in hierarchical clustering also, the cluster should be more or less of similar size. You should not have one large cluster and other satellite clusters. We call them satellite clusters. When you have such clustering, you will fall into this kind of problems.
Clustering can't be applied if this thing is happening.
Maybe the dimensions you used for clustering is not right. So that I'm not saying it cannot be applied. Maybe the dimensions we used are not right dimensions.
I think the car example, what we were telling previously, is the same problem.
Yes, it's because of this problem. I wonder whether you saw the cluster size over there. Did you measure how many records are in each cluster?
We have.
How many were there? Was there
Count is same compared to the actual classification.
Come again?
Count is same and compared to the actual classification done. But the problem is the car data point which was there, it was showing as a bus data point in classification.
That's clear indication of outlier not handled.
So actually in the car data set also, just a view in the sense that instead of doing only 3 clusters, if we actually made something, just an example, if you made 9 clusters, out of which 3 clusters, all 3 clusters belong to 3 different cars, is something that you'll find. Maybe it's like, 3. So if it belongs to any one of those clusters, that all the 3 sets actually belong to one categorical variable. That way also clusters work. Correct me if I'm wrong there.
That can happen. That's what hierarchical clustering tries to do.
No, on the k-means also you can actually...
You can do that, but instead of doing that, you can do a
subset. It looks like subset, but I think hierarchy is the right thing to look at. It's like a bigger circle and you have small circles within the bigger circle. It doesn't make sense actually.
Then you will fall into this trap.
You fall into the same thing.
Probably this is what has happened to your case also.
This will happen every time the magnitude of the axis is significantly different.
Yeah, exactly. When you don't scale it, there's guarantee.
That's where I was coming earlier, saying it will affect our distance because it's square root of x and y.
Absolutely. So when you don't do scaling, guaranteed you will come across this.
I'm talking even with scaling.
Because I had
Even with
earlier,
Z-scores also we have.
because at the end of the day,
Yes.
the magnitude
Spread,
will affect.
yes, spread on the original dimensions, yeah, definitely. That's why the outlier handling during clustering becomes important. Now I'm sure you're able to understand the gravity of the situation. Clustering is not a joke. It requires a lot of study analysis before you implement this technique. Otherwise, I'll completely mislead you. Car ka truck bana dega, truck ka car bana dega.
Probably after this center, we should go through that example one more time. The bus, car, van, just to understand in detail.
Can you show me what the example was?
We will. Let's go to that. I think last we'll go to that once actually. It's not clear yet.
I think I have a code on the RF and MPG. We'll see that. So this is clustering methodology. Okay. So your mathematical space, initially when you start, K means clustering. Suppose I say K is equal to 3. Why 3? No reason, it could have been 30. You'll start with some random 3 points in a mathematical space. Scikit-learn's K means plus plus. What it does is, since you ask for 3 clusters, it will generate 3 random numbers. 5 times. It will generate 3 random numbers 5 times. And of those 5 times, it will take those 3 random numbers which are farthest from each other. Because what some people have demonstrated is, when you start with initial centroids far away from each other, they generally converge to a good solution, not guaranteed optimal solution. Okay? So scikit-learn implements that. So imagine that these are the 3 centroids it has used in the first iteration. All the data points distance from these 3 centroids will be calculated, and they will be associated with the centroids which are closest to them. But as you can see, the centroids are not really centers, they are somewhere on the edge, so we need to recalculate the centroids. How do you recalculate centroids? Simple. You take the x bar of this red points, y bar of the red points, wherever they meet, that is the new centroid for red. Take x bar of the green, y bar of the green, wherever x bar, y bar of the green meet, that is a new centroid. Right, all of you? So the centroids shift, but when the centroid shifts, the data points on the edge, they change their groups. So they belong to a different cluster now. So that means the centroid calculation has to be done again. So this process keeps going on until the centroids either settle down, they don't move anymore, or their movement is minimal and the algorithm cuts the, cuts the loop, stops the loop. So we got 3 centroids, 3 clusters, sorry. So you'll, as I said over here, you will get 3 things from every cluster: the cluster label, the position of the centroid on the 2 axes, and the spread of the data points within the cluster, the variance, within cluster variance. These 3 will be reported to you for every cluster. And using these 3, you have to find out what the data is telling you. Let's move. Battery is dying out. The same logic, same algorithm which I showed you earlier. I've given it in text, same stuff. So the algorithm is guaranteed to decrease, the way this algorithm has been defined, it's called Lloyd's algorithm. It guarantees to decrease the within cluster variance in every iteration. It will change, it will decrease, that is guaranteed. But the only problem is, it's not guaranteed that it will find the best clusters. Any questions? Don't worry about the maths part. In case you want to go through this, let me know if you have any problems. All we are trying to do is minimize the variance within the cluster across all the clusters. Okay. That algorithm, if you actually see the algorithm steps over here, which is what I showed over here, the steps are taken in such a way that this is guaranteed to decrease in every iteration. It will. Okay. Right now, just ignore this part. This is a mathematical transformation of this. If you notice the difference over here, this is distance between 2 points. This is distance between points in the average of the cluster. Okay. Right now, I don't think we are in a state of mind where we can go through this. So please ignore this right now. Let's move on. Okay. So when you plot your elbow, same equation here, you'll see a bend. But unfortunately, in reality, in real life, many times we don't see a bend. We see a smooth curve. And we are looking at a very smooth function. We don't know where to stop, where the best K is. That can happen. That is where your hierarchical clustering becomes handy. So on the same data set, do both hierarchical and k-means. Hierarchical will give you a visual impact, visual impression of how many clusters are likely to be there. You take that as your k value, redo your clustering, see if you can interpret those clusters. Right? Whether a clustering is a good clustering or not, you'll come to know only when you start interpreting the clusters. What I do is, this is not, this is kind of a technique which I have not come across in any books or anything, but I find this technique useful. I use this. So when you do the pair plot, in the pair plot, you remember the diagonal? The diagonal can be KDE. KD is kernel density estimates. So I do a pair plot. In the pair plot, look at the diagonals. Okay. So if I have four attributes, look at the diagonal part. In the diagonal part, if you're seeing bulges like this, somewhere you're seeing two bulges, somewhere you're seeing multiple bulges, somewhere you're seeing only one. That indicates to you that in your data set, there are at least 3 clusters. How many are there? We don't know, but at least 3. What I do is, I multiply, suppose this is 3 and this is 2, I multiply 3 into 2, 6. Looks like at least there are 3 to 6, somewhere in that range clusters. Why? Look at this. When I look at the x dimension here on my diagonal, I will see 1 cluster. These 2 get eclipsed, 2 cluster and 3 clusters. When I look at from this side, y-axis, once again, I might see the small bulge. These 2 get eclipsed, and that cluster is visible as separate. So we have 4 clusters here, but we should not get misled by this. We should not assume that there are 4 clusters. We don't know. Suppose you have 2 dimensions, 1 cluster, 1 cluster. So when you look at it from here, you will see 2 Gaussians. When you look at it from here, you will see 2 Gaussians. That doesn't mean there are 4 Gaussians. Are you all with me? Okay. So visually, we can guess how many clusters, in what range should I explore those clusters. Of course, this dimension is useless for clustering. Absolutely. Right. Kernel density estimates, the word as it suggests, it's a density estimate. It's an estimate of the density distribution of this particular attribute in the universe. This may not be the density distribution of your data. Usually it will be. Sometimes you would have noticed, say for example in car data set itself, you do the pair panel. In car data set there is a car type, manual and automatic. It's a categorical variable. So you should, how can you get 2 Gaussians there? But you'll see 2 Gaussians there. Okay. The reason why that you see the Gaussians there is, this concept is called kernel density estimate. It is estimating the Gaussians from which your data has come. This is not your distribution. And the mathematical function used to estimate this Gaussian, that mathematical function is called kernels. Usually these kernels are Gaussian kernels. All right. So looking at this, we can guess how many clusters are likely to be there, and we can explore that number of clusters in our, k-means clustering. And what my analysis has shown with the limited data sets I've worked with on UCI, this is usually a good way to go ahead with clustering. Some implementation of clusterings, other than what we discussed, this is, we can also use clustering to keep an eye on, say, for example, customer segments, how the clusters change over time. Clusters will never be fixed. They will change with time. How frequently they change, that depends on your domain, what problem statement you're in. Okay. What we do is data points in 3 dimensions. Depending on the scales you're looking at, you'll get different number of clusters. Suppose I'm looking at this scale, I have clusters, well-defined cluster here. You'll never get clean clusters. You'll always get clusters like this, with a lot of data points scattered in between, loose clusters. Yeah.
We are taking 3 different columns. Is it?
3 dimensions. This one.
That we have one dimension. We have to keep changing and just check.
No. This is just for visual analysis. I made 3 dimensions. But the same thing can be done for n number of dimensions. But then the reports will come out in numbers, not visually. Okay. So you can actually track how the data points of importance to you, suppose these are your key customers, how the key customers over time, they're shifting from one cluster to other cluster. What direction they are moving in. If suppose I have cash cows are those customers who generate a lot of business for me frequently. And I'm seeing in the clustering mechanisms, those data points are shifting away towards other clusters, underdogs. Then I can do prevention strategies and make sure that they don't leave the clusters. So clustering is used for that also. In retail, it's used for customer segmentation and analysis. It's used for all these things. Yeah, but this is not part of our delivery. So we'll move on. The reason I'm showing you these things is when you're doing a capstone project, think about these things. Maybe you can bring all these things into your project. This is what I call dynamic clustering. You can use clustering to understand how data is shifting from one point to another point over a period of time. The biggest problem with clustering is, K means clustering is, how do you find the right number of K and where are those K data points? How do you find out? That's the biggest problem. It's an NP hard problem. There's no solution for this. So I'll have to iterate through many times before we find the most understandable clusters. Any questions on this? Shall we move on? AutoMPG dataset. This is what you're talking about. Must be that, must be same, because this is what I've used. Shall I go through this? Okay. How I used clustering on AutoMPG dataset. Let's see that. So let's start with this. This is called car-mpg.csv. Let me tell you what this car is. This dataset is about second-hand cars. Okay. These second-hand cars include cars from Europe, US, and Asia. The problem requirement was, can I, looking at the attributes of the car, the horsepower, the weight, the acceleration, and all these things, can I guess what the mileage of the car would be? And based on the mileage, I put a price tag on it. That is the object. Okay. But that is the objective for supervised learning method. So before we even do that, I want to explore the data and see what kind of information is hidden inside this, which I can make use of, leverage on to build my models, to predict the mileage. That is the object. So right now we are not going to build any models. We're just going to explore. All of you are aware of this. This linear regression is what my objective was. But when I built my linear regression on this model, on this data set, can I take the liberty of scrolling through? Okay. So when I built a linear model on this, all this is basic statistics, taking care of horsepower column. There are non-numeric values there. All these things is that. Come straight down. I can't see it from this angle. Okay. Now this is what I wanted to do. I did a clustering on this data set. Okay. But before I do the clustering, I was just analyzing my various dimensions on this data set. Have you seen this data set earlier? You have seen this data set earlier? Can you all please confirm you're aware of this data set? Yes, no? Okay, fine. So if you remember, in this data set, we had the MPG column, cylinder column, so on and so forth, right? This is what I was telling you. Look at the cylinder column. If you expand this, you'll see a Gaussian here. This is kernel density estimates. Now in this kernel density estimates, we are getting 3 clusters over here, 3 Gaussians. Of course, I have given the color based on one of the dimensions. I think it's called, I've given the color based on origin. Origin is the America, Asia, Europe, okay? So that is a natural cluster in the data set where cars from America, Europe and Asia, they form 3 clusters. So those 3 clusters are visible here, okay? And if you look at the dimensions, in some of the dimensions, you see more than 3 clusters. Within the blue cluster, within the blue, you are seeing 3 subcategories. This is what I was telling you. Within the category, there are subcategories which is visible here as overlapping each other. And these are the 2 clusters based on origin. Look at this. Within the red cluster, again, there are 2 subcategories on this dimension. So the number of clusters in your data set is not likely to be 3 in this particular data set. Okay, though naturally we think it should be 3, but when you club those data sets on the various attributes of the car, you might get more than 3. Right? Because we are seeing subclusters over here in those 3. Okay, let's move on. With this impression, I went and did my k-means clustering. In k-means clustering, I gave a range. I said, look for number of clusters 2 to 6. I guessed the range based on my analysis of the dimensions. So when I did this, based on the range, I created the clusters and found the inertia of the clusters, the sum of inertia. I did a plot, okay? The plot comes out like this, elbow plot. Are you all comfortable with elbow plot? I mean, how to make it, how to build it? Okay. Now look at this. This is what I was saying. Though naturally there are 3 clusters in the data set based on origin, the elbow plot is telling you something else. The elbow plot is telling you the drop in error in 4 clusters is much severe. You can't ignore this than in 3 clusters.
I think you've drawn X, Y.
Oh, this is my errors?
No, I think it is.
No, 27,000. That's 7,000.
Okay.
20%.
Okay, what are you talking about?
The scale.
Scale, okay.
1 to
Okay. Sorry, this is my error, inertia. This is number of clusters. Okay. So number of clusters here, though logically should have been 3 natural clusters, but what k-means clustering is telling us there are 4 clusters in your data set. Right? So we go and build our 4 clusters here. Look at this. So I'm going to build 4 clusters. And when I build the 4 clusters, look at the output. This is cluster 0 centroid, cluster 1 centroid, cluster 2 centroid, 3 centroid. Are you comfortable with this? All of you? What are these values? The position of the centroid in the various dimensions. That is what this is. Okay. So each row is 1 cluster, 0, 1, 2, 3. When I did this analysis, I put all these dimensions in your data frame, and so that it becomes easy to understand. So cluster 0, centroid is located on these attributes. Okay. When I did this, and then now look at this. What I'm doing here is, I'm taking the data sets back, all the original raw data, I'm taking it back, and I'm sending it to the cluster.predict. What this cluster.predict, it's deceptively like modeling. This is not modeling. This is not predicting anything. All the records, they are being assigned to different cluster IDs. K-means clustering has assigned it. Now I want to store back the cluster IDs back into the records itself. That's what is happening here. So in the data frame, we did not have any column called centroids. We did not have any column called centroids. Now, what this is going to do is it's going to create a column called group. In the group, it's going to store the cluster IDs. So I'm creating a new column called group. The group column will tell me which cluster this particular record belongs to. That is what the predict function is doing. It takes as input the records, tells you which cluster it belongs to.
So can you please explain elbow curve once again?
Yeah. In elbow curve, I should have actually labeled this. mistake. This is my inertia. Inertia means the sum of variances across within clusters all summed up. Okay. So this is my objective function. I want to minimize this. What you see on the bottom is the number of clusters. K is equal to 2, K is equal to 3. You can't have fractions. So K is equal to 2.
That is why actually I was confused. 2.5.
This 2.0 is it?
This is 2.0 because I gave the range as 2.
Okay. So this does a scale you have set like this, but it would be in the full 2,
Yeah.
3, 4 like that.
It can start from 1, but 1 will be the highest errors. Okay.
Okay, and 3 to 4, if I see then the shift is too much. I
Yeah.
mean, it's a significant shift.
Yes.
That is why we are going for 4.
Yeah. Even though in the pair panel we saw 3 natural clusters, but within a cluster we saw subclusters. That is what is coming out here. So 4 seems to be the likely number of clusters you should look for.
So you told, right? So by KD, we roughly can get idea this much of cluster here. So the range which you have given, accordingly you will
Yes. Shall we move on? Okay. Now look at this. I got my cluster ID stored inside the data frame. Now how do I make use of this? Okay. So what I did here is I stored back the cluster labels into the records. Which record belongs to which cluster label? Okay, that's what I'm doing at this point. Once I've done that, then I make use of my pair plot, make use of my box plot. So in the box plot, what I do is on every attribute, so if there are 8 attributes in this data set, on every attribute, I do a box plot by clusters. So when I do this, look at this. On the first dimension acceleration, there are 4 clusters with many outliers. You're all familiar with box plots. Okay. Now, whenever box plots are overlapping, the bodies of the box plot are overlapping, that's not a very good sign. It's not a good sign. You will not be able to interpret these 2 clusters separately. They will not come out as distinct clusters. They'll have similar properties. Okay. And because when you look at this dimension from this angle, this is acceleration z scored, you will see that there are 2 humps here. This is a separate hump, 2 humps, and this is a separate hump, 4 clusters. Okay, so not a good situation to be in, but let's move on. This is your cylinder. It's an integral column, so box plots is coming out as simple lines. This is displacement. Once again, the clusters are overlapping. It's not coming out very strongly as distinct clusters, right? Maybe it's a 4 clusters. If I restrict myself to 3 clusters, these 2 might get clubbed into 1. These might get clubbed into 1, and I might have distinct clusters. Even though k-means cluster is telling you 4 is the right number of clusters, right? Let's see. We don't know, but there are many outliers here. Outliers indicate loose clusters. Outliers indicate the data points lying on the edge of the clusters. They're making your clusters very large and loose. So we handle the outliers. I removed the outliers here. All I did is any data point which is lying beyond 2 standard deviations, there you go. I replaced it with a median. Go into your data frame, look at the records cluster wise, sort them cluster wise. Any data point which is lying more than 2 standard deviations within the cluster, replace it with the centroid of the cluster. That's what I'm doing here. When I do this, now when I form the box plot again, your outliers are almost gone with few outliers. Those of you are not probably familiar with this. I think I've told you this in the class. Whenever you have a distribution, and in the distribution you have data points in the outlying regions, you replace them with median, your distribution becomes sharper, your standard deviation falls. As a result of that, data points which are earlier not outliers, they start appearing as outliers. So you will never be able to completely eliminate the outliers. They will always be there. As long as I've handled the first iteration outliers, I'm okay. So I'm going to ignore the second iteration outliers. Okay. Now when you do this, look at your boxes. Again, the boxes are almost overlapping. These two are overlapping. These two are distinct from these two, right? So my box plot was not really helping me out with 3 or 4 clusters. Even 3 clusters had the same problem, which means the dimensions are not helping me separate out the clusters properly. What I did is, I went ahead and did an analysis using scatter plot. What I did is, I took one of the dimensions, say for example, horsepower. The target variable which I have to predict in my supervised method is MPG. So let's do a plot between MPG and horsepower and see what the scatter plot looks like in these 4 clusters. Now this is where the information will come out. Okay, look at this particular plot. What do you think this green cluster is? This is horsepower. So what do you think this green cluster is? What do you think this red cluster is? Green is large cars, heavy cars, very high horsepowers. These are probably your Maruti 800s, the small cars, very low horsepower. Mileage is very high, mileage is very low. All of you okay? Now look at this. What is coming out of this analysis is, when I look at the green cluster, your horsepower is not a very good predictor of your miles per gallon. The line is almost horizontal. The slope is almost 0. The slope is almost 0. In case in orange also, the slope is much worse. So your horsepower is not going to be good predictor for mileage for orange color cars. Orange cars is your sedans. Whereas if I go for small cars between horsepower and miles per gallon, there seems to be the kind of relationship I expect, a negative relationship and very strong coefficients. Are you able to get it? Do you understand how we are able to extract information out of clusters? Let's see this further. Look at this. This is your miles per gallon with displacement. Not as bad as in the earlier case, but once again for large car, this dimension is a weak predictor. But for small cars, it comes out to be very strong predictors. So when I'm building a model, instead of building one single model to predict the miles per gallon of all the cars put together, which is silly, I'll build separate models for small cars, separate for large cars. And when I build those models, I will not use the same attributes. The attributes I use to build linear model for large cars probably will be different from the attributes I use to build the model for the small cars. Right? And if you analyze this, one of the worst dimension is your acceleration. This is a horizontal, almost horizontal, and this fact comes out in the pair panel also. Acceleration is a useless column. So if you look at any value of acceleration, you'll find all the cars available. Large cars, small cars, every car is available. And if you look at the pair panel, in the pair panel, look at the acceleration column. Where is acceleration? This is acceleration? Where? This is acceleration. All the clusters are overlapping. So useless dimension. So k-means clustering, I'll show you one more example of how I used k-means clustering. This is for tech support analysis. I hope I have the data with me, the code with me. What I realized is I have to build individual models with different dimensions. So I was getting tempted to try out. This is a linear model. Somewhere down the line, support vector machine didn't help much. It gave me 87% only. I used decision tree. Linear regression, ridge and lasso, none of them helped. They're still giving performance in the range of 70s only. But decision tree came out to be better Oh, it's not there. I removed it. What an idiot. Decision tree gives me almost 90% accuracy in prediction. But looking at the output of this clustering on the various dimensions, I took a call that if I build a linear model, I have to build separate linear models. But if you want one single model, decision tree regressor came out to be the right fit. It gave me an accuracy of 90% almost on test data. You want to explore this? You want to try this out? Would you like to take this as a, yeah? Go and explore this. I have not built the linear models. Go and build the linear models on one cluster and see what their performance is. How it can be used in particular case study, it was used to suggest ideas for improvement of customer satisfaction on technical support. I realized I have overwritten that with another code, though the name of the file is still tech support analysis, but it is not tech support. So I'm going to share this code with you. Just walk through the code, you'll find it easy to understand. If you have followed me on the miles per gallon dataset, you'll be able to understand this particular example, okay? So shall we get into hierarchical clustering? Shall we look at hierarchical, all of you? K-means clustering, though very powerful, very commonly used technique, as you would have understood, it requires a lot of thought process, a lot of understanding of the data before you implement it. And one of the challenges of K-means is how do you know how many clusters to look for? That is where this hierarchical clustering becomes handy. Hierarchical clustering gives you a visual way of finding out how many clusters are likely to be there in your data. But at the same time, I must caution you, hierarchical clusters, though they may show visually some clusters in your data sets, those clusters may not exist. How encouraging. Those clusters may not exist really. Okay, so we need to be careful. There are ways of preventing ourselves from falling into such potholes. So we'll see how we can prevent ourselves from getting into these traps. What are the ways in which we can do it? But before I go there, in K-means clustering, you find the similarity or dissimilarity between data points, for which we use Euclidean distance. All of you comfortable with that? Okay. When you come to hierarchical clustering, what happens is we are going to see agglomerative, that is bottom up. Every record, every data point in your mathematical space is treated as a cluster. So in the next iteration, two of these clusters are coalesced, are joined together to form a larger cluster. Which cluster to join to form larger clusters, that is decided based on the distance between the clusters. Once again, the same rule applies. Closer the clusters are to one another, more similar they are. So I want to combine similar clusters into larger clusters. Okay, but the problem is, when you start looking for similarity between clusters, a cluster is no more a one single data point, it is a combination of data points. So the distance calculation between clusters to find out which are more similar to each other, that becomes slightly complex. It becomes complex because there are different ways of doing it. So the different ways of doing it is shown here. One is called single linkage or minimum linkage. Imagine you have three clusters, blue cluster here, yellow cluster and red cluster. Okay. Now I want to find out which two clusters are closest to each other. What this single linkage method does is it finds out the distance between 2 points which are from different clusters and nearest. So it finds out the distance between red and yellow, red and blue, yellow and blue. Of the three, red and yellow, this distance is the least. So it combines red with yellow. This is called single linkage method. If I look at max linkage, it finds out the distance between the farthest points from the different clusters. Red and yellow, red and blue, yellow and blue. And it takes the one which is least farthest. always it will take the least. Once again, it might combine yellow and red. Or average distance. Average distance is pairwise distance between all the data points here and all the data points there and their average. Do this amongst red and yellow cluster, red and blue cluster, yellow and blue cluster. Combine those two clusters whose average distance is the least.
Will you do partial combination?
What do you mean by that?
So let's say a few points are closer. Will it shift those points?
No.
The reds will become yellow?
No.
Let's say for that single linkage.
Red and yellow will become one larger cluster with maybe different color, representing both of them. Right? So this has to be done across all the data points of yellow, all the data points of red.
Will it be an iterative?
Which one? All of them are iterative, yes. Iterative means, what do you mean?
But finally, when all the points will merge, or how can you tell that there will be distinct points?
You're talking about this one?
Yeah.
Okay, come on again.
So you are iterating, right? And you start merging it.
No, I'm not merging. I'm just calculating the distance right now. So suppose there's a blue cluster here. Any questions?
No.
Hey, no. Suppose there's a blue cluster here. Let's do this. Okay. Now there are 3 clusters here. 3 clusters. Find out the average distance of all of you from all of them. Find out the average distance of all of you from all of them. Find out which average is the least. You merge with that cluster. So these two become one larger cluster. Right? Obviously, average distance of these points from those will be very high compared to these two averages. So I have not considered that. That is what this average method is.
No, what is the minimum limit it will set to maintain the cluster? Is it 2, 3, 4?
All the data points will become one cluster.
All the data
points. Suppose these two clusters are closest than that, all the data points will become one big cluster.
But this would be little risky that it is taking everything, in one go. It is not going point to point, it is taking the whole group and merging the whole group.
Isn't that a better way, because you're taking more variance in your data set to decide which one to cluster?
But what about the boundary points? Those will, create the issue.
No, they will not. So in this case, the boundary points is those two, and these 3 are the boundary points in these 2 clusters. When you merge, they still remain the boundary points in one large cluster. So all the data points put together become one big cluster, super cluster. It doesn't stop. Hierarchical clustering doesn't stop. It stops at that point where you have no more clustering left. Just like in decision tree, the root node, where the entire data frame is a root node, in hierarchical clustering, it stops only when it reaches the root node, where all data points become one super cluster. They need not be. They need not be. I'll just come to you. Just hold on. I know where you're coming from. Yes, ma'am.
In the first example, so you pick those two, which is the closest. So red and yellow is the closest.
Yeah.
Now, if you had picked the red and yellow in the furthermost, so that means distance between red and blue or red and yellow.
Not this blue, the farthest point of the blue. I'm not showing the blue cluster here, the farthest point of blue.
Yeah, so if we had considered 2 other points where red and yellow is far and the distance between red and blue or yellow and blue is smaller,
they would
have merged.
merged.
So then how it will come on the final one? So that means
Okay. Since same question is coming from multiple angles, let's tackle this. So what's happening is, okay, you have 3 clusters. Let me show with triangles and 3 clusters and something of this sort. Suppose I'm using single linkage method. I compare the nearest points. Obviously, this is the least. So I merge these two into, this is one cluster, this is one cluster, this is one cluster. I merge these two into super cluster. When you merge 2 into super clusters, the subclusters don't lose their identity. They don't lose their identity.
In this example, you show that only where 3 clusters are there. In reality, there can be
many, right? And then he asked me, where does it stop? The clustering will stop once all the data points have become part of one single large supercluster, and there's no more data points left to cluster. So this supercluster is your root node in decision tree. The two subclusters is the two branches. Within this branch, you further have subsplits. So what you're seeing here is decision tree. Decision tree is formed based on entropy and Gini. Here it is formed based on this distance between clusters. Did I answer your question? No, I didn't. Again, okay, repeat the question again.
So in this, if we see, then what is the point of the cluster at all?
Just
so
wait.
if we are coming up with the one single cluster.
No. Just wait. Wait. We'll see the point. Yes.
So you are taking the average linkage. You are taking the average distance, right? So how it will be different from the centroid? We can directly take the centroid distance.
No, not necessary. Not necessary. The pairwise distance between these clusters and these, they need not be same as centroid distance. They need not be same as centroid distance. That depends on the distance calculation method you used. He's asked me a very important point. This is slightly slippery because it's mathematical. He's saying average distance of the data points here from here, should they not be same as the centroid distance? Because centroid is the average of the two clusters. It depends on the distance calculation method you use. The distance calculation method should satisfy the triangle of inequality. Do you remember in distance calculation method, I remember doing this in k-nearest neighbors. There are three properties that the method should meet. One is distance between point and itself should be 0. Distance between 2 points cannot be negative. At that time we were laughing. We thought it was silly. You remember all these things? So it's not guaranteed, that's what I'm saying. If you use cosine distance violates that requirement of triangle of inequality. So it can't be guaranteed to you that it will be same. Shall we move on?
Yes. So when you say between A and B, right? You saw the distance between these two.
Yeah.
In the single linkage, the A one.
Single linkage.
You plot these two. The distance was smaller.
Yes.
The second one you're saying complete linkage, maximum distance.
Yes.
Is the same example, can you show that?
Yeah, sure. So in single linkage, we look at say max linkage or complete linkage, where what it'll do is it'll find out the distance between this point and this point, find out the distance between the farthest point here and here, the farthest point from here and here. Of these three farthest points from different clusters, which is the shortest? Those two will get, coincidentally in this case, it's the same cluster, these two will get clubbed.
So if it is very similar, this is the third one, very similar to decision tree. So in decision tree, we get some nodes which we need to prune. So in a similar manner, we will go for this technique also?
Pruning?
Yeah.
We don't need to prune. Why? We'll see that. We'll see. Okay, we'll see why we don't need to specifically do pruning, but we'll see what happens. Right? Still some more length to go before we discuss those
Just
points.
one question
Yes,
for the
please.
classification.
Hmm.
First, we have already done the classification, correct?
Clustering.
First, I asked a question. Will the red become yellow? Based on this, because there are two things going on.
Correct.
First, we have classified. Next, we are trying to kind of build that tree. As part of building the tree, are we going to be smart enough to, again, reclassify?
Yeah. Yes.
We are.
Yeah. In fact, that will be done by the algorithm. The classification, what you're talking about, I know what it's talking about. Let's see how it does that. Shall we? Okay. Let's start with distance matrix. All these algorithms make use of what is called a distance matrix. Distance matrix is nothing but very simple stuff. It's a square matrix. Suppose in your original data set, you had these many records, A, B, C, D, F, G. Okay. And now I'm going to find out the distance between each point in the mathematical space from the other. Distance of point A from point B is 0.5, 0.42, 1, 0.25, and so on and so forth. Let's imagine that this distance calculation is done based on Euclidean distance. Are you all okay? So A and B are 0.5 units away, A and C are 0.42 units away. In case you're unable to connect, what I'm saying here is, I'll just do it between A and B. Distance between point A and B is nothing but the distance on x-axis, distance on y-axis, these two, x square, y square, this is under root of x square plus y square. I'm talking about this distance. Okay? So this is what these distances are. Imagine we are using complete linkage. There are different ways of combining clusters. So I'm going to use complete linkage. Okay? When I make use of complete linkage, it looks for the least max distance between points. Okay? So when you start for the first time, given these distances between the data points, the least distance is 0.2. So it combines F and B and makes them into one cluster. So in the next iteration, the distance matrix becomes BF and rest of the data points. The B and F, they lose their identity. BF becomes one single data point. It's a one cluster, right? Why did you combine them? Because they're similar. So if you combine them, they lose their identity. So BF is now the data point. Now the question is, between BF and say point A, how did this come to 0.62? How did it find 0.62? Correct. Look at the distance between B and A, F and A. In the original matrix, look at the distance between B and A, 0.5. F and A, 0.6. You went for max linkage. So it took the max distance. So between BF and A, the distance is 0.62. Similarly, between BF and other data points, it takes a max distance. Are you all okay? Now look at this. This is called dendrogram. The beauty of hierarchical clustering is it gives you a visual interpretation of what's happening. B and F data points, they have been clubbed together at a distance of 0.2. At distance of 0.2, they have been clubbed together into one. Which means if I look at these 2 points from a distance of 0.2 units, they look like one single point. Right? So these two have clubbed into one at a distance of point. This is called the dendrogramic distance. Okay, you'll understand the importance of this down the line. So this is called dendrogramic distance. Now, in this matrix, where BF is appearing as one single point, now which is the closest cluster to, which are the closest clusters here? If you look at this analysis, the closest clusters come out to be E and A. So E and A get combined and they form one cluster. And both the point E and A are replaced by this cluster called AE. Dendrogramically, the point A and E, they get merged at a distance of 0.1 to somewhere 2 point, whatever it is, 0.25. 0.25. So at the dendrogramic distance of 0.25, A and E appear as one cluster. Once again, apply the max linkage, find out the distance between A and E in other points. Let's look at the distance between AE and BF. What you have to do is you have to see the distance between AF, AB, EF, EB. You will take the max linkage is 0.778. Right? 0.77. So this is my new distance matrix. Once again, look for the least distance. When you do this, you will see that all the data points, individual data points are being replaced by clusters. Then clusters get replaced by superclusters. So AE and CG get merged at a dendrogramic distance of 1, 2, 3, 4 point something. 4.2.
So actually the previous one, when you were combining Yeah, A and BF. At that time, you said that you have to compare E with B and A with F. The
A with F, A with B, E with F, E with B. See which distance? All four here. So I get my this cluster, and finally I end up with a decision tree like a structure where horizontal axis, x-axis represents your data points. What is important to us is the dendrogrammic axis. Some people show it vertically, some people show it horizontally. Okay, next slide, if you see it's horizontal. Doesn't matter. The important point for us is the dendrogrammic distance and the looks. What's happening here is at low levels, okay, these data points are individual clusters, but as we move up in the dendrogrammic scale, the data points start getting coalescing, merging. What is the objective of clustering? Tightest and farthest. Farthest clusters are those which combine at a very high height. Nearest clusters are those which combine at a very low dendrogrammic scale. So those clusters which combine together at a very high dendrogrammic level, they are the farthest clusters. All of you okay? So in my dendrogram, I should be looking for clusters which combine at a very high level. These are farthest and tightest. What we do here is, visually looking at this, I decide at what dendrogrammic threshold should I draw a line. When I draw a horizontal line, that horizontal line will cut vertical lines. As many vertical lines it cuts, that many clusters you get. So if I draw a line at this point, I get 1, 2, 3 clusters. Of the 3 clusters, one of them is an outlier. It has only one data point. But these two looks like they're good clusters. If I draw a dendrogrammic horizontal line at 1, 2, 3.5 or something, then I get 1, 2, 3, 4 clusters. But then, I mean, these two clusters, I mean, they're coalescing just above 0.4, so it's not a good idea. Look at the next plot. Same data set is shown here as dendrogrammic. Okay. If I draw my threshold somewhere here, I'll get clusters and I'll not be able to distinguish. I'll not be able to understand what the clusters are saying. They'll be like box plots overlapping each other. If I shift towards higher values of dendrogrammic distance, then here, for example, 3, I'll get 3 clusters which are very far away from each other. Dendrogrammic distance between the clusters is very large, and they are all balanced clusters. So dendrogram tells you visually how many logical clusters are likely to be there. Logical clusters are those clusters which meet at a very high dendrogrammic distance. Looking at this visual stuff, I can go back and redo my k-means. So the purpose of hierarchical clustering is this. Now, which are the 2 points which are closest to each other here as per this? B and F, right? These are the closest points. So what hierarchical clustering algorithm will do is it will merge these two into one cluster first. So it will show you pictorially like this, where B and F are merging at a dendrogrammic distance of 0.2. 0, 1, 2. This 2 is this 2. So they get merged into one. At this level, B and F become one data point. Okay. So I get my new matrix, distance matrix. Now I need to find out the distance between BF and other data points. The distance between BF and other data points is nothing but B versus C, F versus C, which is the max. Why max? Because you've gone for max. So it does this for all the data points, and you get the distance between BF and all the data points listed out here. And rest of them remain the Euclidean distance which you borrowed from. Now in this matrix, which are the clusters which are closest? 0.25. This is the least. So now what the algorithm will do is it will merge these two clusters into one. So pictorially it will show you this, where A and E are merging at 0.25. Once again, it will recalculate the distance matrix. And this will continue to go on until all the data points have become part of a large supercluster, the mega cluster. This is the root node of your decision tree. This point is this. So when I look at my dendrograms, it gives me an idea about how many clusters are likely to be. I should be looking clusters from, I should come from the top, come down, and I should decide where I need to draw the horizontal line. Wherever you draw the horizontal line, make sure the clusters that you get are farthest from each other. If I draw a horizontal line here, I'll get 1, 2, 3, 4, 5, 6, 7 clusters. But those 7 clusters are same as your data points. If I draw a horizontal line here, I'll get 1, 2, 3, 4, 5 clusters. But no use. These 5 clusters are mostly your original data set itself. You won't be able to understand any logical groupings, nothing will come out of it. So we always look for clusters which merge at a very high level and they are equally balanced, populated. It should not be that one is a large Jupiter, another one is a small moon. We don't want that clustering also. Yes.
So using this diagram, there should be 2 clusters.
2 or
because
3.
3 is that D is outlier.
This is outlier and this is outlier. So maybe I'll have 3 clusters or maybe 2 clusters. You're right. So I'll get meaningful information when I go for k is equal to 2 or 3. I need to check out which one. All right. So another way people draw is horizontally. And in this case, as probably it's coming out, there are 3 clusters here. We can see that there are 3 logical clusters. So I have to draw the line somewhere here. When I do this, one cluster is an outlier. Okay, one cluster is an outlier. There's only one data point in that cluster, but otherwise I'll get 3 good clusters. Very good interpretation of dendrograms. How do they use dendrograms in clustering? I've taken this picture from this URL. Okay, but a point of advice, a point of caution. The structure of your clusters will completely change depending on which method you use to combine clusters. If I use a different method, say single linkage, the structure of the tree will completely change. Generally, in data science, we go for centroid-based max or the average. Single linkage we avoid because single linkage clusters can give you amoeba-shaped clusters in your mathematical space, no particular shape, and they become difficult to interpret. We want spherical clusters, and spherical clusters come out of this average and max distance. These two generally give you spherical clusters. When I say clusters, I mean clusters, superclusters, superclusters. Spherical. Then I have to go and see the data. I'll put these cluster IDs back into these records and go and see the attributes of these records. What is it that makes them come together in a cluster? Then I'll give them a label. I'll say, okay, these are a bunch of people who are interested in sports. These are a bunch of people who are interested in politics. So I will have to interpret those clusters and put a label on those clusters. That labeling is a manual effort. Meaningful label. Algorithm will give you the labels in form of cluster ID 0, 1, 2, 3, but meaningless. The meaning part will come from our analysis. We have to do it.
But when you have multiple data points, more data points, right?
So convert them into box plots and see, based on box plots you interpret. Based on box plots you interpret. What I'll do is, I'll dig out that one example of tech support analysis and I'll tell you how we interpret the clusters using box plots. We'll do that. Yeah?
So we went through the tech support analysis.
We have gone through that?
Yeah.
No, during
the session.
This, session actually we have gone.
Last week?
Last
Then you would have.
We went through the box plots. We spent a lot of time on the box plot session.
Yeah. So I always use box plots to interpret the clusters. A lot of people make use of the centroids to interpret the clusters. You want to know how they do it? I'll just take a fictitious example. Now you imagine you have 2 dimensions. And in these 2 dimensions, this is interest in sports. This is interest in music. Politics is a dirty word. Music. Interest in music. Something of that. Okay. Now you find a cluster here and centroid here. You find a cluster here and centroid here. Okay. And you find a cluster here, centroid. Can you interpret these clusters for me? Can you interpret these 3 clusters? Correct. So these people are those bunch of people who are more interested in listening to music, playing music, but less interested in sports. They'll spend most of the time with guitars and all those things. Whereas these guys, you'll find most of them always on some football field or cricket field, probably watching sports. Okay. These guys do both. How did you interpret this? You interpreted this based on the position of the centroids on the various dimensions. Keep in mind, we have converted them to scale them into z-scores, which means this is 0th value in sports. This is 0, these are all negative, these are all positive. 0, these are all negative, these are all positive. These are a bunch of people who are positive on music but negative on sports. These are a bunch of people who are positive in sports as well as music. So these guys like sport and music. These guys like only sport, not music. You interpret the clusters based on their position of the centroids on the various dimensions. But this is not easy. When the number of dimensions is too many, it's not easy. In such cases, we make use of box plots to interpret the clusters. Box plots would give you the same thing. Move on, shall we? Okay.
Yes. That if we are changing this distance measure like complete NF,
yes.
Is it possible we will get the number of clusters also different?
Yeah, absolutely.
Then if we are using this number, that 3 clusters, and using k means, then there also we are doing it wrong. Right?
Exactly. So finally you will come to know whether what you've done is right or wrong is when you're able to interpret the clusters meaningfully. So visually, when the box plots come very far away, separated from each other on those dimensions, then you can say, okay, I think I got good clusters. But if the box plots are overlapping in most of the dimensions, you are in trouble. So you might have to go back and change your distance calculation method both at the data point level as well as cluster level. Yes. Yes.
But then why, in those particular cases, is there any problem with the ergo method that it is not a
No. Both elbow method, this method, and the Celote analysis, because you said you have done Celote, all these 3 methods should converge to the same k value. All these 3 methods should converge to the same value. At least they should point out the range, the right range. One can't say k is 5, the other says k is 3, the next says k is 15. That should not happen. Visual way of telling you what are the structures in your data set. It all depends on what kind of cluster merging mechanisms you're using, single linkage, max linkage. The structures might change. Only thing is, these structures may not really exist. You have to be careful. If you go very low in your dendrogrammic distance, you're taking a risk. Such structures may not really exist. But when you're on the higher side of the dendrogrammic distance, very likely you're looking at logical clusters. Okay, finally, one very important point when you're going to do hierarchical clustering is what is called the cophonetic coefficient. And you already know the formula. It's just a wine in different bottle. Same old wine in different bottle. So we use a metric called cophonetic correlation coefficient. What it means is, when you build this tree, to represent the distance between the data points at different levels, how much of the original distance between the data points was maintained in the dendrogrammic distance. What do you mean by that? Between these data points, there is some Euclidean distance, the original distance matrix. What is the correlation between that matrix and the final dendrogrammic matrix that you created? What is the correlation? There has to be a correlation. They should be linked to each other, correlated to each other. This original distance matrix based on Euclidean distance. This is the dendrogrammic distance I'm creating at every level, 2 level, 3 level, 4 level. How much of this original distance is reflected in this dendrogrammic distance? That ratio is called cophonetic correlation coefficient. It's nothing but same correlation formula, xi minus x bar into yi minus y bar divided by standard deviation of the two. It's the same correlation formula. I'll show you the formula. Don't get hassled with the formula. This is the formula. If I take all the original distance and find out the x bar is shown as x. If I take all the cophonetic distances and represent their bar, the average is t, xi minus x bar, yi minus y bar divided by standard deviations. Okay, let me show this to you on board. The distance between two data points, okay, this is the Euclidean distance. Now this belongs to one cluster, this belongs to another cluster, and you are using this cluster joining mechanisms, the distance calculation mechanism. Say you used a distance called centroid based distance. Once this data point belongs to this cluster, it loses its identity. It is represented by the centroid. Once this data point has belonged to this cluster, it loses its identity. It is represented by this centroid. So now the distance between these 2 points, A and B, is Euclidean distance is this, but dendrogrammic distance is this. The dendrogrammic distance between A and B is this, assuming you take centroids as distance calculation method. If you use max linkage, the distance will be something else. If you use single linkage, the distance will be, suppose I use single linkage. So the dendrogrammic distance between A and B is now this. So whichever linkage method you use, how close that method is to the original distance calculation. Why do we say this? Why are we doing this? Simple. Now look at this. If you have tightest and farthest clusters, you will see that their Euclidean distance between data points and the dendrogrammic distance between data points will be very close to each other. If the clusters are loose, then the Euclidean distance between the data points and the dendrogrammic distance data points will not converge. So you achieve the objective of tightest and farthest. Your Euclidean distance and your dendrogrammic distance, whichever methodology you use, will be very close to each other. They'll correlate. So when the coefficient of correlation is close to 1, that indicates that the dendrogram has preserved the original Euclidean distance. If the coefficient of correlation is very close to 0 or 0.5, oh, not good. That means you're having very loose clusters. So when you do hierarchical clustering, it will throw this coefficient to you. Based on this coefficient, you can decide whether the linkage methods that you used for clusters is the right linkage method, or should I change and try something else. Okay. There's one more linkage method, which is, for some reason, I don't know why it's not shown. It's called WARD. W-A-R-D. What WARD does is, it looks at these clusters and finds out on combining which clusters, will the resultant clusters have maximum variance, increase in variance. If I combine these 2 clusters, the variance increases phenomenally. If I combine these 2 clusters, the variance increases but not as much. Right? So what distance will combine those 2 clusters which result in minimal increase in variance in the supercluster. Minimal increase in variance in the supercluster. That is called Ward distance. But usually we use max linkage and average linkage. Because we want spherical clusters. Hey, no problem, that's okay.
We are doing this linkage and all on the clusters, right?
Yeah.
First we have to form the clusters.
No, you tell what methodology you use to form the cluster, the algorithm will use that methodology to form the cluster.
So to calculate the distance between the red and yellow, we said, so red is one cluster and the yellow is one cluster, or only the data?
That has been formed, the red and yellow has been formed in the previous iteration. In the next iteration, which cluster should I merge? So every iteration will be merging clusters. Which cluster should I merge? That depends on what method you have used for linking the clusters. So when you first start from the first iteration, in first iteration, all the data points are my clusters. So which cluster should I merge? Euclidean distance. So first iteration over. Second iteration, now I have clusters to merge. How do I merge? Then the linkage methods come into play.
As we see here, like D can come as an outlier.
D can come as an outlier? D can come as an outlier, okay.
And that can change our cluster, like we will take D as a cluster.
Oh, absolutely. In clustering, outliers will form their own cluster. Yeah, it can happen. D is the farthest here, so it can be an outlier. It can end up creating a separate cluster of its own. Can happen. Dimensions, the correlation happens at every iteration. Okay, it's basically xi minus x bar, yi minus y bar. So all these distances, this triangle, sum it up, divide by total number of data points, that is my x bar of this. So xi minus x bar, same way yi minus y bar here, all the dendrogrammic distance, total it up, divide by number of data points. So keep doing this at every iteration. So shall we do a hierarchical clustering on a Wine data set? Yeah, this Wine data set, I think we've already seen this. And the objective is basically to build a model where we can predict the class of the wine based on the attributes. But before we do that, make use of your exploratory data analytics clustering and see whether some useful information comes out of this data set, which can be used to find the direction in your supervised methods, right? So that is the objective. So this is my data, the header data. I'm going to move on, and based on a pair plot analysis, once again, I'm using this to guess the number of clusters. In the first dimension, a single Gaussian with some bumps here and there. But in the second Gaussian, we can clearly see, in the second KDE, we can clearly see at least 2 Gaussians. Yeah. In the third one, 3. In the fourth one, there's one large and followed by small, not reliable. This can become a Jupiter and this can become moons, not good clustering. Same way here also, same way this also. In this, you see there are 2 clusters, one behind the other. In fact, 3 Gaussians sitting here. So based on this diagonal analysis of the KDE, look at this. At least 3 clusters, but looks like many small clusters. So you can drop this. Okay, you can drop this. This is the target variable which is causing the clustering. Since we're going to predict the quality, you can drop this. But what you're seeing on the other dimensions is somewhere 3 clusters. You're seeing some 3 clusters hidden in these dimensions. All of you okay? Move on. I'm making use of agglomerative clustering. I'm using a distance calculation method, Euclidean 6. Okay. I'm specifying number of clusters here. Don't get confused with this. Agglomerative clustering will print out the dendrogram to me. Based on the dendrogram, I'll decide how many clusters I need. But this algorithm requires you to input number of clusters. So let this be the first iteration where the number of clusters is some random number. Don't worry about this. The reason why the algorithm needs this is the output of this algorithm is going to be centroids. How many centroids to generate? So generate 6. We'll see it later whether 6 is optimal or not. Okay. So this 6 is a ballpark estimate, so may not be reliable, but it needs it, so we're given it. You fit the data to it. This is where the clusters will be formed, the hierarchy will be formed. Okay. Oh, I've not run this code. Okay, no problem. Let me move down. And there you go. I asked for 6 clusters, so it's given me 6 labels. And it has given me the centroids of the 6 labels. This is not important. I come down, straight down. Okay. What I'm doing here is, since this methodology stores these labels back into the data frame itself, I'm grouping the data by labels. All the records which belong to cluster 0 should come together, cluster 1 should come together, so on and so forth. This is exactly what we did for box plot in the k-means clustering. It's the same stuff. I'll use this later on. So come straight down from SciPy, Scientific Python, clustering libraries, hierarchical clustering. I'm making use of cophonetic distance calculation, coefficient calculation, dendrograms, and the linkage methods. Now look at this. I'm going to use on this wine dataset average linkage method. Okay, and that average linkage method, I'm going to feed it to this cophonetic coefficient calculator. This calculator is giving me a cophonetic coefficient of 83%, which means 83% of the original distance between data points has been maintained by this dendrogram. Which dendrogram? You'll see it down the line. When I plot the dendrogram, this is the dendrogram I'll get. Okay. In this dendrogram, these are all the record levels. You see a smudge here. This is because there are too many records. It can't be shown on the screen. Okay, and these are all individual records which are getting clubbed at different dendrogramic distance. Not very good place to be in. What we would like to be in is, we would like to be in a place which is very high in dendrogramic distance. So in this, if you look at this command, this plot, I've given a threshold here. What I've said here is, at the threshold of 40, draw a horizontal line. So at the threshold of 40, which is somewhere here below 50, when you draw a horizontal line, it cuts 1, 2, 3, and 4 vertical lines, and you get 4 different clusters: red, light blue, green, and this one. If I change this threshold, I think, let me run this and show it to you. Let's not jump these things. Give me 1 second, please. I'll just run this properly. We've done this, yeah. Okay. This is the one we had originally, okay. If I change this linkage method from 40 to, say, 80 and redraw this, it's a very computationally intensive algorithm, k-means and hierarchical. So many distance calculations have to happen. Yeah. Now look at this. At a dendrogramic distance of 80, which means you are somewhere here. When you draw a horizontal line, you're going to cut only one vertical axis. That means all data points become one cluster, super cluster. If I change this to, say, around, say, I want 2 clusters, I make it 60. It'll recalculate all those things. There you go. I got 2 clusters. But as you can see, one cluster is a very large cluster, the other is very small clusters. If I go for 2 small clusters in the red cluster, if I do that, then I'll have to give a very low threshold. But when you give low threshold, your clusters become uninterpretable because there's not much difference between the clusters. So that is the dilemma. Maybe the linkage method I've used is not right. So the linkage method which I used, if I change the linkage method, say now in this case I'm changing the linkage method here, I'm changing the linkage method to where is complete. Earlier it was average. Now I change it to complete means max linkage. When I redo this analysis, I get different clusters. So every time you change the distance of finding the nearest clusters, distant methodology of finding nearest, your decision trees will change. Once again, look at this. The reason why I'm not happy with this is, if I want equally balanced clusters, I'll have to give a very low threshold. If I give a very low threshold, it becomes meaningless clusters. But at a very high threshold, I'm getting imbalanced clusters. One very large cluster, one very small cluster. Not a good idea. So I change the dendrogramming, the distance calculation method again. This time I take WARD. I draw the dendrograms, and WARD seems to give slightly better results. Now I'm getting at least, if I drew a threshold at say 450 or something, I'm likely to get 1, 2, 3, and 4 clusters, and the clusters are equally balanced, more or less of similar size. Are you able to see that? So if I draw my threshold at this point, somewhere at this point, if I draw a horizontal line, I get 1 cluster, 2 clusters, 3 clusters, 4 clusters, and the cluster size are similar, almost similar cluster size. Let's look at the cophonetic coefficient. The cophonetic coefficient for WARD is only 66%. Only 66% of the original distance has been maintained by your dendrogrammic distance. Many times, this 66% is actually good. We consider it as a good coefficient. You will never find yourself in a situation where the cophonetic correlation coefficient is 1. It will never happen. Crossing the threshold of 70 itself is difficult. So we have to take a call whether this is reliable and look at the dendrogram. At what threshold I get meaningful clusters? Is that threshold sufficient for me to separate out the think that the clusters are different from each other? So what I would do in this case is, I'll go ahead and do a k-means clustering based on this. Whether this is good or not will be decided by whether I'm able to interpret the clusters or not. So finally, the quality of the clusters is subjective. Okay, so these are tools at your disposal for you to decide whether clusters are good clusters or not, but the quality of the clusters will be subjective. Are you able to interpret the clusters meaningfully? And that's a manual process, unfortunately. No, I can use the same centroid, same groupation from this also, I can do that. But I always make use of this to also do k-means, and this, are they giving me similar results? The clusters I get in k-means, the 4 clusters I get in k-means, and the 4 clusters I get here, if I go back and rerun this with 4 clusters, these 4 clusters are giving me similar results. That's what I'll find.
But the cluster group can be different through this.
If they are different, very different, then it's not reliable.
But it can be different.
They will be different.
It will be different.
Guaranteed to be different. How much is the degree of difference? In one cluster it says this is a sedan car, in the other cluster I'm not able to interpret it. Sorry. Clusters will be different. Even though you get 4 clusters both in hierarchy and both in k-means, you get 4. They will be different, but difference should not be too much. Uninterpretable.
You run both of them are dependent, you compare them.
See, the reason why we do so much of things in clustering is this is going to lay the foundation for your supervised methods. You form your alternate hypothesis based on this.
But what is the point in comparing if the clusters are going to be different from that methodology?
If there are 2 different uninterpretable, this guy is saying something, that guy is saying something, is useless. Then clustering mechanism itself is not reliable. If I'm able to see that the 2 clusters are giving similar interpretations, then I'm in a safe zone. Then I'll formulate my alternate hypothesis. I'll say for large cars, NPG cannot be predicted using my acceleration.
It again leads to the data handling again.
Yes. All the magic happens in the data. That was my first sentence when I started this first engagement with you. Okay, this Celote analysis code, yeah. This code I have taken from scikit-learn user guide. Plotting this Celote analysis, it requires a lot of code just for plotting. Okay, so what I've done is, to explain the concept to you, I've taken this code from scikit-learn user guide. So this is my mathematical space or feature space. In this feature space, you are seeing four logical clusters, 4 natural clusters, okay? But imagine we don't know how many clusters are there, we asked for 2. So it gave us 2 clusters. The algorithm, the k-means algorithm has given you 2 clusters. In these 2 clusters, are these good clusters or not? We can find that out using what is called the Celote coefficients or Celote plots. What the Celote coefficient is, it's a ratio. Ratio of, take any data point, Take for example the green data point here, the green one. What is the average distance of this green point from all the points in its own cluster? The pairwise distance. Okay, what is the average distance of the green data point from all the data points in the same cluster? Versus, what is the average distance of this same green data point from the data points in other cluster? Okay, so we find out the ratio of this divided max of this distance or this distance. If the clusters are very tight and far away, I'll write down the formula here, Celote coefficient formula. The formula is max of, I'll take A comma B, where A represents the average distance of a data point from other points in the same cluster, the cluster to which it belongs. Okay, B is the distance of the data point from nearest data point in other cluster. Okay, so you take this one cluster, take any point here, find out the average distance of the point from the other points in the same cluster. Let's call it A. Find out the distance of this data point from the data point in the nearest cluster. So A by max of A comma B. Max of A comma B, if you have tightest and farthest clusters, it will always be B. The ratio will always be A by B. This will always max up. Okay. Now, what you see here as a continuous plot is actually not a continuous plot. It is different lines placed on top of each other. Look at this edge. It is jagged. So these are lines placed on top of each other, each line for one particular green point. The Celote coefficient is max for the point which is farthest from the other cluster. The Celote coefficient, this one, the last row here, this is the Celote coefficient of the green point, which is the closest to the other cluster. So here for this green point, the average distance of this point from the other points versus the distance of the other points in the other cluster, these two are almost similar. The ratio is almost coming to 1. Yeah. So this row, this green line over here is the Celote coefficient of the nearest point. This is the Celote coefficient of the farthest green point. Same way in black. In black, the farthest black point will have the highest Celote coefficient. The nearest black point to the other cluster will have the least Celote coefficient. And in between will be the other data points. Now, when you find this kind of a Celote plot, where one cluster is very large, the other is small, you are in a not a right zone. You are not in a right zone. Other thing is, you look at this red dashed lines. This red dashed line is average Celote coefficient of all the points. average Silote coefficient of all the points is what this red line is. And as you can see, most of the black points have a Silote coefficient less than the average. Not a good idea. When I change this from 2 to say 3 clusters, though there are 4 clusters, I don't know there are 4, so I try k is equal to 3. Once again, you see the Silote coefficients for each point in each cluster is shown here, and the black cluster is performing very poorly. Not a good idea. When I make this k is equal to 4, where it reflects the natural number of clusters you have in your data set, you will see that all the clusters cross the average Silote coefficient boundary. And good part of the cluster is on the right side of the average Silote coefficient. And their distributions are also similar in size. You got the tightest and natural clusters when you have right k. So Silote coefficient is the ratio. The ratio on the numerator, you have the average distance of a point from its own clusters versus distance of the point from the nearest cluster. This ratio is called Silote coefficient. When the clusters are touching each other, very close to each other, you will see that they are very close to the boundary. The black cluster is touching the other clusters. It's very close to the boundary. Yellow cluster is touching the other clusters. It's very close to the boundary. Whereas blue cluster is tight and far. Most of the data points have very good Silote coefficients.
Looking at this diagram, how much is good in terms of the distance after the dotted line? Right? Difficult to say that.
Overall, what it's telling you is all the clusters are crossing the points. Good. They are similar in size. Good. Okay. Of course, yellow cluster and the green cluster is still a concern, but that is because they're touching each other. They're touching each other. That's why you're finding that.
And again, to clarify on B, point B, is the distance of that data point versus every point in the nearest
cluster.
Average.
Nearest cluster, yeah.
Average distance.
Yes, average distance. Yeah.
So the red.
I'll take her first, then I'll continue. Yeah.
So when we did this assignment, so we got one table, one matrix kind of thing, where the variance was there, average Silote was there, and centroid was there, if I remember correctly. So if I have numbers, I mean, I think that this range between 0 to 1, and then for 2 cluster it was giving some average Silote, then for 3 cluster it was giving some average Silote number. So how to interpret that?
The max Silote coefficient you get, the better the clustering is.
Okay, so for different 0 to 3, where I will get the max one, that I will...
That is the best Silote coefficient. That is the best clustering.
And that I can consider for further analysis.
Yes.
Okay. So variance should be minimum and this should be maximum.
Yeah, correct. So Silote coefficient, elbow method, then visual analysis, all these methods should converge to a small range within which you should find your right clusters.